Hi everyone, my name is Ian Abraham and I'll be presenting our work on Stein variational ergodic search. This was work done in collaboration with Derek Lee from Oxford University, Cameron Lurch, my PhD student at Yale University, and Fabio Ramos at NVIDIA and University of Sydney. So exploration is rather hard. Robots need to decide where and how to explore, and there are infinitely many options to choose from, all of which provide some meaningful amount of information that the robot can use to do tasks like mapping, data collection, surveillance, and general information gathering problems. We often want our robots not to just choose one way to explore, but to keep track of multiple exploration strategies. This is especially true in dynamic environments where the environment may make it difficult to collect data in certain regions. So we're looking for notions of robustness to worst case scenario. However, there are a few open challenges that we need to address. First is, how does one even go about capturing the multiplicity of exploration solutions in an optimization formulation? And second, how do we go about efficiently optimizing and enumerating the potentially infinite number of solutions? So our approach is to consider the problem of coverage as an inference problem. Specifically, we treat exploration as an inference problem over ergodic coverage trajectories. In this case, we use the spectral ergodic coverage methods that balance where to explore based on minimizing the distance between time spent covering an area with respect to the expected information distributed in that area. The spectral ergodic metric provides a likelihood model that captures the multiplicity in the ways to explore and cover an area. Then we leverage Stein variational inference methods to efficiently solve an approximate posterior distribution on exploration strategies. These Stein variational inference directly optimizes a posterior distribution that can be used to provide several candidate trajectory solutions for exploration. So an additional benefit of our approach is that the Stein variational inference problem can be solved in parallel. In combination with the spectral ergodic metric, which can also provide further parallelization, promotes favorable computational scaling, and as a plus, we can get exceptionally fast inference times which can be used for planning and control for exploration. So we find that our approach produces several diverse exploration strategies. Here is an example of an output of our approach generating 4 trajectories to uniformly explore the 3D space with several obstacles. Note that the optimal chosen trajectory, shown in green, was determined based off a heuristic that sought for the lowest control effort trajectory. In particular, we find that our proposed approach generates a diverse set of solutions by first leveraging the Stein variational gradients to diversify solutions and then converge on locally optimal solutions facilitated by the ergodic metric. We demonstrate the effectiveness of our approach as well as the massive parallelization permitted by the spectral ergodic metric and the Stein variational approach to cover the shown information map underneath, subject to the obstacle avoidance constraints shown by the green obstacle. So you can see the exploration strategies shown in black provide several strategies to explore the 4 modes underneath while avoiding the obstacle. In addition, our approach facilitates sensor-driven exploration in an online setting. Here we demonstrate multiple redundant coverage solutions using a sonar-based sensor to map an environment shown below. Note that the exploration plans are readily adapted as data is collected and the information evolves. An advantage of our approach is that we are independent of the chosen sensor model and the dynamic constraints of our system. We further show the potential of our approach for exploring in a highly dynamic and cluttered environment. Note that our approach provides several candidate paths that can be chosen from at any given moment, allowing the robot to sample from these 4 peaks shown below while avoiding all the obstacles shown in green. For more information, please visit our paper at the RSS website, and we'll be at the post session for more questions.
Thank you, Ian. Do we have questions from the audience? Raise your hand if you have one, and you will get a nice box. Yes.
Hi, Ian. Can you talk a little bit about guarantees that you have? I noticed that the obstacles were soft constraints, for instance.
Yeah, they're soft constraints. So we didn't implement any hard constraints purely for lack of laziness, because that wasn't the point of the work. So we don't have any constraints on obstacle avoidance. However, we can at least make some statements that we can eventually find a trajectory that does avoid the obstacles. We can just search for that. But there's nothing that prevents us from using an augmented Lagrange method or some interior point method to actually guarantee those constraints. The hope is that eventually you do find a solution, because the gradients actually do provide the Stein-Vector gradients do provide many solutions. We should at least find one, which is kind of convenient. Yeah.
All right. Do we have one more question from the audience?
It's early in the morning.
It's early in the morning. I would actually have one question.
Yeah, go ahead.
Can your framework deal with some like set defined tasks, such as gaze somewhere or see something periodically, but not go there in particular?
I don't see why not. So the thing that gets us the multiple solution or the multiple trajectory solutions is the Stein variational method. The thing that we care about is actually whatever optimization metric or likelihood model we're using, that it has more than one local minima. Otherwise, you're just going to get one local minima, or you're going to get spread out around the local minima in different level sets of it. So you could include that as a cost function and get to this point at this time. So long as we got these exploration strategies that are being generated, that's fine as well. Yeah.
Okay, thank you very much.
All right, thank you.
Thank you, Ian. And
Yep.
Thank you. While we set up, for those of you who joined since the morning, can the next speakers of the session please line up on the first row so that we can call you up swiftly, continuing. Our second presentation will be by Wilson Jallet. Wilson, the floor is yours.
Hi everyone, I'm Wilson Jallet. I'm a third-year PhD student between Paris and Toulouse in France. I'm going to talk about nonlinear model predictive control and how to make it faster. So NMPC is a way of getting really nice motions really quickly, but are rich. You can put in your dynamics, you can put in your constraints, and if you want to be good, you can go high dimensional and body models like Talos you saw before, okay? What you do usually if you have constraints, you can do SQP, interior points, augmented Lagrangian, and you have to compute some kind of second order step using a Newton method. You usually get some kind of linear quadratic sub-problem as your iteration problem, sometimes with some dual organization since you're doing interior points or augmented Lagrangian. It leads to a nice structured linear system like this, that's nicely block banded, and you have a bunch of tailored methods to solve it. The classical one is the Riccati recursion. Well, the problem with Riccati, of course, is it's fast, but it's still linear in time, okay? Let's see an example of how it works for n equals 2, okay? You set up your cost to go matrices and vector. You formulate some kind of equation over your co-state. So people know the PMP will know about this. Then you fold it into the initial system and you rinse and repeat. You can extract your co-state and feedback in state, okay? Your control feedback. Now the question is gonna be, this is good, okay? We know how to do this. We can even enhance this for constraints. So we have an example of that in the paper of how to extend it to constraints. The question, how do you speed it up? How do you go multi-threaded, okay? So we have an answer for this, is to parameterize, to parallelize your solver. So you introduce your Hamiltonian, your Lagrangian, okay? And you're gonna take a look at some of your stages and say, let's split the problem on some of these stages. So maybe try to be uniform, okay? So we're gonna select a subset of stages, okay? Set up a parameter that's gonna be the last co-state that links to the rest of your problem. And we're gonna look at the Lagrangian and just take the sub part, okay? A subpart that's going on our subset, okay? And we solve a parametric Riccati recursion and we condensate this subproblem, but going to T1, into a primal dual quadratic form. So this is kind of a partial condensation. And then we do this in parallel across a partition of your time horizon, okay? Usually take as many partitions as you want to use threads, and then you reduce to a nice three-diagonal block system that you can solve using, I don't know, Cholesky. We have an algorithm for this in the paper. So we did a bunch of synthetic benchmarks on a M1 Studio Mac with a fairly high dimensional system that's actually a quadruped. We just extracted a subprime from a quadruped. You get a nice 2x speed up using 4 cores. And the more cores you add, the better performance you have until you reach something that's going to break your cache. We plotted what we think is a good upper bound on the speed up. And you can see that you don't get 100% efficiency. That's because you added right-hand sides to be able to separate the problem. So you're going to pay your price. You have no free lunch here. Then we tried it on the actual quadruped. We did NMPC on the quadruped. We went from 10 milliseconds on 2 cores to 5 milliseconds on 6 cores. So it's a fairly good speed up. Let's see the motion here in action of the actual solo 12 quadruped that you can get online. It's open source. You just need to print it. So we get some nice cute motions here. And it's actually running a full 1 second horizon here. So you got 80 time steps, which are 12 milliseconds each. And we also tried a nice little humanoid that's actually Talos. We have a real one in Toulouse. We didn't have access to it during making of this paper, unfortunately. So we ran it in simulation in Bullet, okay? So this is a, 2 second horizon? No, it's 0.5 second horizon. We got 50 time steps, 10 milliseconds each. So we get a nice motion here. We've got a bunch of constraints here. So on the range cone, etc. This is all implemented in our framework called Alligator, which is open source. You can get a link by going to the poster and scanning the QR code over there. It's open source. We hope it will be useful to the community to unleash more complex models for whole body manipulative control on real robots, hopefully. Since we went parallel, we can start cutting down on the time it takes to solve one iteration. Okay, thank you very much for listening.
Thank you, Wilson. We have time for questions from the audience. Raise your hand if you have a question. Yes. Yeah, up there. Thanks to our volunteers who jog to the question askers. Don't fall.
Thanks for the nice talk. I'm wondering, have you compared to other QP solvers? There are many out there from the MPC community. And how do you deal with non-convexity and invisibility? Thank you.
So we don't actually deal with these problems at the QP level, okay? So this is just the linear quadratic iteration. This is just computing the Newton step. We actually deal with non-convexity and all these things using visual heuristics for augmented language solvers in our framework. So this is at the top level algorithm. Because we're not actually solving the constraint QP here. We just, it's like if you select the active set, you just get equality constraints and you just have to solve a linear system. So this is all we're doing here. If you want to solve a non-convex problem using the full solver, you just need to select this thing as a backend. This is just a bunch of linear algebra tricks at the end of the day. Does that respond to your question satisfactorily? Okay.
Yes.
I can see your.
You can discuss also afterwards. We have time maybe for one quick question. No, quick one. All right, then thank you very much, Wilson. And our third speaker, yes. Thank you very much. Will tell us about differentiable robust MPC. The floor is yours and the video has started.
Okay, so tube-based monopredictive control, or tube MPC for short, enables safe, robust, and real-time control of nonlinear systems acting in the real world. The robust control problem is made amenable to real-time MPC by dividing the problem into 2 optimization layers. The first layer is a nominal MPC that generates a deterministic nominal trajectory that solves the task in the absence of noise or disturbances. The second layer, the nominal MPC is then augmented with an ancillary MPC that performs feedback on the state of the system ensuring it lies within some safe distance from the nominal trajectory. Plotting the controlled trajectories for all possible realizations of disturbances results in a safe tube that is centered around the nominal trajectory. However, tube MPC approaches fail when encountering out-of-distribution disturbances, which could occur due to environmental effects or large sim-to-real gap. For example, if we encounter a large state perturbation, the tube MPC will fail, causing large deviations from the nominal performance and unsafe solutions. To address this shortcoming, our idea is to use differentiable optimization to adapt the tube MPC based on the observed behavior of the system. To do so, we'll define a high-level task objective that arises naturally from the problem formulation of tube MPC. This loss function is a function of the solutions of the nominal and ancillary MPC problems, and by minimizing this objective online with respect to both controllers' parameters, the tube MPC is made adaptive, resulting in trajectories that are automatically adjusted to prioritize safety and allowing the controller to rescue poor performance caused by a large sim-to-real gap. Minimizing this task objective requires backpropagating through both of the MPC optimizations. This is accomplished in a fast and accurate manner by drawing connections between the gradient backpropagation and dynamic programming. This allows us to exploit the structure of the optimization and the theoretical results generalized prior works in differentiating through the solutions of MPC problems. Now I'll present some results demonstrating our approach on safe vehicle tasks in the presence of large state noise. NT-MPC here is a standard nonlinear tube MPC approach without adaptation. Trajectories controlled under NT-MPC deviate from the nominal and the majority cannot reach the goal. Meanwhile, DT-MPC results in safer trajectories that complete the task with higher probability. Furthermore, we observe a beneficial emergent behavior where the tube size and shape naturally narrows when the system is most unsafe. We find similar results when applying the framework for the control of a quadrotor system in the presence of large disturbances and many obstacles. Next, we applied our method for the control of the Majoko cheetah system. We see here on the left that the NT-MPC without adaptation is unable to respond to large noise in the environment, causing the cheetah to flip over. Meanwhile, our approach on the right continuously adapts to the environment, producing a stable behavior even in the presence of large disturbances. We also perform a similar comparison on the quadruped system. NT-MPC gets stuck because the true state diverges from the nominal one due to the large noise. To fix this failure case, DT-MPC adapts the controller parameters online, ensuring the true state remains close to the planned nominal state. This results in the successful jumping maneuver you see here on the right. Finally, we present a hardware experiment on the Georgia Tech Robotarium. Here we see NT-MPC successfully completes the task while avoiding 5 other stationary agents. Next, we let the other agents move with some small random velocity, which introduces some non-stationarity into the environment. This causes NT-MPC to quickly violate the prescribed safety of the system because it cannot effectively respond to this shift in task. Meanwhile, DT-MPC maintains the desired safety of the system by continuously adapting to the other agents. We'd like to highlight some of the smooth turning maneuvers that are made possible because DT-MPC continuously adapts in order to maximize the predictive performance of the controller. So in conclusion, we propose an adaptive tube MPC framework for safe real-time control of nonlinear systems. Our approach solves common failure cases of tube MPC, such as a large sim-to-real gap. We apply differentiable optimization to enable the tube MPC to respond effectively to the environment. The backpropagation through the MPC layers is fast by exploiting the structure of the optimization. And we provide some generalizations of previous work in differentiable control. And finally, in the paper, you can find an analysis on the accuracy of the gradients produced by our differentiable MPC algorithm. Thank you.
Thank you very much. Do we have questions from the audience? Raise your hand. I would actually have one question about the tube MPC. So one common issue with tube MPC is that what happens is if the problems become infeasible or like the tube is too large, do you have some guarantees in your framework that this is not going to happen for the ancillary MPC?
Yeah, so that's a good question. So yeah, there's a few ways we can handle that. One of the things that we propose in the paper is to use, okay, so the way we're handling safety and essentially the constraints on the problem is through embedded barrier states. And that's essentially you're going to augment the state of your system with a barrier. And that barrier kind of has dynamics that you can define. And then we use ILQR to actually solve the control problem. And basically your solution is safe as long as that barrier state is bounded. And what we're proposing to sort of attack some of these infeasibility scenarios is to actually relax the barrier state, relax the barrier a little bit, introduce some slack essentially, and that kind of allows you to still get a solution, but it's still gonna push you away from the unsafe region due to the effect of the barrier.
Okay, thank you. Yes.
Yeah.
Do we have one quick question? It is. Yes, we have a quick one. Thank you.
Can you tell us the level of observation noise in your hardware experiments, and if you have done some ablation of how things deteriorate as it increases?
Yeah, so we didn't do any ablation experiments. That's kind of something we want to get to, I think, in the future. But yeah, for the hardware experiment, the observation noise, so we use a Dubin's vehicle model, and it's I think in that particular experiment, the noise standard deviation is not very large. It's like 0.02 or somewhere around there. And then we're actually focusing more on how the model is sort of mismatched from the real hardware and the kind of observations we're getting in there. And that's kind of what we're using to adapt the controller, if that makes sense.
Thank you very much. Thank you.
Good morning, everyone. I'm Wei. On behalf of my PhD student, Wen Han Cao, I'm very happy to present our paper, Computational-Aware Learning for Stable Control with Gaussian Process. This is a joint work between Manchester, TU Munich, Carnegie Mellon, and Tsinghua. It's I have to click.
Should skip. Is it started?
Gaussian process is broadly applied in robotics and control. However, GP machine learning or Gaussian model is notorious for its expensive computations, especially on mobile and edge devices, such as onboard computing, tiny mobile robot, or effect of processor overheat. In this paper, we want to ask one question: how to guarantee the stability of a GP-based dynamical system under limited computation? How to learn robot dynamics using Gaussian process? Typically, a dynamical system can be described by ordinary differential equations. When these equations are unknown to us, we can learn the dynamics using the observed data. In the Gaussian process machine learning, typically, we have a Gaussian prior, then we can predict the future behavior of the state in a dynamical system using the posterior mean. And also, we can quantify the prediction confidence or prediction uncertainty using posterior covariance. The most computationally expensive part is the inversion of this matrix K, which is known as the kernel-Graham matrix, to characterize the correlation of the input data. To solve the most expensive part is equivalent to solving a linear system probabilistically using numerical optimization algorithms to process the data or computation sequentially to save computations. And these iterative optimization algorithms can be regarded as Bayesian inference. And this Bayesian viewpoint allows us to decompose the posterior covariance or prediction uncertainty into two parts: mathematical uncertainty and computational uncertainty, which are corresponding to the effect due to limited data and the limited computations, respectively. When we learn the dynamics of inverted pendulum, if we use all the data, there's only mathematical uncertainty, colored in blue on the left-hand side, and the region of attraction or the initial safe condition will be very similar to the true one. If we reduce the computation, the computational uncertainty will increase, which colored in green on the left-hand side, and the region of attraction or the safe initial condition side will become smaller, more conservative, which is better. If we don't consider computational uncertainty, okay, the region of attraction will become larger than the true one, meaning that the system will start from unsafe initial conditions. Bad. Finally, we established the GP model-based stability condition and derived optimization-based control. Similar to the typical model-based stability condition based on Lyapunov function V, in this new GP model-based stability condition, we replace the true model as its upper bound, then derive this inequality, which incorporates both computational uncertainty and the mathematical uncertainty explicitly and respectively. Then we can use this inequality as a constraint in the optimization-based control, which can be solved efficiently using SOCP solver to update onboard. In the online model learning, a trajectory will track a trajectory, for example, ship infinity with water slosh dynamics using limited computation. All the computations are performed onboard using NVIDIA Jensen Orin. In the setup, we reduced the update frequency or learning frequency to save computations. If we use all the computational resource, the tracking errors by using computation-agnostic controller will be very similar to the one using computation-aware controller. If we use half of the computational resource, the tracking errors by using computation-agnostic controller will become worse. If we only use 20% of the computational resource, the tracking errors by using competition-agnostic controller will become much worse than the one using competition-aware controller. In this paper, we propose a new method called competition-aware learning for stable control with Gaussian process. This method is promising for online model learning and control in robotics and limited computations. Thank you.
Thank you very much. Do we have questions from the audience? Raise your hand if you do. Yes, we have one question here. Thank you.
Thank you very much. Very, very nice presentation. I'm just wondering two things. The first one is how you can be sure that the K inverse is not going to be singular at any point doing the probabilistic approaches. And if you consider white noise, you can incorporate on the Lyapunov function something close to the Kalman filter, something like that? I'm just wondering. Thank you.
Okay, this is a fantastic question. Yes, for the first question, actually, we do a lot of experiment, and we found that the matrix can be singular, and we choose the one without introducing this singularity. And this is related to the question regarding how to actively collect the data, which has more information to access the system. We haven't touched that yet, but it's a very interesting direction in the future. And so far, we just do that empirically. Regarding the second one, so as you can see, the iterative optimization method can be regarded as recursive Bayesian inference. So essentially, Kalman filter can be regarded as recursive Bayesian inference. That's essentially the idea. So that's why we're using this method to do that. And the key insight from that, okay, for Kalman filter, you have the covariance, but now we also have the covariance for the prediction. And this can be decomposed into two parts. So that's the key insight. And also in the community, which is called probabilistic numerics, okay? And people solve, okay, solve differential equations using Kalman filter. So it can be also considered as a estimation or prediction problem. Thanks.
Thank you very much. Thanks. Let's send the speaker again.
Hi, everyone. So we are calling out the five speaker. Are you around? Yu Peng Wang, Yu Liu? If you're around, please come to the stage.
Hello, everyone. I'm Yu Peng Yang. Today, I'm going to share our recent work on how to maintain long-set connectivity for a group of robots. A multi-robot system may consist of different kinds of robots to conduct different tasks at the same time. For example, a group of mobile robots divided by two sub-teams or tasks to spread out the space with different sub-team level goals to ensure the robots are within the certain distance so that they can cooperate and share information smoothly. They need to maintain first subgroup connectivity so that they can share information smoothly within the same subgroup. And second, they need to maintain global connectivity. In this way, the entire robot team can work as a whole component. This well-connected multi-robot system has a lot of applications, such as field exploration and 3D mapping. Traditionally, people consider that if the robots are within the communication range, they can communicate and share information with each other. However, if the robots use Wi-Fi or Bluetooth signal to communicate, the signal will easily be blocked by the obstacles. So, in this paper, we consider the line-of-sight communication, which requires the robots are not only within the communication range, but also remain occlusion-free from obstacles. And it is even changeable to maintain connectivity for the robot. While robots are moving, traditionally people use the perfect positional information to decide the boundary condition and the control constraints for the robot to be connected with each other and revise their original controller to ensure the robots are always within the communication range so that they can communicate with each other. However, in reality, the robot's position information are from GPS or state estimation process, so the position information may be incorrect, and it is hard to use this imperfect position information to decide the boundary condition and the control constraints, and hard to decide how to revise the controller to ensure the required connectivity. As we discussed before, it is hard to maintain line-of-sight connectivity even for two robots. For the multi-robot cases, the question becomes more challengeable. For example, given the current robot position, we can get the current line-of-sight communication graph. We definitely don't want to maintain all edges to be line-of-sight connect, because it will introduce unnecessary motion constraints on robots, so they cannot perform their tasks well. The first question becomes to how to determine a subgraph which requires less motion constraints to maintain. For example, instead of maintaining every existing line-of-sight edges, preserving only the right edges while moving makes space and thus providing more motion flexibility for the team. And then, with this graph, how can we develop the motion constraints on each pairwise robot to ensure safety and line-of-sight connectivity over time under noisy observation? Finally, how to solve the problem in a decentralized way? To solve all challenges mentioned above, our method first constructs the current line-of-sight communication graph based on the current observed robot position. Then, we use a graph-based method to find the best subgraph to maintain, which has the minimum number of edges to be line-of-sight connect, and their subgroup a line-of-sight connect. And finally, it is easiest to maintain. Hence, our control strategy is that we seek to minimally modify the task rate controller so that it is safe with satisfying probability and line-of-sight connect with satisfying probability subject to the best graph. And finally, we use a modified CADMM method to find the best graph and solve the resultant control revision problem in an iterative and decentralized manner. At each time step, given the task rate controller, our algorithm minimally modify it and give you the desired satisfying controller that guarantees the desired safety and line-of-sight connectivity. In summary, we provide the greatest flexibility for the robot control while ensure the desired global and subgroup line-of-sight connectivity and safety. Finally, we show our simulation results here. The original task performance is that different color robots will move to different task regions and perform different tasks. The gray edges are the current line-of-sight communication graph. The red edges are the selected graph, which are calculated based on our method. The dashed circle is the observed robot position. The colored circle is the ground truth robot position. In the middle, if the method doesn't consider the positional uncertainty, the robot will easily lose line-of-sight connectivity. And on the right-hand side, if the method doesn't dynamically update the edges to maintain, the robot control will be dominated by the requirement of line-of-sight connectivity, which cannot perform their tasks well. Compared to those two, the result from our method, shown on left, not only guarantees the desired safety and line-of-sight connectivity, but also ensures the best task performance. Besides, we also use real-world experiment to validate our method. The original task performance is that the black robots are moving to task region 1, and the white robots are moving to task region 2. Here is the performance of our method. The robots using our method are able to form an ad hoc formation, which can ensure the robot reaches the task region at best, while ensure the line-of-sight connectivity. Thank you for your attention. This is my contact information, and this is a paper link. Please feel free to stop by our poster. We are looking forward to interacting with you.
All right, thank you. We have time for a couple questions in the audience. Is it? No. Is the video?
There's no question. Okay.
Yeah.
We have a break.
Yeah. So we wait a little, so we are on time. If Rafael, Javier, if you want to come to the stage and set it up. Right, so the next speaker is Rafael Borks. Rafael, you can start.
Hello to everyone, and welcome to my presentation on Hamilton-Jacobi reachability analysis for hybrid systems with forced and controlled transitions. A hybrid system is a class of system that displays both continuous and discrete behaviors. They are particularly powerful for capturing systems that have multiple operation modes or contact-rich applications, as they are naturally captured by these kind of frameworks. But ensuring safety for this kind of system is usually hard because we require to reason simultaneously about both continuous and discrete controls. Tackling this problem from a reachability perspective is our goal in this project. For this, we pose the question, can we find an initial set of states that under some optimal policy can guarantee safety of a hybrid system? The problem setup is as follows. We will define a set of discrete states, here represented as circles, each one with its own dynamics and operation domain. From within this operation domain, we might be able to transition to another discrete state whenever we want through a controlled transition, such as switching gears in a car. We might also be forced into another discrete state because we exit the operation domain, such as losing contact with the ground in a jumping robot. The safety for this kind of hybrid system can be guaranteed through a backward reachable tube, or BRT for short, which captures all the initial pairs of continuous and discrete control that, following an optimal policy, can reach or avoid a target set within some time horizon. The key result of our work is a theorem that captures this BRT through an underlying value function for the hybrid system. Due to time limitations, I can't go into the details, but I will shed some intuition over this result. Here we consider the cases for states inside and outside the operation domain. For states outside the operation domain, we have to take a forced transition, and the optimal decision is obviously to go to the state with the minimum value. For the states inside the operation domain, we first need to rearrange some terms. Here, we also have the option of taking a controlled transition into another state, but we could also forward propagate in time using the dynamics of the mode as in classical Hamilton-Jacobi reachability, while also keeping track of the minimum cost ever acquired over this trajectory. In summary, what we're doing here is applying dynamic programming principle over all the possible continuous and discrete controls to get this value function. We also provide a numerical method to approximate this value function while minimally modifying the previously presented result. This gives us a numerical tool to actually calculate this value function and the continuous, optimal, and discrete controls. We test this in a simple example of a one-leg jumper that has two main discrete states, a stand state that can push against the ground and a flying state. Here, we show in blue the BRT for all the states that can reach this target region in green while avoiding colliding with the terrain. The transition between modes is captured by whether the leg is in contact with the ground or not. Here in this animated trajectory, we show how the system evolves within different slices of the BRT. We also highlight how the system first builds momentum to take this optimal transition. This continuous control action is not hard-coded, it just emerges out of the reachability analysis. Next, we test this framework on the high-level planner for a quadruped. This system has multiple locomotion modes that it will try to use to reach the pink goal region. Here we see the robot leveraging the right slope, where it uses a normal walking mode into a slope walking mode, into a very slow walking mode to take that tight turn to eventually reach the target set. To show that the system is robust to bounded disturbances, here my co-author Shuang is kicking the robot as it tries to take the ground route when the right slope is not available. Here, the state feedback controller continuously tries to take the optimal continuous and discrete actions to try to reach the target as quickly as possible while still avoiding collision with the obstacles. To conclude, we present an extension for classical hybrid Hamilton-Jacobi reachability. We also present a method to capture the BRT for such method and a numerical algorithm to capture this BRT for any generic hybrid system. Thank you for your time.
I have some time for questions here.
Hey, really good work. One question I had was, it looked like most of these systems are still continuous in some sense. While they do have a hybrid transition, the slip model that you use is still continuous, right? Is there an assumption you've made about continuity, but it is still hybrid transition? Or, for instance, a bouncing ball will have a impulse change, and then
yeah, you mean continuity on the states. The
yes,
system also considers states
right.
have reset maps when we can like teleport a state from one part of the state space to another. It also manages those kind of transitions. They're not in any of these two examples that I showed here, but in the paper we have an air collision example where we take instantaneous transition in the state space to show that it also can handle these like state reset maps.
The value function would look really nasty, wouldn't it?
It would? What?
How do you compute the value function in that case?
Oh, in this case what we're doing is that the value function is being represented over a grid. So when we do a state transition, all we have to take care is like which state maps to which other state on this other grid. So it's cumbersome, but it's doable.
Thank you. I have time for one more question. Over here. Thank you.
What's the dimensionality of the problem that you can deal with? Because you did mention kind of discretization.
That's an excellent question. Hamilton-Jacobi reachability is known for being very bad at scaling with dimension. The normal Hamilton-Jacobi reachability analysis scales exponentially on state. And here with the reset map condition and the multiple states, we have the same exponential scaling plus an extra quadratic scaling in the number of discrete states. So this is usable for fairly low dimensional systems. Actually, what we're trying to do now is extend this to a system that doesn't use a grid and use a learning method to actually capture this value function without having to deal with this like obviously exponential nature of a grid.
All right, let's thank the speaker.
Thank you.
Thank you. So the next presenter will be Nico Uday. Nico, your stage.
Yeah, so hi, my name is Nikhil. I'm a PhD student at UC San Diego, and today I'm going to be presenting our work, Jiggle, an active sensing framework for boundary parameter estimation in deformable surgical environments. So for this presentation, I want you guys to start by considering the problem presented by these two deformable tissues here. Just by looking at them, can you tell me how they're attached to the environment? Well, no, not really, right? Like at first glance, they look pretty much identical. So to do this, we have to actually actively interact with the environment. We have to, well, jiggle. So the natural next question that arises is, what action should I take in order to kind of best discover the environment? And the thing is, surgeons do this kind of all the time. They need to constantly manipulate the tissues in order to understand the structure and the attachments in the environment. And these attachments are actually really important to surgery. A large part of surgery is spent either removing these attachments to do things like access the site of the surgery or resect some diseased tissue, or to create attachments through processes like suturing. So inspired by this, we present Jiggle, where the core part of our method uses the discrepancy between simulated and observed interactions in order to compute a probabilistic update on the boundary attachments, which we then leverage to compute effective and safe future actions. So we divide our method into kind of two main parts, estimation and active sensing. So let's go ahead and start by talking about estimation. We represent our tissue for estimation using a PBD, or position-based dynamics simulator, which is fully differentiable. And in order to represent those boundary attachments, we use springs of varying strengths that attach to virtual particles which are fixed within the environment. In order to kind of probabilistically track those boundary attachments, we use an extended Kalman filter, which has kind of two major steps: a predict step, where we evolve the boundary attachments based on some assumed motion model, as well as an update step, where we incorporate in new observations. The key thing here is that that update step involves computing this Jacobian J, which we're actually able to really easily obtain by leveraging the differentiability of our PBD simulator. In order to kind of demonstrate our estimation capabilities, we use real-world experiments where we actually sutured chicken skin onto chicken thigh in order to create these ground truth attachment regions. Now, notice that as we deform the tissue, the regions that are deformed actually decrease in uncertainty, which are shown in blue, as well as the estimated attachment points, shown in purple, began to closely match the ground truth. So now that we've figured out estimation, let's move on to active sensing. Our active sensing framework mainly aims at maximizing information gain while respecting safety-critical constraints that are particular to surgery. So for information gain, we actually prioritize deforming uncertain regions of the tissue, and we enforce safety by constraining the spring energy on the estimated boundary constraints. We also add a soft constraint in order to penalize actions that exit some safe workspace, and we show our objective function at the bottom of this slide as a sum of these terms. To actually select that next action, we start with an initial set of large action samples. What we can then do is we can iteratively kind of update these action samples based on the gradient with respect to our objective function, and then we finally select that best sample and take a small step in that direction. Here we show some simulation results on active sensing. So the video shows regions of increased confidence in blue, while the graphs show entropy on the top and then boundary energy over time. Notice how our method takes intelligent actions like this fold here in order to decrease the entropy while keeping the boundary energy at a pretty safe level. And the estimated shape that we finally get at the end of active sensing actually matches the partial ground truth fairly well. So our approach also supports topological changes in the boundary conditions, such as cutting, which is very prevalent in surgery. We incorporate priors on that topological change into our Kalman filter's motion model, as we show here. And in this experiment, we're basically kind of iteratively estimating and then cutting away those attachments in order to finally free this tissue from the environment. So as a summary here, we presented Jiggle. Our approach leveraged differentiability of PBD simulators with an extended Kalman filter in order to estimate boundary parameters, which we used to generate an optimization-based entropy minimizing active sensing strategy. Thank you.
Thank you, Nico. We have some time for some questions.
Hello? Oh, yeah. Hey, awesome work. So one thing I was noticing, actually, was when you're doing the folds, you typically have just one point of contact. Does that active sensing component break that grasp and then go to another area, or do you have to like replan it from a different point?
That's actually the next line of work that we're planning to extend this to. But right now, it's just one point of contact, and how can you maximize information gain from that one point?
I see.
Yeah.
Thank you.
Okay, we have time for one more question. All right. If we, yeah, please.
What is the pathway here for real-world implementation of this, getting it into the surgery room?
Sure. I think one big kind of challenge here is occlusion when it comes to observability of the tissue. So when things kind of fold over each other, you lose observability, and that gets really challenging. And that also is another big challenge when extending this stuff to a lot of like 3D volumetric structures, and that's something that we're exploring now, combining partial observability with these sort of estimation frameworks, I think, yeah.
All right, let's thank the speaker.
Thank you.
All right, so we have the last speaker of the session, Michelle Zhao. Let's hope it loads. Yeah, perfect.
Awesome, thank you. Hi, I'm Michelle. I'll be presenting our work on conformalized teleoperation, confidently mapping human inputs to high-dimensional robot actions. This was work done in collaboration with Reed Simmons, Henny Mani, and Andrea Baichi. So robot teleoperation can be challenging because users need to map low-dimensional inputs to high-dimensional robot actions. And when constrained by input interfaces like 2DOF joysticks, this can require frequent mode switching. And prior work uses neural networks to learn low to high DOF mappings, enabling more intuitive teleoperation. Specifically, these controllers take as input the robot state, plus a low DOF human input, such as a joystick command, and map onto the robot's action space, such as high DOF joint velocities. Now, let's consider another scenario with this learned shared controller in action. The task is goal reaching with one of two goals, and the controller is trained on demonstrations reaching both objects. A new and very novice user comes in and intends to control the robot towards reaching the blue object. To do so, she provides inputs to the controller via a 2DOF interface. Now, let's take a closer look at what happens when she tries to control the robot to reach the blue goal. As the user gives input, the controller predicts the user's intended high DOF action, but unfortunately, her inputs fail to elicit the desired high DOF actions, and the robot twists away from the intended goal. Now, the reason for this failure is quite complex. For example, human inputs could be out of distribution, or perhaps the neural network cannot handle this multimodality effectively. Even if we may not know why the learned controller is failing, we need a method to detect when it fails. And this highlights a key question. How can we ensure that we trust the learned assistive mapping? Our key idea is to use conformal prediction to calibrate the learned controller based on how well the model is working for a particular user. Specifically, we leverage adaptive conformal quantile regression. This statistical method provides asymptotic coverage guarantees without distributional assumptions. The key ingredients for conformalized teleoperation are 1, adapting the assistive controller to estimate its own uncertainty via the additional output of upper and lower quantiles. 2, collecting a held-out calibration dataset of low-D inputs and ground truth intended high DOF action labels across all time steps in a user teleoperated trajectory. In other words, the calibration dataset is a small set of correct input-output pairs provided by a target user. And 3, a nonconformity score, which measures how erroneous the initial quantile intervals are. And with this, we can automatically adjust the uncertainty intervals, enabling us to guarantee that the desired high D output of the controller will be within the calibrated uncertainty bounds with high probability over time. So now, as the model sees target user data, the interval size adapts to cover the ground truth high DOF actions the user intended. And with prediction intervals that guarantee coverage, we can look to the size of the adjusted intervals as now a user-calibrated measure of uncertainty. In our experiments, we examine how different sources of uncertainty affect the confidence assessment of our controller. The 3 sources of uncertainty we investigate are uncertainty from multimodality in the training distribution, low control precision in training, and diverse user strategies for providing low D inputs to the controller at calibration time. And for the purpose of this talk, we'll highlight how our controller handles uncertainty in the context of diverse user input strategies. So H star is the input scheme seen in the training distribution. As the user input schemes deviate from the training scheme, large uncertainty intervals enable us to detect this misalignment. Compared to an uncalibrated assistive controller, we can also ensure consistently higher coverage on the calibration data across these different input strategies. And overall, this allows us to meet our key challenge of assessing how much we can trust and how confidently the teleoperation controller is able to work for different users. Please see our paper for more details on our experiments and come talk to us at our poster session. Thank you.
Thank you, Michelle. We have time for a couple of questions. Over there.
Thanks for your talk. My question is that the basic assumption of conformal prediction is IID assumption, but for the dataset of sequential control, this assumption does not hold. So how do you solve this problem?
Yeah, so adaptive conformal inference is a method proposed by Gibbs and Candace, which basically eliminates that assumption. Like, if you don't have IID data, you can basically treat the conformal prediction problem as an online gradient descent problem, and then it enables, so the cost of that is you get asymptotic coverage instead of coverage over like a static data set.
Okay, thank you.
Yeah.
We have one more question over here, down here.
Sorry, I'm going to hijack this. Very interesting talk. So interesting idea. I'm kind of wondering what, once you discover that there's some kind of anomaly, what do you intend to do with it? How do you intend to correct the robot's action?
Yeah, I think the two courses of action are training a bespoke model for a particular user, or training the user in better at being able to use the controller.
Okay, we have a final question over here. Oh, yeah.
Yes, thanks. So I wonder, how can you map two DOF input to a, like, say, 6-dimensional freedom output? So maybe, for example, you want to reach something up or reach something down. How can you control that with only 2 inputs?
Yeah, so the training of the kind of base model relies on like a fixed set of tasks that you'll kind of be performing, and so like generally you wouldn't be able to do kind of like motion in 3D with only 2D inputs, but if you're kind of only doing the same trajectories or the same set of trajectories over and over, you can learn essentially a 2D latent space that can handle that because it's conditioned on the robot state as well.
All right, thank you, Michelle.
Thank you.
So with this presentation, we'll wrap up the session. If you have more questions, you can reach the speakers at the coffee break. So let's all enjoy now some coffee and some good discussions. And let's thank again the speakers for the last time. Thank you.
Hello, everyone. Good morning. Welcome to the planning session. My name is Yana Tumura, and together with my colleague Lin Zhao, we will be chairing this session. It's 10:01, so let's get started. I would like to ask the speaker of the first paper to get on stage. Come up and take it away.
This video.
Can we get the slide started?
Hello everyone, I'm Xinzhu Liu. Today I will talk about leveraging large language model for heterogeneous ad hoc teamwork collaboration. Nowadays, multi-robot collaboration is applied in many fields, but most existing studies cannot directly solve the ad hoc teamwork problem. Research on ad hoc teamwork most focus on 2D simple things and cannot apply to 3D visual environment in robotics. In this paper, we study a more general and challenging ad hoc teamwork problem, in which a heterogeneous ad hoc agent joins any team at any time from any location. In the ad hoc teamwork task in our paper, an original heterogeneous team is randomly selected from candidate teams. They collaborate with each other to execute the specific tasks. After a period of time, an ad hoc agent joins the team at any location, and all agents need to reply actions. Finally, the ad hoc agent collaborates with the team to complete the task. This task matches the original intention of the ad hoc teamwork and focuses on a more general and challenging setting. The proposed ad hoc framework consists of visual semantic perception, dynamic subtask planner, dynamic subscale planner, subscale execution, state assessment, and communication module. The subtask planner and the subscale planner forms a theoretical planner based on the large language model, which is effective in action reasoning. In the subtask planner, we propose the interactive reflection of thought, which includes 3 stages. The first stage is to generate multiple candidate subtasks based on capabilities and states of all agents. The second stage is to evaluate the generated subtasks based on the current states and rank them from good to bad. The third stage is to reflect if each selected subtask is feasible to execute based on newly obtained communication message in sequence. Then the selected reasonable subtask is input to the dynamic subscale planner to generate the subscale that can be executed by the low-level controller. Next, we will show some experimental results. We evaluate the proposed model in the tidying up task, in which heterogeneous agents need to find all misplaced objects and replace them to reasonable locations. We have built a benchmark to evaluate in the simulation environment. We first show the collaboration process of the IROT-based ad hoc agent with teammates. At the 5th step, the ad hoc agent joins the team. When the ad hoc agent plans the subtask, it first generates 3 candidate subtasks and then ranks them from good to bad. Then it selects the subtask in sequence and broadcasts its intention to teammates. It rejects the subtask with communication message from teammates. Finally, it helps the team complete the task. We then compare the IROT-based ad hoc agent with other ad hoc strategy. After the ad hoc agent joins the team, it collaborates with the original team. The ad hoc agent with the proposed IROT method completes the same task earlier than other methods, which demonstrates the effectiveness of our proposed framework. Then we also apply the proposed model to the real-world scenario. In the physical validation, we use 3 heterogeneous robots in the experiments. We show the collaboration process in which the small robot without the manipulation ability is regarded as an ad hoc agent. The small robot joins the team at 60 seconds. It detects misplaced full bottle and broadcasts its information to teammates to help improve the efficiency. The subtask planner can have multiple rounds of reasoning during the interactive reflection stage. We then show the comparison result, whether the small robot joins or not joins the team as ad hoc agent. In the ad hoc team, the corrupted robot decides to replace the full bottle based on the detection information of the ad hoc agent. It is a key to improve the efficiency. Then we use the final video to demonstrate that the proposed ad hoc framework can solve the ad hoc teamwork task in the case that the original team cannot complete the original task, which demonstrates the general ability of our framework. That's all. Thank you.
Do we have questions?
As a prompting method, what's the difference between your IROT method and the ordinary chain of thought COT method?
We propose the IROT method, which consists of 3 stages. The first stage is to generate the candidate subtask to execute, and the second stage is to evaluate the generated subtasks. And the third stage is to use the newly obtained communication message to rejudge whether the selected subtask is reasonable. And each task is implemented by the traditional method of chain of thought.
We have time for 1 or 2 more questions, if there are any. In that case, I'm going to ask, have you ever seen that a subtask would not be executed well, or could you comment a little bit on the limitations of the method?
Yes, we propose a method to ensure the reasonable of the reason subtask. We have 3 stages to ensure we can generate the right subtask. But if we generate some wrong subtasks, we have the state assessment module to re-evaluate this process and re-plan the whole subtask plan, so we can self-reflect this problem.
Great. Thank you very much. Let's thank the speaker.
Thank you.
The second paper in this session is Interactive Predicate Learning from Language Feedback for Generalizable Task Planning, and unfortunately none of the authors could be here, but they sent a wonderful substitute, so let's welcome her.
So we introduce Interpret, an interactive framework that learns symbolic predicates from language feedback for generalizable task planning. So I'm Jia Huifu, and I'm here presenting for all of the authors Mu Zhihan, Yifeng Zhu, Song Chunzhu, Yingnian Wu, and Yu Zhu. This work is a joint effort by UCLA and UT Austin. So many household tasks, such as cooking pasta, require robots to plan a long sequence of actions, and this problem is known as task planning. Traditionally, task planning relies on a symbolic planning domain defined in PDDL, Planning Domain Definition Language. A PDDL domain consists of predicates that define important symbolic relations, and also operators that describe action preconditions and effects. Notably, each predicate is associated with a binary-valued predicate function that classifies whether the relation holds or not, given raw observations. While PDDL-based planning is effective, it's usually non-trivial to handcraft predicates and operators, even for human experts. Then how can robots learn predicates for planning? Human infants can quickly learn spatial concepts from caregivers' language feedback during physical play. Inspired by this, we propose to learn predicates from language feedback during embodied interaction. As a robot interacts with the environment with primitive actions, we have a non-expert human given language feedback that provide information on task goals and action feasibility. Interpret learns predicates and operators on the fly, which are then used by a PDDL planner to generate plans for further interaction. The pipeline of Interpret starts up from leveraging GPT-4, a pre-trained large language model to process language feedback. We identify the predicates to learn, extract predicate labels, and reason action preconditions. Then for each identified predicate, we generate its predicate function in Python using the prior knowledge of GPT-4 by composing low-level perception APIs with logical structures and arithmetic operations. We assume a non-set of perception APIs that provide basic visual understanding abilities, such as object detection, segmentation. Then such predicate functions can directly parse raw observations into the symbolic state. We further interactively correct the predicate functions with GPT-4 to align their predictions to the extracted predicate labels. This mechanism allows closed-loop predicate learning from language feedback. Then with the learned predicates, we also learn operators from interaction data using a cluster-then-search algorithm. To evaluate Interpret, we design a suite of simulated and real-world robot manipulation domains that feature different task semantics and constraints. In particular, we want to evaluate how well the learned predicates and operators can generalize to unseen tasks with first, that there's more objects, and second, novel goals, and ultimately a combination of both. In simulated domains, we compare interpret with two LLM-based baselines, inner monologue and code as policies. Interpret shows remarkable generalization ability. On the most challenging test set, it achieves 73% success rate and outperforms all baselines by a large margin. In real-world domains, interpret solves 40% of the most complex tasks on average, while the baseline fails completely. The learned predicates and operators enable interpret to solve challenging tasks such as stacking multiple objects on a receptacle and preparing for a breakfast table. And here are the two videos. So that concludes our presentation. If you want to learn more about the work, please refer to the project page through the QR code here, and you feel free to drop the authors an email if you have any questions. Thank you so much for your attention.
Thank you for the presentation. Since we don't have the authors here, feel encouraged to send the questions to them via email. And we are welcoming the next speaker, who is John Michaud, and we'll be talking on safe planning for architecture-related robots using reachability-based obstacle avoidance with spheres. John.
Thank you. Okay. Hi, my name is John, and today I'll tell you about our work that develops a novel safety representation for real-time trajectory planning. Okay, so the goal of our paper is to generate safe motion plans that can move the arm from some initial configuration to a desired configuration. And here our definition of safety means that we want the robot to avoid collisions while also satisfying its actuation limits. And so here we'll assume that the robot has access to a high-level planner and that this planner can generate a discrete path towards the goal. And so our main question is, how should the robot both represent and enforce safety while it's planning trajectories between consecutive waypoints? And so there are a number of ways to represent safety, but broadly speaking, they fall into two different categories. The first category includes discrete time representations. And here, these representations only enforce safety at particular time points. But it can be challenging to use these representations in real time if you need to check safety frequently. In contrast, there are continuous time representations which over-approximate all possible motions of the robot over some finite time horizon. But most of these methods tend to be overly conservative or they're difficult to compute in real time. So we address these challenges in an algorithm that we call Sparrows. And Sparrows over-approximates the motion of the robot using a collection of spheres. It represents all of the obstacles in the environment using an exact sign distance function. And then we combine these two representations into a novel obstacle avoidance constraint that we use for real-time trajectory planning. So we do have a few assumptions. The first assumption is that the volume occupied by each joint can be over-approximated by a sphere. We also assume that the volume occupied by each link can be over-approximated by the convex hull of two consecutive spheres. And then for simplicity, we're assuming that each obstacle is an axis-aligned cube. So the key idea behind Sparrows is that if we combine interval arithmetic with the forward kinematics algorithm, then we can over-approximate the swept volume of the robot. And so here's how this works. We start by over-approximating the joint angle trajectories. We then use forward kinematics to over-approximate the position of the joint frames using spheres. We then add those joint position spheres to the nominal joint volume spheres. And then finally, we over-approximate the swept volume of each link using another collection of spheres. And so once we have this safety representation, we can then use it to build our obstacle avoidance constraints. And so our insight here was that if we can enumerate all of the vertices of each obstacle, then we can represent the collection of obstacles as an exact sign distance function. And in fact, we can prove that when we use these representations, we can guarantee that collisions won't occur during planning. So here's an example where we're comparing sparrows to a number of state-of-the-art methods. And what you'll notice is that QRobo, TrajOp, and MPOT, they'll all experience collisions before the robot can reach the goal. And if you look at RMTD and compare it to sparrows, you'll notice that RMTD's safety set is much larger. And so it actually gets stuck before it reaches the goal. And it's only sparrows that can reach the goal for this particular example. So we actually compared sparrows to these baselines while varying the number of obstacles. You can see sparrows significantly outperforms the other methods while avoiding collisions. And then finally, we compared sparrows. We evaluated the performance of sparrows on scenes where the obstacle placement resembles what the robot might expect in a more realistic scenario. And what you can see here is that sparrows successfully reached the goal. And when we compared across a number of trials, sparrows outperforms the other methods. Okay, so that concludes my talk. Please feel free to check out the website, the paper. You can play with the code if you download from GitHub, and I'd be happy to take any questions.
Can you hear me? Yes. Hi, great talk. You mentioned that Sparrows requires that we model our environment as a set of prismatic volumes. Is it possible to extend this work for a more complex environment geometry, or is that a fundamental limitation of the Sparrows method?
Yeah, so the question is, can we use a more general scene representation with sparrows? And the answer is yes. So it should be relatively easy to, use a set of point clouds. One representation I was really excited about when I first started working with sparrows was sign distance fields. But actually, in a few weeks, we'll have a paper posted on an archive where we use sparrows with Gaussian splats for obstacle avoidance.
Hello. So my question is also self-collision handled by spheres? Because I guess different links would have different sets of spheres, and definitely at least one sphere between each link would be overlapping. Is this manually handled, or?
Yeah, so the question is, how are we handling self-collisions? So I guess I have maybe 2 or 3 answers to that. In the videos that I showed, we're not considering self-collisions. If you look at the project page, we should have some videos where we're planning with multiple arms. And I believe we are we're enforcing self-collision constraints using the spheres. It does get a little bit unwieldy the more spheres you have. And so right now, we're actually working on a different representation to handle self-intersections. So essentially what we figured out is that we can write down the sign distance between 2 tapered capsules, and then grind through a bunch of math and sort of compute that analytically and its gradient.
Thank you.
One more question here in the front.
So there's a very long tradition of using spherical approximations for robots for collision checking for optimization, right? I think Chomp was doing that with SDF. What were you using for representations for the comparison points? And what are you doing different in the optimization here, given this representation choice?
Okay, so the question is, how is our spherical representation different from representations that have been used in the past? Right. So the representations that have been used in previous methods were discrete time representations. So they might over-approximate the robot with a collection of spheres, but they're only checking safety at discrete time points. Our representation actually enforces safety over time intervals. So we're actually over-approximating the entire swept volume of the robot. how much, like what's our success rate? Is that what you said? Oh, sure. Our success rate is, so at least in the examples that I showed, I think the best we were able to do was 87%. We do consider a task to be a failure if we have two planning iterations where we can't find a solution. So it is true, we're solving a nonlinear optimization, we can't necessarily find a solution, but that doesn't seem to happen very often for us.
Thank you very much. We will need to leave the rest for the poster session. So let's thank the speaker again. And the next paper is Motion Planning in Foliated Manifolds Using Repetition Roadmap. And our presenter is Jiaming Hu.
Hi, I'm sorry, Jiaming is unable to make his trip due to visa issues, so I'm going to present on behalf of the team. And my name is Jiawei Wang. I'm coming from University of California, San Diego. And here is our work, motion planning in foliated manifolds using repetition roadmap. So most manipulation tasks consist of multiple subtasks. A common strategy to solve them involves using a set of manifolds to represent each of them. By navigating a strategy across them so we can solve the problem. And this is called multimodal motion planning. A lower right image shows an example of motion planning where the manifold structure is called sequential manifolds. However, simply using a manifold to represent one single subtask is too naive. For instance, opening a door by grasping its handle offers the robot multiple grasping options, each leading to different manifolds with different constraints for the robot arm, where sequential manifolds will be hard to represent it. Yeah. Therefore, foliation should be used here. Basically, foliation is a set of parallel manifolds sharing specific constraints, where each manifold is defined by a coparameter. Here is one example. If the constraint requires the end effector to move in a horizontal line, the coparameter could be the position of this line. If we visualize the manifold defined by different line positions in the joint space, then we can say a key property of foliation is that two manifolds will be similar to each other, and if their coparameters are closely together. So, after converting the task into foliated manifolds, we can then navigate across these manifolds. However, as the number of possible coparameters increases, the number of manifolds increases and the complexity of the problem will grow exponentially. This is particularly challenging in cases where the solution strategy exists in only a few manifolds. So as a result, searching for the solution within a large number of manifolds in hard tasks becomes extremely difficult. Therefore, in this study, we propose to use a repetition roadmap to improve the efficiency of the sampling-based motion planner in navigating foliated manifolds. The core idea is to leverage the planning experience from previous explorations to guide the planner in later queries. So first, let me briefly introduce the repetition roadmap, which is an abstract roadmap that utilizes probability distributions to model specific spaces and convert the space into graph structure. So therefore, during planning, the roadmap can return a set of distribution to guide the motion planner by solving the graph. So similarly, instead of building roadmap for a single manifold, we construct a large roadmap to model foliated manifolds. So we did this by construct a repetition roadmap for self-collision free space and duplicate it for each manifold, then convert them by intersections between manifolds. So therefore, given a task, we can search for a node sequence from the roadmap to guide the motion planner in foliated manifolds. So after exploring a manifold, both successful and unsuccessful planning experience are used to update the roadmap weights in similar manifolds. So therefore, in following queries, the motion planner can avoid explore efficient regions in different manifolds. However, many constraints can only be represented as zero-value manifolds. So relying on only probability distributions to guide the motion planner may not always be efficient. Therefore, we incorporate the idea of outness, which can provide more precise mathematical representation for managing thin manifolds. After exploring one manifold, we can compute the outness and use them to guide the motion planner in similar manifolds instead of using only distributions. So here is an example to slide a curve in a maze, allowing regrasping. So in this scenario, there are two foliations, one for sliding and another one for the placement of each object, and they both serve as coparameter. The manifold structure corresponding to these foliations is shown in the upper left corner. Compared to previous approaches, our algorithm demonstrates a higher success rate, as it is shown in a table. So here are more examples in the simulation. Great, thanks so much. Please see me at the poster if you are interested in our work.
Do you have questions?
Thank you for the very interesting talk. So how do you know in which manifold you are when you're doing some sampling?
I'm sorry, so the question is, how do I know which manifold I need to construct? Is that the question? Yes. So the manifold here means, the manifold here is defined by the coparameters. So, for example, in our task, it's a manipulation task. And the coparameter is defined by the graph poses and the placement of the object. Yeah. So here, each graph poses consists of a manifold. And all of the graph poses consist of the foliation. Yeah, I hope that answers the question.
One final question.
Thank you. Hello? Can you hear me? Okay,
Yeah,
there we
sure.
go. Okay. You're speaking of coparameters and foliations, but it looks like your examples have a discrete set of manifolds. Does your work apply to continuous manifolds, such as those used in manipulation planning?
Not yet. So in our work, the connection between the manifold, in different foliations, are connected by sampling. So it's like a discrete approach. So we don't have a continuous approach yet. Yeah.
There are some existing approaches that simultaneously explore the space of manifolds, building a discretization of the manifold set, as well as motions upon those manifolds. So perhaps you can take a look at those.
Yeah, sure. Yeah, we can take a look at those. So, is that the question?
Just a suggestion.
Yeah, sure, no problem. Yeah, we'll definitely take a look at that.
Thanks to the speaker. We will
Great, thank you.
continue with the next one, language augmented symbolic planner for open world task planning.
Hello everyone, I'm Guanqi and I'm presenting our work, Language Augmented Symbolic Planner for Open World Task Planning. The target of task planning is to determine the sequence of action that a robot should perform to reach a specified goal. For instance, to finish the task of heating milk in the scenario shown here, the robot needs to execute a long sequence of actions. For this case, language-driven planning methods such as enomologers and probe prompts that use a large language model to generate plans often fall short. Some actions in their generated plans are logically incorrect. In contrast, classical methods using symbolic planner can find value solutions for such cases. However, using symbolic planners requires human engineers to provide complete domain and problem knowledge, including lots of definitions and rules. For example, in PDDL, a planning task consists of 5 components: objects, properties, initial state, goal, and actions. due to human oversight or other factor, the knowledge required for the planning may be incomplete. So what happens in an open world setting where the planning knowledge is incomplete? For example, the action pour liquid lacks a precondition that the target object should be able to contain the liquid. The milk could be poured into the sandwich and spilled onto the table. And missing objects like a microwave safe cup can prevent the planner from finding a solution. So our work aims to leverage common sense knowledge in large language model to solve those problems. And in our open world setting, the action precondition, properties, and objects can be incomplete. Here is an overview of our proposed language augmented symbolic planner, LABS for short. Initially, the planner generates a plan for the planning problem. Then the agent executes the actions in the plan. In case of an execution error, our methods invoke the large language model to supplement domain's knowledge to the planner based on the description of the error observation. Similar to a human, the large language model first generates all possible calls and then verify them one by one to see if the new action precondition derived from the cause can prevent the error. And if the planner is unable to fire a plan afterwards, the large language model can augment the planner's task-specified knowledge with necessary objects to assist the planner in finding a solution. Here we designed 4 tasks in the kitchen domain for evaluation. For each task, we construct at least a pair of incomplete PDDL domain and problem finals to test our methods, and results shows that our methods reach the best performance. And we compare our methods with COPE, which also combines the large language model and the symbolic planner for open world task planning. And COPE requires the provided cause of error to reach performance similar to our methods. But given the textual observation used by our methods, COPE doesn't perform as well. With the help of GPT-4V, we applied our methods to the real-world scenario. Here you can see a demo that our methods successfully completes the task of rearranging the table talk with incomplete domain knowledge. This work is just a preliminary attempt and has a few limitations, such as only updating the knowledge after the error occurred, and we are working on addressing those limitations. To sum up, we propose a novel framework that integrates large language model to enable symbolic planner to operate in an open world environment. That's all. Thank you for your time.
Any questions? There in the middle. In the middle. One in the shirt, sitting in the middle. Back seat, back row.
Thank you very much for your presentation. Is it working? I have a question regarding the reliability of the LLM. Do you have observations of how reliable the outcomes were to use?
Actually, we use the large language model to generate all possible calls. So for one error, the large language model may generalize some like 5 or 6 calls. Then, based on all the calls, we will try all the possible calls and then find a new action precondition and add it to the original PDDL finals and to see whether the new PDDL finals can be used to find a value solution. So it contains a loop, so it will be more reliable to just based on one possible cause.
Thank you.
All right. Okay. Go ahead.
So I presume the ability of the LLM down here to come up with, to augment the domain knowledge successfully depends on how good the error observation was, right? So it depends on the perception of how you failed.
Yeah.
Which again you describe by language, I presume, to the LLM.
Yeah, first for the error observation, in the real world, we will use the GPT-4V to generalize the scenes description. And in our experiments, we just predefine some error observation and use the large language model to rewrite those predefined textual observation, then to get a diverse input for our methods.
So now you have a limited set of errors that you can deal with.
So can you repeat your question?
So the types of failures that you can deal with right now is predefined and limited.
Yeah, currently.
Right. Due to time limitation, we will leave other questions to the poster session. The next is the collision unfolding point trees.
Hello, I'm Clayton Ramsey, and I'm here to present our recent work on accelerating motion planning against point clouds using accelerated nearest neighbors for collision checking. I'll skip straight to the good part. Our work enables robots to plan in real time using sampling-based motion planning from start to goal against dynamic, unmodeled obstacles in a perceived environment where the ground truth geometry is not known. This even works in cluttered, cramped environments where there's very little room for the robot to maneuver. And the way that this works is, in our demonstration, we had a camera on the ceiling recording point clouds at 60 frames per second. Every time we got a new point cloud, we would rebuild our scene representation and then run a sampling-based motion planner from scratch every single frame to connect to the start and goal state. The key contribution that enables this approach is our accelerations in collision checking speed. By having nanosecond scale collision checking speeds, we get millisecond scale planning times, which means that we can run the sampling-based motion planner fast enough to keep up with the point clouds being streamed in from our camera. Some recent work from our lab massively accelerated collision checking using SIMD, single instruction multiple data parallelism found on every single CPU. But the problem with this approach was that it only worked with explicitly modeled primitive geometry that was entirely known to us at construction time. So when we're dealing with dynamic environments, we need to change our approach. There are lots of ways of representing your perceived environment for the sake of collision checking, but none of them really meet our needs for this real-time approach, which requires parallelism in our checking algorithms, nanosecond scale collision checking speed, but also using ordinary CPU hardware without GPU acceleration or dedicated ASICs. So we're proposing a new data structure, which enables us to represent point clouds and collision check them very fast. To start off, let's make a conservative approximation and model our robot as a set of spheres. Then, collision checking between the spheres in our point cloud is just a nearest neighbor search, where we find our nearest neighbor for each sphere, and then check if that nearest neighbor is in collision. That tells us if the cloud is in collision. If we're doing nearest neighbor search, one of the first data structures we might reach for is a KD tree, which partitions a space into a set of prismatic cells, each containing one point, and then assembles these cells into a larger tree. The problem with the KD tree is that its search algorithm is branchy and has a backtracking step, which is hard for branch predictors and difficult to parallelize. So our proposed data structure, the collision affording point tree, amends this. Let's start by looking at one cell of the KD tree, highlighted here in blue. If we know that the maximum size of our sphere on a robot has radius r max, then a sphere centered in our blue cell could only ever collide with points P1, P2, and P3, because they're the only points within a range of r max of the cell. Let's call those 3 points, 1, 2, and 3, afforded by the cell. And then, at construction time of the tree, we'll mark those afforded points with the cell of the tree. So then, we only have to do a search through one subtree of our search tree to find all the possible candidates for collision for each sphere. So instead of searching many subtrees, we search only one, which gives us a massive improvement in performance. In our benchmarks, we compared against many different methods, 2 of which are shown here. An octomap in blue, a voxel-based method, and a traditional KD tree in orange. We can find that our collision check time is orders of magnitude faster than both. In green, our sequential implementation, in red, our parallel implementation. This massive speed up translates to enormous improvements in our motion planning times. In the right column, we have our end-to-end planning times from perception all the way to action beginning. And we find that using our data structure for collision checking, we get planning times under 10 milliseconds for the UR5 and Panda robots. This means that we can run motion planning in the loop, where we can respond in real time every 16 milliseconds as a 60 hertz camera streams in a new point cloud. To summarize, our data structure, the CAPT, massively accelerates collision checking, which enables real-time robot motion planning. We have an open source release available at the QR code there. And with that, thank you very much for listening, and I'm happy to take your questions.
We will have time for 2 questions. That first.
Thanks for the really cool talk. I'm curious, just on the motion planning side, I realize the contribution is in collision checking.
Yes.
But can you talk a little bit about how you're either reusing the RRT or like what the goals are, really what the computation is on that side? Like where, how does the RRT, besides just computation time, take advantage of this? Or like what are you actually computing?
So in this case, we're actually not doing much that's special in the way of our planning. We're using a dynamic domain balanced RRT Connect if you care about the details. So speaking broadly, all we're doing is just doing motion planning from start to goal, assuming that the perceived point cloud is static, and we're just sampling fast enough that as the point cloud changes, we're able to change our trajectory online.
Hello. Thanks for the nice talk. I've got 2 questions. The first one is, there are a lot of GPU-accelerated collision checkers, and so why do you insist on using a CPU-based approach for your collision checking? And the second question is, does this work with partial point clouds?
So the first question is, why are we using CPU collision checking instead of a GPU? So there are a few reasons for that. One of the first ones is power consumption. So we find that GPUs are often very power hungry, and our goal is to try to develop methods that are applicable to edge hardware that has low parallel or low dedicated GPU hardware. And the other reason is we want to ensure that we can develop a method that's applicable to very wide arrays of hardware. So instead of having to target a single GPU or work with compatibility across CUDA versus AMD and all that, we're just targeting general CPUs with SIMD, which is much better supported. And then the second question was, how do we handle partial point clouds? In this case, our data representation is only as good as our perception. We're not intentionally modeling uncertainty in this case, although we are very interested in extending our work to discuss uncertainty and misperception in the future.
Thanks.
Right. Thanks to the speakers again. We'll move to the next presentation.
Okay. Good morning, everyone. I'm Jim from the Chinese University of Hong Kong, and I'm happy here to share our work on home topic passage planning for robot manipulation and navigation. So in robotics, simultaneous generating multiple pulses with certain topological properties found vast applications. Pulses are planned for deformed object manipulation and swim navigation in complex environments. So this work unleashes pulses potential by efficiently planning pipeline. We consider home topic passes where any two passes are not blocked by obstacles. To find short paths both wide and have large free space alongside, we present a new passage detection condition and the passenger-aware optimal path planning. Then passage can be generated very, very efficiently. So in passage detection, so unlike CNIS or Voronoi diagrams to measure free space, passage transversal information is lightweight and compatible with sampling-based planners. But combinatorial passage detection is only reductant and explicit criterion like short passage awareness is problem dependent. So we hope to find some intrinsic properties. So the visibility condition leaves many reductant passengers. So let's see from the robot's perspective. So assume the robot is at the passenger center and we'll see how it's constrained. So if it's closer to any other obstacles, then the current passenger should be invalid. So we call this condition the extended visibility condition. So the routing passengers after the pure and the extended visibility check are depicted by the dashed and the solid lines respectively. So we can see that a dramatic passenger number is achieved by the extended visibility condition. And the sparse and informative passenger distribution can be obtained. This statistic results show that the passenger number is nearly linear with respect to the, in two conditions. And in the 3D space, sparse passenger condition can also be obtained in different height intervals formed by obstacles. So intuitively, they're like virtual gates in this space. So with sparse passengers, passenger-aware optical path planning finds the path with optimal passenger traversal for the path set. So such a path should be short and have large free space alongside. So here path 1 is shortest, but path 2 is short and it passes wide passengers, so it's better for swim motion. So we design a compound cost function containing the minimum passenger width as a weighted term. So this cost is compatible with sampling-based optimal planners to update sample cost. So it encourages passes to be short and at the same time to avoid larger passengers as a result giving in different weighted costs. So finally, to get the entire passage, we only need to plan one pass because all the passes will pass the same passengers. And then we can just traverse the planned pass to other agents, of course, with some pass deformations. Yeah. So here are some results in obstacle-dense environment. So we first plan a single pass using passenger-aware optimal path planning based on RT star, and then we perform locally adjusted the planned path, and then it's transferred to other agents. The passes in the chalk pro is obtained by separately planning each pass and imposing the home topic constraint explicitly. The bottom row is generated by our pipeline, which better accommodates home topic passes in confined space. For efficiency evaluation, sparse passenger help to save over half the planning time, and it can guarantee the path optimality in general. And for passage generation, our framework shows significant advantages since it's not sensitive to the passenger number. It's also very adjustable for the path coordination. In application, we show the key point passage planning for deformed object manipulation and for swim navigation in city environments. So they can find wide and short passes. So in summary, there are three takeaways we want to share. The first is the sparse passenger detection. The second is the passenger-aware optimal path planning algorithms and the whole pipeline. So in the future, we plan to address dynamic environments and the interior constraints among passes, and of course extend to multiple home topic passes. So that's for my talk. We'll come to our post section for any further discussion. Thank you.
Any question? We're gonna have one question. fall behind the schedule a little bit. All right, if there is no question, our last speaker is Nishant Kumar.
Hello. Okay, so it's a very exciting time to be in robotics. We're seeing pretty rapid progress in skill acquisition via learning-based approaches and also via more traditional controls and motion planning approaches. We've also seen progress on using various planning approaches to sequence skills together to solve long horizon tasks directly from perception, such as in the sweeping task shown in this video. However, these skills and planning more generally fail when we try to deploy them in novel scenarios. Consider this example where we try to deploy the previously shown sweeping skill with a new table and objects. The skill uses too much force in the scene, causing it to fail. In this work, we ask the question, can we learn to overcome such deployment failures through deliberate practice? We assume that all our skills are parameterized by some continuous vector theta that determines skill behavior. So for instance, a grasping skill could consume x and y and an angle to influence how it grasps this wall-mounted hammer. Similarly, a placement skill might consume x and y at which to drop an object a set height above another object. We imagine this setting where such skills are designed in a robot factory. Each robot from the factory is equipped with these skills, as well as some parameter prior distribution by the factory, and then sent to a different deployment site. In a particular deployment, the robot is given tasks to perform by a user, but also given some practice time during which it is free to explore to improve its ability to solve future tasks. Our concrete goal is to learn parameter policies autonomously during practice time to better solve tasks encountered during deployment. Towards this, the key question is what skills should the robot practice during its practice time? Towards answering this question, we leverage the notion of skill competence, which is simply the probability that a skill will succeed from any state it might be executed from. And this can be empirically estimated by observation. Competence is useful as a concept because we can use symbolic planning to provide us with maximum likelihood task plans based on competence for any task. Our approach, estimate, extrapolate, situate, answers our key questions, saying that we should practice the skill whose improvement would lead to the greatest expected improvement in success rate on the overall task distribution. We do this by first estimating the competence of every skill that we have, extrapolating it, assuming we would get one more data point from practice, and then situating this skill in the task distribution via planning on previously observed tasks. So for a concrete and fun example, consider this task in which the robot is asked to put a ball on the table. Unfortunately for our robot here, the simplest possible plan is not going to work because the table is slanted. During the robot's practice time, it initially decides to practice putting the ball onto the table directly, hoping that it will improve at this skill, and this will lead to task success in the future. This is because the maximum likelihood task plan based on observed competences is only 4 steps. As the robot practices, however, it observes more failures for placing the ball on the table. This decrease in competence of this skill causes there to be a new maximum likelihood task plan involving the ring that has been conveniently left in the room. The robot decides to try placing the ring onto the table and is able to observe a success. We allow the robot to autonomously practice in this fashion for 3 hours with absolutely no manual intervention by a human. Notice that during this practice time, the robot is predominantly figuring out where to place the ring on the table such that the ring will rest stably. This is what we would expect since this is the skill that the robot is least competent at, but that is most important for task success. After practice, the robot has learned to solve the task by using the ring. And owing to its perception and planning capabilities, it is even robust to adversarial intervention by an unfriendly gremlin. Our approach can be applied in an even more challenging environment in which the robot must learn how to correctly sweep some toys from a table into a bin. Once again, the robot is able to be robust even after learning, even despite adversarial intervention. Thank you, and I'm happy to take any questions. If you're particularly excited about this work, please contact Tom Silver, who is starting a lab at Princeton next year.
All right, any questions? Here in the front row.
So I suppose your skills come with post conditions, right? And you must be able to detect that. Are these also somehow parameterized? Because the post condition may be different depending on the environment you're deploying.
Yes, great question. So we're actually using like a PDDL-based planning representation where the skills, the post conditions and preconditions are all defined in terms of predicates, and these are parameterized by object. So, you can define like on top A and B, and that is parameterized by any object A and B.
Yeah. So the notion of on that table that was tilted, right? It's a little bit different than what it came from the factory.
Yeah, that's right. So the assumption here is that all these conditions are like, maybe come from perception and are like general, they will work in any environment. But yes, we, specifically set, like in this example, we, had some very specific bounds for that table.
Right, thanks, great work.
Hey, thanks for a nice talk. How do you know, so you have an intended effect, but how do you know when the skill is not learned completely? How do you know that if you've finished executing the skill?
Sorry, how do we know if it's not learned completely?
So while it's learning, it doesn't achieve the intended effect, right? So how do you know when to finish, when the execution has finished?
Okay. So we assume that like a skill is a policy. So we will just, a policy that like returns done basically at some point. And so you can think of it like an option if you're familiar with that. And so basically control will get passed to the skill. The skill will like do things and then it will return control at some point. And in the worst case, if the skill is unable to do anything, we'll just return control after a set amount of time. So like it will basically always terminate in this way. And after the skill has returned control, we're going to run perception to check whether like the expected conditions have been achieved or not. And depending on that, we just classify success or failure.
Okay, thanks.
All right. Yeah, all right. Let's thank the speaker. So with that, we will end this planning session. The next session will be the manipulation. All right. I will hand over this to the chair of the next session.
I think we just give it up there. Hello. Hello, everyone. We're going to start our first session on manipulation for this conference. My name is Tirtha, And I'll be one of the chairs handling the first 4 set of papers. And then I'll hand it over to Ram.
Yep, so let's get started.
All right, so the first paper is optimal non-redundant manipulator surface coverage with rank deficient manipulability constraint. And the speaker is Tongyang.
Okay, hello everyone, I'm Tong Yang. I'm honored to present our manipulator coverage algorithm. First, I want to introduce the manipulator coverage problem. In this task, we assume that the surface is a node. The manipulator is non-redundant, and obstacles are all static and known. Due to the limited reachability of the manipulator, given a configuration, it might only cover a part of the surface. So after that, the end effector has to lift off from the surface, and the manipulator will do reconfiguration. After that, it will the end effector will be landed back to the surface and the coverage continues. So our previous work can optimally determine which part of the surface should be covered by which kind of configurations, such that the number of overall discontinuities is the minimum. And this is okay. This is the image of the next video of the animation. And here's the illustration of the motion of such optimal planning. In this planning, we don't care about how to generate the two motion, either back and forth or spiral. As long as the manipulator can cover each part of the painted region one by one, the motion will only have two discontinuities. And and we noticed that some problems don't use full rank manipulability constraint. So some singularities are valid. That means the manipulator won't hit any obstacles. And the end effector has the mobility in all the required dimensions. So in this paper, we try to generalize the scope by considering valid singularities. In order to do this, we have to first generalize the graph representation. Previously, we used a color to represent a kind of configurations. So by overlapping the paintable region of colors, the graph model will contain a set of regions. However, in this paper, some surface points will have an infinite number of singular configurations, which means that there may be an infinite number of colors, which cannot be modeled by previous algorithms. We proved that we can always locally make some modifications to the graph model. So that the new problem can be formulated by the previous graph structure. So that means the previous solver can be used to solve the new problem. The other difficulty is in discrete scenarios. Previously, singularities and their neighborhooding configurations are purposely removed. So there was a joint space gap. We can easily identify whether two configurations are joint space connected. But in this paper, there is no gap around the singularities. So even if two configurations are very close, they may stay on different sides of singularity. So they should be given different colors. So in this paper, given the discrete surface, we propose a mechanism to identify a minimal region used for singularity visiting. And we use a constraint planner to find the path for singularity transition. Here's the setting of our real-world experiment. We model the problem in MATLAB and calculate everything. We can identify 4 kinds of configurations, and you will see how they are connected by singularity visiting in the video. This is the first segment of motion. You can see as the manipulator is approaching the singularities, the wrist flipping becomes bigger and bigger because it's more and more near the singularity. And you can see from the graph that there is an unfilled hole. And this is the minimal region used for singular transition. In this case, we don't know the exact position of the singularity, but a constraint planner will do this. So if the sphere match resolution can be higher, then the region can be smaller. Finally, this is the second segment of motion. The whole task is finished without any factor discontinuity. Thanks for the listening.
Thanks. Questions?
There's someone right here.
Thank you. Normally, redundancy, having more than 6 degrees of freedom is one way to overcome certain kind of singularities. My question is, your definition for a valid singularity, it is exactly the same when you have redundancy and when you don't have any kind of redundancy?
Actually, this problem is considered, it can be seen as a kind of non-redundant cases, and actually when the manipulator is singular, it lost more degree of freedom. So it is a kind of under-accelerated system. We are consider if the manipulator is less capable, but the task is also lack capable, then whether we can solve the problem.
Okay, thank you.
Any more questions? So if not, I have a question. So can you comment on the quality or the characteristics of the surface that's being polished and the role of that might have in the connectivity?
You mean the quality of mesh reconstruction? Or?
No, the surface under which. So it's a continuous spherical surface, but can you comment on the undulation of the surface or any assumptions that's required on the surface itself?
I don't think there is a requirement for the type of the surface. It can be analytic or discrete. If we use a formula to describe the surface, then we might analytically know where the singularities are. But if we are given a point cloud, then it is impossible. With probability 0, we can find a surface point with singular configurations. Yeah.
Thank you. So next paper is adaptive graph, material adaptive graph-based neurodynamics for robot manipulation.
Thank you. Hi everyone, I'm Kaifeng, and here today we introduce adaptive graph, material adaptive graph-based neurodynamics. Okay, so objects made from different materials exhibit distinct physical behaviors. Even among objects of the same category, differences in physical properties will lead to different dynamics, which will also make the final states largely different. To carry out effective robotic manipulation, we need to distinguish the dynamics of different object instances. In adaptive graph, we learn a graph-based neurodynamics model that can adapt to objects of different physical properties. We first use a graph to represent the object states by sampling particles spatially and connect edges based on proximity. Then, the graph is fed into a message-passing graph neural network, and by training it to predict the future states, the network learns the physics within particles. Our key innovation to this framework is to employ physical property conditioning. For example, for a rope, we can represent stiffness as a continuous variable and use it as an extra vertex input feature. This allows us to train a model on diverse ropes together and result in a more unified dynamics model. Our model can be trained on a variety of materials besides rope, such as rigid blocks, granular objects, and cloth. They are each characterized by different physical property variables, such as the center of pressure, granularity, and stiffness. For unseen instances at test time, we perform online inverse optimization to refine their physical property variables based on the physical behaviors we observe during random interactions. Here, we present an example of a low-stiffness piece of yarn. When predicting its deformation in response to an action, The baseline model and dynamics model without online adaptation fails to predict the correct bending effects, as it can only model the dynamics of an average rope. In another example, for highly stiff polymer ropes, our predictions also correspond more closely to the actual outcomes. Our method can capture the dynamics of various objects that belong to rigid boxes, ropes, granular objects, and cloth. These results highlight the improved dynamics prediction accuracy of our method compared to the no adaptation baseline. We also show the adaptation results of our physical property variables. In this example, the granularity of stones and M&Ms. Through inverse optimization, the estimated granularity value converges to the optimal value, which minimizes the dynamics prediction error, measured by mean chamfer distance. We tested 9 granular objects with varying granularity, and the estimation rankings correspond, they align very well with human impressions of these objects. For example, granola having the smallest granularity and toy blocks having the largest granularity. We can observe similar outcomes with ropes and cloth of various stiffness levels. They are all consistent with human impressions. For example, for ropes, yarn is the softest and cable being the largest, most stiffest, and for cloth, model fabric is the softest and the plastic sheet is the stiffest. Finally, our method enhances model-based planning for manipulation of different materials. In this box pushing task, the adaptation of the center of pressure of the box enables more effective actions to reach the goal. For example, this non-adaptation baseline fails to reach its goal within a certain time steps. We also evaluate our approach across several other manipulation tasks, including rope straightening, granular object gathering, and cloth relocating. Our method is consistently more effective, achieving the objectives in fewer steps and with lower errors. To summarize, we have developed a unified graph-based neural dynamics model that adapts to diverse materials with varying physical properties. Additionally, we apply online estimation of physical parameters. Finally, this enhances the effectiveness and efficiency of various deformable object manipulation tasks. Finally, more information about our paper, Adaptive Graph, can be found on our project website, and we already published our code. Thank you for listening.
Questions? Yep.
How much do, first, thank you for the talk. I was curious how you're doing the perception to actually compute the graphs, and also how much do errors in that perception affect your ability to get good optimization for calculating your parameters, your like physical parameters?
Okay, yes. So the question is, how do we do perception to get the graph? One of the most important reasons why we use a graph neural network and use graph as a representation is because it's very flexible. In all of our tasks, we only use the point clouds observed using those cameras. The raw point clouds segmented and fused together. And we do some downsampling to get the graph vertices. That's our perception-based pipeline.
With like any issues where errors in that perception might affect how you're estimating your physical parameters? Like, is it robust to that?
I think the perception pipeline is pretty robust, and during our physics parameter adaptation, because we can segment the objects really well, and of course another reason is that most of our tasks are relatively in a 2D environment, so the adaptation results will come from the observed behaviors from the start state and after executing an action to the final state. So the perception model works well, and in this case, the physics, which gives us pretty robust physics parameter estimation results.
Thank you.
All right, thanks.
Thank you.
So we have one last question, and we'll move on.
My question's related. I was curious, what happens under occlusions, and I really want to understand what you mean by state better. It looks like you have features, then you create a connected graph on these features, and then push the features around.
Yes.
But I could certainly see even in your videos there are some occlusions due to the manipulator itself.
Yes. So yes, we admit that it is a current limitation of our method because we use raw point clouds as input. So if there are large occlusions, like an entire part of the object is not observable, then we'll not be able to model the dynamics of that part. But in future works, we're very interested in finding ways to solve this issue, probably by using some point cloud prediction methods, or we can use some latent representation to model the dynamics of the occluded parts.
All right, thank you. Thank you for the talk again.
Thank you.
Our next presentation is an online presentation, so we'll be playing a pre-recorded video, so we will not have any question answers regarding this presentation. So the presentation is Human-Oriented Representation, Learning for Robot Manipulation.
Hello everyone. Today is my honor to present the paper Human-Oriented Representation Learning for Robotic Manipulation. This work is done by MSc Lab in UC Berkeley. For the motivation and problem statement, we start from some observations from human perception systems. Humans in the real world can efficiently explore and interact with environments in manipulation tasks with strong perceptual skills. If we transfer such perceptual skills to robotics, robotics can perceive the world through like representation, vision detection models, affordance. We found that human can get a better perception system with some pre-knowledge like knowing where is the key object. For robotics, the representation is always learned from a pre-trained model, which covered many scenes, so it will have potential to acquire pre-knowledge during the pre-training. Therefore, in this paper, we wanted to find a way to inject human prior knowledge into robotics visual representation learning. In this work, we propose that a robust and generalizable visual representation can be automatically derived from the multiple simple perceptual skills that mirror those critical to human-environment interactions, as shown in this figure. Humans learn to extract a generalizable behavioral representation from perceptual input by mastering a multitude of simple perceptual skills, such as spatial temporal understanding and hand-object contact estimation, all of which are critical for everyday scenarios. For our method, centered on these human-inspired skills, we introduce Task Fusion Decoder, TFD, as a plug-and-play multitask learner to learn human-oriented representation for robotic manipulation for different representations. Unlike current state-of-the-art visual representations, which primarily rely on self-supervised objectives, our approach harnesses the power of these human-inspired perceptual skills with low-cost human prior. For the manipulation task, we evaluate our representations by fixed a visual encoder and attach with different policy learning, like behavior cloning and diffusion policy. These are the demos for our simulation tasks, for different embodiments. The experiment result in simulation shows that our method shows advance over different benchmarks and across different visual representations. We observe that our method improves the policy success rate compared to directly using the original representations, indicating our method can help capture human-oriented and important representation for manipulation tasks. Then, we test our proposed human knowledge injecting method in a FANUC robot arm. We freeze the visual encoder and test on behavior cloning in this experiment, and the result shows that our method can also be useful on the real robot. To verify if the prior human knowledge is injected for the visual representation, we visualized the attention map for the representation through our methods. The most right line is our representation. You can find that our representation can obviously capture a key region in the manipulation. It also demonstrates that our method places greater emphasis on the manipulation area while filtering out redundant information from the entire task area. Moreover, We inject the human prior knowledge from human videos, so we test our method on computer vision human videos benchmark and show great results. Also, it can predict the contact frame and contact region in the real human worlds. Also, the strong result of these vision tasks verifies that our method can capture the task relationship, hence making them benefit each other, showing effectiveness in learning a multitask joint representation. Finally, we introduce a dataset for industrial robot policy learning in this paper, the FANUC manipulation dataset for robot behavior cloning, including 17 manipulation tasks and 450 expert demonstrations. These are some demos from it. Thanks for your listening.
Thank you. As this is an online presentation, we won't have any questions. So we'll move on to the next presentation on dynamic on-palm manipulation via controlled sliding. William Yang.
Hello. Yeah, I'm happy to present our work on dynamic on-palm manipulation via controlled sliding. In this task, we are interested in dexterous dynamic manipulation, which we explore through this tray manipulation task. In this task, the robot is commanded to retrieve the tray, then lift the tray, and then place the tray back at its initial position, doing so all with just its end effector. This task is challenging for a few key aspects. I just want to highlight a few. The first is diverse and repeated contact mode transitions. This task heavily utilizes sliding, not only between the end effector and the tray, but also between the tray and the external supports. And throughout execution, the system is constantly switching between contact modes, which is difficult from a planning perspective. The next is the task requires sliding, which is difficult because of known inaccuracies in our frictional contact models. So this necessitates a reactive approach. Finally, we're dealing with forceful interactions at speed with the object, and this presents its own challenges for how to control for those interactions. So how might we try to solve this task? We can try reinforcement learning, or imitation learning, or methods like motion primitives or reference trajectories. And I'd actually argue that all of these probably could work on this task, albeit with significant engineering effort. However, what if we want to perform a new task? So let's consider this entirely different task where we want to rotate the tray, where it has to leverage contact with the wall in order to rotate the tray. Well, we'd have to probably retrain in simulation, or collect new demonstrations, or do additional offline planning such as generating new motion primitives or reference trajectories. I'd argue what we really want is to be able to generate some new tasks without additional offline computation, and we don't want to be able to essentially reward function hack to essentially give the algorithm the answer. So we want to really be able to specify these tasks with a very simple basic quadratic cost. And I actually argue that this is also super important because if we truly want to be able to stitch together low-level capabilities, we have to be able to specify these new capabilities in an intuitive manner. So to be explicit, we define the entire tray manipulation task with just 3 static targets and no additional references or guides. So how do we solve this task? So we take a standard approach where we abstract away the robot to just consider its end effector. And we focus on the interactions between the end effector and the tray and the external supports. We model these interactions as forces, and we assume that the end effector can be directly controlled with inputs U. This is the model we use to construct a linear complementarity system, which for those unfamiliar is a local piecewise linearization of the system, as well as a local linearization of the potential contacts as well as their activation functions. To be explicit, we consider 7 total possible contacts, 2 per support, and 3 to capture the surface-surface contact between the tray and the end effector. We generate a new LCS every control iteration by linearizing the state, leveraging Drake for both autodiff and geometry queries. Using this LCS, we leverage recent breakthroughs in contact implicit MPC that can plan for states, inputs, and forces without the pre-specification of the contact mode. I want to highlight that this really isn't trivial. We're considering 7 possible contacts per knot point. And for each contact, because we require sliding, we're considering between sticking, sliding in each possible direction, as well as no contact for each contact point. Okay, now that we have the MPC plan, we actually have to be very careful on how we actually track that plan. because we're dealing with forceful interactions. And the key takeaway with our choice of tracking objectives is that the MPC is planning with contact forces in mind. So we have to incorporate these somehow, which we do so with a feed-forward force term at the end effector. The end result is really interesting emergent motions. It's just this repositioning gate that utilizes the supports. And I want to highlight that we perform a completely different task, again specified as just now a single target, but we use the exact same LCS model with the caveat that we have to tune different gains. So in summary, we perform contact-rich dynamic manipulation using contact implicit MPC. We do so with very simple target specifications and no additional references or guides, with the caveat being that we need different gains. And I want to thank our sponsors, and I want to highlight that we perform other variations of the task as well, and all the footage is available at our project website as well as our code. Thank you.
Thank you. Questions from the audience?
You one there, center.
Right in front.
Thank you for the great talk. So I wonder, how sensitive is your method to the provided initial guess? And also, how is that initial guess obtained? And I also have a second question that I can answer. I can ask it after you answer or
Sure,
now.
I'll answer the first question first. Basically, the question is, how do you provide the initial guess? We just give it zeros for the initial guess, and then we warm start from there. So there's no, we don't give an initial guess for at all.
Okay, that's cool. So I also noticed that you had some rotational motion in your MPC or in some of your experiments. How do you model the contact for those motions?
You're talking about the rotation?
Yeah, do you model it as like a patch contact or as contact points? Or?
Yeah, so we don't capture contact patches. We just kind of approximate it with multiple contact points. So that between the end effector and the tray, we model 3 contacts to make sure to capture surface contact. And that seems to work well for a rotation. You really just need this 3 contacts to make it stable, because we don't allow we kind of fix the contact points on the end effector.
I see,
Right.
Thank you.
Thanks. We move on to the next question.
Now? Oh, no, it works, thanks. Sorry. 2 quick questions. You mentioned friction you can handle in all directions, but you have a piecewise linear model. How do you do this with linearity? And second question, quick, did you need to tune a lot your MPC solver because it's quite hard MIQ peeps problem? Thanks.
Yeah, I mean, great points. So I want to clarify, not every direction, but we discretize it into 4 directions. So we can support more directions as well, but we discretize it into basically 4. It's the 4 tangent directions of a pyramidal friction cone. And for tuning the MPC, it's very sensitive. We leverage ADMM to decouple the contact constraints and the dynamics constraints, and that introduces additional tuning variables for the consensus costs, and that's fairly sensitive. But we are able to tune in simulation, and that seems to work pretty well. It transfers pretty well to hardware.
Great. Let's thank the speaker again. Next up, we have a presentation on efficient data collection for robotic manipulation via compositional generalization. Please.
Hi, everyone. My name is Jensen. Today I'll be talking about our work on investigating compositional generalization with robotic manipulation policies and exploiting this for more efficient data collection in imitation learning. So robot manipulation tasks can vary in a huge amount of different environmental conditions. For example, even the relatively simple task of picking up an object from a table can vary in both the object that is to be picked up as well as the height of the table, among many other possibilities. When collecting demonstrations for imitation learning, there are many possible strategies for varying these different factors during data collection. In our work, we investigate whether or not we can prioritize covering individual factor values during data collection such that we can exploit composition in order to achieve overall generalization more efficiently. For example, we can consider a strategy that picks up a spoon from a short table and a fork on a medium table, and then assess whether or not a robot trained on this data can generalize to a spoon on a medium table, such that we can avoid collecting data for situations like this the composition would already address. Additionally, we can assess whether or not prior robot data in the form of large robot data sets that have previously been collected can help policies achieve composition of their in-domain data more efficiently. So in our real robot experiments, we consider the task of putting a fork inside of a container on a real kitchen countertop. We primarily consider varying the following environmental factors, which consist of the object type, the object position, container type, table height, as well as the table texture. And we designate one value per factor as part of a base set of these factor values. Here we show an example rollout for our task with just the base factor values. So in our experiments, we find that policies can indeed compose environmental factors to generalize to novel combinations. For example, when training on data that only varies a single factor at a time, as visualized by the green dots in this figure, we can often generalize compositionally to the unseen combinations as visualized by the pink dots. We call this kind of data collection strategy the L strategy, based on the shape in this figure. So when we evaluate in a compositional setting where two factors differ from the base values, we find that a policy trained on data without any factor variation usually fails to generalize, indicating that data covering these shifts is often needed in practice for success. Here we show an example of this failure when we change both the fork and table texture in particular. But when we train on data from our L strategy, which only sees each factor in isolation, we are still able to succeed, suggesting effective composition of these factors. We also observed that including prior robot data can be critical for composition. In our experiments, we specifically consider using the Bridge Data V2 dataset. When training from scratch, we often observe that even when we train on our L strategy data, the policies are unable to succeed in situations where there are shifts for two factors at a time, indicating that without prior robot data, policies can compose these factors poorly, even when seen individually. So here's an example of that when we change the fork and container type. But by incorporating prior robot data, we are now able to achieve successful composition of these in-domain data sets that we collect, suggesting the importance for facilitating composition. We additionally show that by considering compositional generalization during data collection, we can efficiently transfer policies to entirely new environments that encompass new combinations of multiple different factor values. So we first visualize the kitchen that we collect all data for our experiments in. We also show two different kitchens that we assess transfer in, which both have inherent differences, including some that we don't explicitly consider during data collection, such as distractor objects and lighting conditions. And if we do not include variation in our in-domain kitchen, then we are unable to achieve successful transfer to these other kitchens at all. But instead, if we use data that covers all individual factor values in our base kitchen using our strategy, as well as by incorporating prior robot data, we are now able to achieve successful transfer to new kitchens that has never seen before. We first demonstrate this kind of transfer when we don't consider any inherent or any additional changes beyond the inherent differences in the new kitchen, but we can also add new shifts found in the original kitchen to the new kitchen, and we are still able to achieve transfer in these settings as well. Here's an example of this with the new fork and container type in a new kitchen. So while our overall results suggest that by accounting for composition, we can make data collection more efficient, our policies are still unable to succeed all the time with certain factors. So for example, we observe this most frequently for factors that interact together physically. So on the left example, we see that if we vary the object position and table height together, which both affect the grasp motion needed for the task, then the policy is unable to compose these factors and grasp the fork properly. Another example of this is if we vary the object position and the container type together, which affects the place motion of the task based on the narrowness of the new container. So this often results in failures as well. So future work can better address improving generalization with these physical factors, such as maybe by varying factors in a more intelligent way during data collection, or just generally providing more coverage for these during data collection. Thank you.
Questions?
Thanks for the talk. I wasn't quite clear how you break it down in terms of the neural network, how you factor the policy, and then how you recombine them when you change the factors.
Yeah, so we don't do any factorization of the policy itself. This is just one big end-to-end model trained using imitation learning. The only way we break things down is at the data set level. So we have different components of our data set that expose the policy to various environmental conditions, and we consider doing this or assessing whether policy can generalize to novel combinations of these.
Great. We have time for maybe one short question. Ooh, there's one up front.
Thank you. I have a question about how the generalization would improve and to what extent these factors can be discretized, or are there something in between type of factors, which kind of you indicated with one of your failure modes.
So do you mean discretization into different factors or discretization within a factor to like different values of that factor?
Yeah, just what is the spectrum of how you discretize these factors?
Like how do we choose like which different factors we consider? Yeah, so I think in general there are like almost like infinitely many ways you could possibly characterize these types of things. I think for the experiments we specifically consider, we choose the things that we think are most relevant for like achieving generalization in like practical settings. So like things that you might vary a lot in like a real household environment, for example. And also things that we can control systematically, and like maybe like more subtle changes is more challenging to address, and we can consider that in future work.
Great. Let's thank the speaker again. Next up, we have demonstrating learning from humans on open source dexterous robot hands.
Hi, I'm Kenny, and as you said, I'll be demonstrating learning from humans on open source dexterous robot hands. There's recently been a lot of research interest in robot hands. Humanoids are wanting to do a variety of different tasks in human-like environments. Learning from human data has been a very popular way to train foundation models. In addition, there's been a lot of growing interest in prosthetic hands. What robot hand should people use? However, there's not that many available. The Allegro hand has weak motors and costs over $15,000. The Shadow hand, while it's small and tendon-driven, costs over $100,000. In my research, I've been looking to build dexterous robot hands that are low-cost, customizable, strong, robust, easy to use, and highly dexterous, which is very hard to do. My first robot hand, Leap Hand, was at RSS 2023. It's dexterous, low-cost, and strong and durable, and costs under $2,000. First, we introduced a universal abduction-adduction mechanism. What that means is, as you can see on the left, Leap Hand can move its finger left and right when the finger is down and in the upward configuration. This is thanks to the fact that the MCP side joint is after the MCP forward joint. Looking at the Allegro hand, it can move its finger left and right when the finger's up, but when it's down, it just twists in place. This is not that human-like. Leap Hand is really easy to make and repair. We provide all the instructions on our website at leaphand.com, uses off-the-shelf motors, and can be 3D printed. The assembly time only takes 3 hours. When things break, everything is modular and it's easy to replace parts in accidents. There's been a lot of community development and support in the last year. There are over 100 Leap Hands in use today and a great open source community, and people have been very willing to share code. One of my favorite recent works is DexCap, which shows a variety of different autonomous results using 2 Leap Hands. In Leap Hand v2, we announced a new hand that has human-like size and dexterity and is smaller than Leap Hand v1. It's also low cost and will be fully open source soon. We have a URDF for sim to real, and we show a lot of robust teleoperation results. The key differentiating factor of Leap Hand v2 is it has robot bones and skin. Similar to a human hand, there is skin on the outside that's soft, that's compliant, and interacts with the environment. The internal hard bone structure makes the finger very strong. The soft material twists and bends without breaking and is very durable. The internal PLA structure allows the tendon to slide very easily and allows it to grasp very tightly. This can be 3D printed in one piece from a 3D printer that has 2 materials that costs under $1,000 to buy. We also include 2 articulated joints in the palm, one near the 4 fingers and one near the thumb. This allows it to grasp really tightly on objects and tools such as hammers and other different objects. The Leap Hand kinematic structure has 17 motors and 21 degrees of freedom. This is similar to a human hand, which means we can do a lot of different tasks similar to a human hand can. A question I get often asked is, well, how do we retarget from human hand data to the robot hand? The naive approach is to do joint mapping, where you take the joint angles of the human hand and you map them directly to the robot hand. However, you'll often find that the pinch graphs are inaccurate. This is due to the fact that the human thumb and the robot thumb are very different. We introduce a hand retargeting approach via energy minimization. What that means is we want the pinch graphs and the distances from the human and robot hand to match. We train this on internet data of human hands, and this makes sure that the retargeting approach makes human-like poses on the robot hand. We use this approach on teleoperation for human video, where we have one RGB camera watching me teleoperate a variety of different tasks on leaf hand. We show that we can do a variety of different tasks in the wild, such as cup stacking or box rotation. Additionally, we can use the same pipeline to retarget human hand data from videos on the internet directly to the robot hand and arm. These priors that we learn from the internet data means that we only need a few demonstrations in the real world to fine-tune our policy from the internet data. We also said we can use the internet data along with real-world RL to fine-tune our policy. In this case, because the robot hand is soft and compliant, it does not break and it does not damage the environment, and you can really run RL in the real world. Today we'll be showing a motion capture glove at our demonstration. The motion capture glove is highly accurate position tracking at a fingertip. It's low latency, does not suffer from occlusion problems like the Vision Pro, and we'll be open sourcing our code. The Manus Meta glove has great hand tracking and is great for robot hand use. To track the arm, we have to introduce something else. We use a teacher arm approach similar to Jello and Aloha. We map the joint angles from this to the robot arm. This is very accurate and very intuitive to the user. Users can teleoperate two hands and arms, which is over 50 degrees of freedom in real time for a variety of different tasks. It's very natural to do, the data is high quality, and we can train behavior coding policies very easily to do autonomous tasks with bimanual and an arm. We'll have our robot demo on Thursday, where we'll have all three of our hands on display, and we'll also be able to teleoperate the system for yourself to try it out. And please visit our website for more results and information about our hands. Thank you.
Questions?
Hi. Are there any sensing on the hand? Because it seems that a lot of more delicate tasks requires like accurate force feedback or like other forms of like haptics feedback on your hand. But it seems that if you're just 3D printing everything, are there any ways that you can achieve like add haptics to the hand, basically?
Yeah, it's something I'm looking at. Some people have used Leap Hand and they put gel site on the fingertips. And the gel site and the fingertips give them some sort of touch information. You can also use like proprioception or like current, basically feedback from the motors themselves to tell you, how much contact you're in or how much force you have to apply to close a hand. But we don't have like explicit touch sensors that I've designed for Leap Hand, at least so far.
Any other questions? Oh, there's one up here.
Hi, good talk. Regarding Leap Hand 2, you mentioned something about skin. Can you tell us more about that?
Yeah, so the outside skin is TPU rubber. So that TPU is easy to 3D print, and it's like, it's got that like grippy texture to it, and it's also flexible. So like when the finger comes in contact, that rubber will bend out of the way, and it won't, shatter or break like ABS or PLA. And then the internal is PLA, which, it gives it that stiffness, so it's still pretty strong. So like you're basically trying to balance something that's soft and also something that's rigid, and the softness gives it that like ability to be durable while still being strong.
Okay, let's thank the speaker again. So next up, we have reconciling reality through simulation, a real-to-sim to real approach for robust manipulation.
Thank you. Hi, everyone. I'm Marcel, and I'm going to present our latest work on reconciling reality through simulation. We also call it Rialto. So our goal is to learn robust policies with minimal human supervision. But how can we get there? So on one side, we could do imitation learning. We could collect a set of demonstrations in the real world. However, for this case, we need large human effort just to collect these policies and train robust policies. On the other side, we could do reinforcement learning in simulation. However, in this case, then we would need expert effort to create the scenes and also to do reward engineering and obtain the policies. What we propose instead is to construct simulations on the fly to improve the robustness of imitation learning. And we call our method Rialto. This is an overview of all of the big variety of scenes that we can tackle with Rialto. And we basically show that it's very robust to a variety of disturbances, distractors, and that it can be applied to a large variety of scenes. So basically, the overview of our method is that we're going to leverage digital twins of the real world to do reinforcement learning in simulation of real-world demonstrations that we collected. The first step of our method is to basically bring the real world into simulation, so do the real-to-sim transfer of the scenes. In this case, what we do is we take our phones and we can take a scan of the environments using any 3D reconstruction method. So as long as we can extract a 3D mesh out of the video, our method is going to work. And in the paper, we explain more about we give recommendations on which techniques to use. Then, when we extract these 3D meshes, we gave a new GUI that basically allows the user to set up the scene, add articulations, add different objects, and this is fairly easy to do and can be then directly imported into the simulation, and we can do it within 4 minutes or something like this. The next step becomes bringing some real-world demonstrations into simulation for later RL fine-tuning. And we do it through this new procedure that we call inverse distillation that consists in training a vision-based policy from some real-world demos. We then roll out this vision-based policy into simulation to try to collect a set of successful trajectories. And we then put this into a privileged information demonstration data set. Then these demonstrations are going to be used for RL fine-tuning with just sparse reward or with this extra imitation learning loss. Basically, having these real-world demonstrations are very important because our models are actually might have some flaws, and then the policy could exploit the model's inaccuracies. But the real-world demos makes it so that the policy is actually going to be transferable to the real world. Then the next step becomes just once we have these state-based policies working in simulation, we need to transfer it to the real world. And in this case, we do some standard sim-to-real transfer, so teacher-student distillation. However, we add an extra code training loss on the real-world data that we collected on the second step, and we show that this actually narrows the sim-to-real gap. Then now, let me show you a few results of what we obtained with Rialto. We're basically going to show a big variety of scenes where we can do disturbances, add some distractors into the scene, and our policies still are successful enough. So this basically to show you a bit the structure. So on the right, we're showing how it compares against imitation learning. So in this case, we compare imitation learning with the same set of demonstrations. We just collect 10 demonstrations in the real world, and then we compare using Rialto, where we can do the RL fine-tuning against this imitation learning. And the performance is pretty significant, so we go from 22% to 80% on the other case, and this happens in all of them. On the bottom left, you can also see the simulated environment that we use for Rialto, so you can also get a sense of how realistic the digital twin looks like. And then on the rest of the panels, we see the different disturbances that we bring Rialto through. And we show again that we can move the objects around, add distractors, and the policy is still very robust to all of these changes. This is one additional task where we put mugs on the shelf, and I can just move the mug around, remove it from the hand, bring it from the shelf back into the table, and all of these, none of these behaviors have been seen in the demonstrations. It's all a product of the reinforcement learning in simulation. And that's going to be everything, so thank you very much, and I hope to see you during the poster session.
Thanks, very interesting. So when you build the digital twin, you must be able to have a notion of an object. So how do you extract from your sensing data and you understand what is a separate object?
Yeah, exactly. So in this case, so there's some latest work that are trying to basically automate all of the articulations from the scan into the simulated version. In this case, we have this GUI so that the user can directly set a bounding box around the objects and separate them and have them as different free rigid body objects.
So was that included in the 4 minutes that you said setting up the
Yes,
data?
yeah, exactly. So that is within the 4 minutes. Yeah, exactly.
We have time for one more question.
Thanks a lot for the talk. So could you elaborate a bit more in simulation? What all do you randomize?
So in simulation, we basically apply some disturbances to the actions and randomize the object poses. We also add distractors so that then like the vision becomes also robust to it.
Great. Actually, we have time for one more, so.
We also have someone.
Talk. Do you know, how do you infer the physical properties of the objects in your simulation?
Yeah, so that's a great question. So actually, what we claim is the model is actually imperfect, but it's close enough to the real. So we have basically some default values that we can reuse across all environments. And then the important thing is that these real-world demonstrations show a behavior that is actually going to work in the real world. So just this biasing towards this realistic behavior is going to allow you to not exploit those inaccuracies from the policy. As we saw, for example, the microwave had the hinge on the wrong position, and if you just don't use the demonstrations, then it's just going to exploit it. But just the real-world demos make you like go towards the right behavior that is then going to transfer.
Thanks.
Great. Let's thank the speaker.
Thank you.
And our last talk for this session is SAGE, Bridging Semantic and Actionable Parts for Generalizable Articulated Object Manipulation under Language Instructions.
Okay, hi everyone. I'm Haoran, and I'm happy to be here to present our project, SAGE, a framework aiming at language-guided generalizable articulated object manipulation. Well, articulated object manipulation can be very challenging due to its diverse semantics, geometry, and actions of articulated objects. And as we all know, general-purpose large models have rich semantics understanding, while domain specialist robotics models can understand physics and actions better. In our proposed model, we hope to mix their strengths together to balance semantics and physics. And here, imagine that you bought a new blender for your kitchen. To make juice with it, you need to truly understand the semantics and the functionalities of its parts, in this case, the container. To turn on this blender, the robot needs to press its container, and it will blend the ingredients in it. And here, we understand the part at the semantics level as a container, just like the container in a coffee machine. It's used to load ingredients. But when we want to turn on it, we consider the part at the action level as a part to be pressed, just like a button. So here, we introduce our SAGE framework to understand the parts at both semantic level and the action level. Our pipeline takes human instruction as input and interprets it into a semantic part and an action program. And the action program is a triplet of semantic name, join type, and state change. To achieve so, we first mix the domain specialist model, GAPRNet, and the general purpose large vision language model, GPT-4V, to generate a context-aware scene description. And the scene description, along with the human language instruction and the optional user manual of the object, are joined embedded into a template prompt, and then the input to GPT-4V to generate semantic parts, names, and action programs. We further ground the semantic part into a target actionable parts. Here, for the blender, the semantic part is the container, and the actionable part is the slider button. We then estimate the part pose along with the press motion. And finally, we execute the action and turn on the blender successfully. And here we show another very interesting task. The instruction is to open it without object name. And the same as before, we first generate a context-aware scene description. And then the semantic part and the action programs. And here, with our grounding model, we get the actionable part pose and joint. But here, the attempt to open the door by utilizing the handle where it was closed failed. This is because the microwave cannot open the door directly using the door, but need to use the button to open it. And we give feedback on the target part pose and the actual part pose to our planning model GB4V. And it found that here is some failure and decided to replan. This time, with its prior knowledge and the part analysis, GB4V says pressing the button to open the door slightly, followed by an action to revolve the door. And you can see here the new policy executes and open the microwave successfully. And here we show more video clips to demonstrate the diversity and the generalization ability of our method. And our method can handle diverse and even vague instructions and have a very strong generalization ability. Okay, thank you.
Questions?
This is sort of a philosophical question. Something that seems to be a trend in a lot of the papers in this session is like using these existing models, and then as those models get better, hopefully these methods will get better. I'm curious if you've thought about closing the loop the other way, like using the insights from deploying the robot and seeing where it fails, like to actually just improve the models as opposed to, I guess, change your prompt at runtime.
Here in our, if I understand your question correctly, maybe you want to combine some more like advanced model to our system. I think here during the like policy execution, we use some heuristic to open the target pose. If we predict the action, for example, the pressing the button, open the door, we have some heuristics proposed in our prior work, GapperNet, to open it or press it. And if we can like add more add a more advanced method to the execution part, I think it will be better.
Okay, I think there's a question over here. Yeah.
To understand 100%, I would like to ask some questions. How can this robot interactively know if it failed whenever it fails?
Yeah, good question. I think this is the power of the combination of our 3D like small models and like large vision language models. For example, during like the execution of the like open the microwave, we have our 3D small models to track the part pose, and like during the like interaction, we found that we want the part to open like for example like 90 degrees, but it's just open a little bit. Maybe some failure case happen, and we give this feedback from small models to large models, and the large models will understand, okay, maybe some failure happened, and we will reply, and to get a better like plan.
So the 3D states for the goal is manually predefined before this?
Yeah, for our articulated object, we mainly focus on the parts of the articulated object. And our small model is very generalizable across different articulated objects, but only here we only focus on articulated object, and we focus on part tracking.
Understood, thank you.
Okay, let's thank the speaker again. We'll break for lunch.
Hello, everybody. Welcome to session 4 on field robotics. We'll go ahead and get started. So my name is Derek Paley. I'm from the University of Maryland. I'm the director of the Maryland Robotics Center. I'll be chairing this session.
Hello, and I'm Nara Karapetyan. I'm from Woods Oceanographic Institution, and I'll be co-chairing with Derek.
At this time, I'd like to invite our first speaker to come on up to the podium, Tirtha. All right, Tirtha will be presenting on demonstrating event-triggered investigation and sample collection for human scientists using field robots and large foundation models.
Thank you.
Thanks, everyone. My name is Tirtha, and I'm going to present this work which has been co-authored by almost 21 people, but more have contributed to this work. It's a large-scale collaboration of field robotics and human-robot interaction. Now, what we wanted to really understand is how we can integrate the state-of-the-art technologies as well as large foundation models into doing field sampling, and how can field robotics help in this domain. So this is a collaboration between Cyro Robotics, Data61, Mineral Resources, Space, and Astronomy, and QUT. So we set up a scenario where there's a mock sandpit which is mimicking a remote area, and we had a base station set up almost 100 and 150 meters away from the station so that there's no contextual bleed from the location by the human. So the human is giving a command directly to the robots. Our robots are ATR-based tracked robots. We have two robots. One of them has an arm, which has a custom soft gripper mechanism on our front, and then the arm is a Frank Amica Panda. We are detecting an event based on vibration sensors, which is feeding back an information into the user interface that you see here. The user interface, the user is actually communicating with the robots through a natural language interface, which is parsed through a prompted GPT, which converts the commands into specific tasks that the robots can perform. So it's not an open-ended task. The tasks are known to the robot. So the scenario you can see starting from left, somebody had thrown a rock. We are mimicking that as a meteor strike. The vibration sensors has picked up a location. These locations are called impact zones. Based on the location, the human operator can actually query the scene based on the semantic information that has been pre-built by the map, by the robots, by exploring. And based on the semantic information, the human can actually understand and identify actions to take. So here we have a scientist who is giving a command to the robot to do a particular action, and she's an astrogeologist, and she has very limited information about how to interact with the robot directly through the robotic interfaces like RViz, Gazebo. So we are using the notion that a natural language interface can actually enable large swaths of domain experts to interact with the robots. So she has requested the robot to go to a particular impact zone. Now, this zone is not precisely known. This is a rough estimation of where the impact could have happened. The robot is then starting to investigate that local area to find out what those variations in the scene has happened. So based on the information that's coming out of the in-hand camera, you can actually see that these images are sent back to the human operator, and you have an interactive mechanism where you can query the images based on the vision language models to query what areas of interest to be shown. So for example, in this case, the operator has requested to see rocks, and you could see in the paper that there are different versions of the rock which is coming out from the operator's input. Once a specific rock has been identified that needs to be picked up, integrated holistic reactive controller is activated, and the whole body reactive control actually goes towards and stabilizes the arm. And then there's an open loop control which goes forward and picks up the rock. Now, the critical part of this is we have an in-house built soft gripper mechanism, which is enabling much more robustness than a hard object to pick up the rock. And based on what the robot has picked up, the operator can then give a command for the robot to actually go to a new location, do more semantic understanding, do some scientific experiments, or send the robot home. So this is a very simple overview of what we think are the pipelines and the fundamental steps that we need to take to move the scientific area of investigation forward. So we have a demonstration set up and in the lunch and in the tea time. So I would request you to come and have a look. And if you have more technical details, they are present in the paper. Thank you.
Do you have any questions for our speaker? I've got a question for you. So for those of us who've worked in the field, there's a big leap going from the laboratory to the field environment. But in your application, you're thinking about going to the lunar environment. So what additional considerations have gone into this system to allow it to operate on the moon?
So right now, I must confess that this is not built for lunar surfaces, as you can see with the robots and the controllers that's running. So we are actively working on doing remote presence and remote operations, which means that we have to ensure that the communication bandwidth is limited. There's a delay in the communication, so the data that might be coming back is maybe a little bit more sparser. It may not be fully actuated. And while we have separated the human and the operator and the robots a little bit, like 100 meters, they're still running through a local network, which will not have it in the lunar environment. So what could potentially happen is the failures that are occurring in the lunar environment has to be addressed both at the location of the robot itself, and then if it is failing to do certain things, to trigger that back into the human request. The foundation models that we are looking here, they are querying the GPT models, which will not be functional if these robots are in the moon, so they will have to run some embodied AI system or smaller level scales, but we hope that these smaller embedded AI models can be used in a meta level to trigger very task-specific foundation activities in a much more robust manner.
Great, thank you. Let's thank our speaker again.
Thank you.
Right, our next speakers are Ryan Lee, John Harrington, Russell Wong. They are going to be presenting Crater Grader, autonomous robotics terrain manipulation for lunar site preparation and earth moving.
Okay. Hi, good afternoon. Yeah, we are presenting Crater Grader today. Some motivations. Lunar infrastructure is of utmost importance for developing a sustained presence on the moon. That being said, the terrain itself is not ripe for this type of development, as it is full of craters, rocks, and is generally very unstructured. We present Crater Grader, a novel system for autonomous robotic earth moving within lunar constraints to address this type of issue. We frame terrain manipulation as an optimal transport problem in which we apply material movement utilizing linear programs. We constrain our system using lunar constraints, such as GPS-free robot localization with site work precision. The main objective of Crater Grader is to take some plot of unstructured terrain, such as full of craters, and make it flat. And this is measured using two key metrics, the first being the grade angle of the fit plane with respect to the ground plane, and the smoothness of this fit plane. These requirements are lifted from the NASA Luster RFP, which specify a 1 degree desired grade and a 1 centimeter smoothness. Crater Grader is a purpose-built platform built from the ground up, utilizing custom hardware. We have two main modes for manipulating terrain. The first being an actuated blade beneath the vehicle for bulk transport, and second being a drag mat smoother out the rear, which smooths out high-frequency terrain variations.
Crater Grader's localization sensor suite was designed to be flight-forward, considering lunar operational constraints. It incorporates a novel application of a robotic total station for lunar construction for precise GPS-free positioning and localization, and as well as utilizes an IMU and onboard encoder odometry for slip estimation during terrain manipulation. Dynamic height maps are generated from stereo vision and represented as 2.5D height maps, where each individual cell is a 1D common filter. Noise is injected to this map as needed during terrain manipulation. So our optimal transport planner takes the initial site representation and converts it into representations of high and low points from our map, represented as source and sink nodes. What we then do is determine what the optimal source to sink material transport assignments are between these high and low nodes in order to convert the site into a desired design topography. So we separate this into two cases. The first one is where we think there is more sink volume than source volume. And in this case, we recognize that because we can utilize all the source volume, where we have an inequality constraint, recognizing we want to reduce all of it, while having an inequality constraint and recognizing we don't necessarily have the same guarantees for the sink volumes. And we separate these cases because we are able to minimize what would be a mixed integer linear program to two sets of linear programs to reduce time complexity during runtime. Equivalently, the second case is where we have more source volume than sink volume. And in this case, we recognize that we'll be able to fill all the sink volumes in our optimal case, but we will have excess source node volumes. We have these two different cases as mentioned, recognizing sort of how there will be cases in our work site where we could have the excess volume in either the source or the sink. There could be extensions to this in the forward.
Using these source-to-sink nodes as waypoints, we then use an online A-star lattice planner to generate kinematically feasible trajectories to traverse on. We additionally incorporate a topography cost to avoid being high-centered when climbing terrain. We conducted experiments in the physical sandbox. In A, you see us performing an exploration pass to map the initial work site. In B, we conduct grading to do bulk material transport to grade the craters. C shows intermediate steps within the process, and D demonstrates a comparison between initial and final worksite topographies. We also extended to simulation environments. This is an example lunar worksite where we applied our transport planner to and demonstrate that we can be generalizable to multiple craters as well as arbitrary terrain. The black arrows show the waypoints. Then this is our hardware experimentation. As you can see, Crater Grader is fully autonomous and can conduct end-to-end grading with an actuated grading blade. You can see Crater Grader currently pushing in the crater rim into the center and backing out for the next pass with the visualizations there. Through end-to-end trials as well as a live demonstration, we have shown to be able to grade 1 meter craters within the sandbox up to NASA specifications. These include the previously mentioned grade and RMS smoothness specifications with the comparison on the right for pre and post grade. Thank you very much, and we're happy to take any questions. Thank you very much.
Thank you. Any questions from the audience?
Thank you, and thanks guys for a cool talk. I was wondering, like, what was your motivation for doing a custom platform, you know, with all of the extra effort that brings, and like, what are the key design features that that it has that are relevant to your application?
Yeah, that's a great question. So one of the main reasons we chose a custom design platform was it gave us the flexibility to sort of try different terrain manipulation end effectors. And so, for example, having this large sort of underbelly center for us allowed us to sort of test different forms of blade control. We ended up realizing that we were able to do something relatively simple, but it provided the flexibility during the time. Definitely something we would consider going forward. In addition to that, we also had the explicit steering was something we considered as well, but we just wanted to keep things sort of this balance between simplicity and allowing us to sort of focus on the core autonomy problems.
We probably can have one very quick question.
Hi. Oh, it's a bit loud. Okay. So I see in your simulated experiment where the car is larger than the crater, which won't be the case on the moon, right?
I see it. Well, that's a great question. So I think the question was that in some cases the robot is larger than the crater, which may not always be the case in reality. So we were following the specifications from a NASA RFP, which particularly focused on craters that were up to 2 meters in diameter at maximum. That is because usually the work site that would be chosen for this kind of operation would not be an area with overly large craters.
Okay, thank you. Yeah, that's much clearer.
Right, thank you. Let's thank our speakers again.
Thank you very much.
Thank you very much.
At this time, I'd like to invite our third speaker, Lan Tao, to come on up. He'll be presenting poem, Probabilistic Online Attentive Mapping for Efficient Robotic Information Gathering.
Hi, so I'm Lan Tao Liu, and I want to present the work on behalf of other authors who are not able to travel. So robotic information gathering answers how the robots can collect the most useful data to learn an accurate model of some unknown function with applications such as environmental monitoring, 3D reconstruction, search rescues, etc. So here is one example. Assume we want to deploy an underwater vehicle to map an unknown seafloor and with limited traversals and a limited data collection. And the data here must well characterize the seafloor elevation features. In other words, the data must be informative. And this typically requires probabilistic model, and a Gaussian process is a good option for modeling spatial mapping. So we recently proposed a tentative kernel that allows GP to pay more attention on complex regions with non-stationary kernel scales. And this process typically requires cubic time. And to improve it, one natural way is to leverage the stochastic variational GPs that approximate the true posterior with a sparse model using a set of a condensed point called inducing points. However, the marriage between the attentive kernel and also the SVGP does not end up well because the optimization process struggles to simultaneously optimize both the inducing points and also the length scale, leading to model degeneration. And to solve this, our solution is the model disentanglement and also guided optimization. And we found that the optimization of the inducing points and also length scale they are highly correlated and can be computed using pivoted Chomsky decomposition, which essentially assigns more inducing points around complex regions. And then all the model parameters can be updated using variational expectation maximization, where the E step improves the inducing points and also variational parameters, and the M step refines the hyperparameters. And this is called probabilistic attentive mapping, and it is effective with a linear time complexity. Our goal next is to improve the complexity to be constant time so that we can make a decision online. And first, if we apply the PCD on the entire data set, and that requires linear time. However, instead, we want to apply the PCD on the previously optimized inducing points plus the newly received data, and that requires constant time. And for the update of the variational parameters, and we again want to avoid the using of the entire data set, and we develop the update mechanism to be iterative, where each iteration has two additive terms, and one term is about related to the older data, and the other is related to the new data. And this allows us to incrementally append the new data term with constant time. And finally, for the hyperparameters, and our observation is that the robotic information gathering is not strictly a streaming problem where all the data are used once and then discarded. In robotics, data is expensive, and we want to leverage the fact that we have all the data and leverage about the mini-batch stochastic gradient optimization, and that also requires constant time. So this demo showed that we can attentively allocate all the inducing points with constant time, and we validate our method with many seafloor maps, and compared to the streaming sparse GP variance, we show that our model is always superior to, in terms of the model accuracy and also the uncertainty quantification with really impressive practical runtime. And this example shows that our method, the POEM, can allow the robots to quickly identify complex regions by collecting more samples around the complex regions. And in contrast, the baseline failed to do so and collects the data sampled in a uniform but uninformative way. And other baselines can also miss important portions on the most complex region on the right. In conclusion, we investigate and also review that the training for sparse GPs with the next-generation kernels is challenging, and we propose the constant time update rules and validate the method with extensive experiments. And we also open source the code where the code link can be found in the paper. Thank you.
Do we have questions for our speaker? I have a question for you. So if I understand correctly, there was an initialization phase where the robot collected initial measurements in order to calculate the statistics. Is that the period of time when the hyperparameters were estimated as well?
You're right. So for GP, we do require some rough estimate about the entire environment, and therefore we have to deploy the vehicle to do a quick sampling in the entire space. And that stage does not need to be very advanced, any planner, even random walk can be good. It just allows us to get a quick idea how we can update or warm start the hyperparameter estimates. And that's what we need. So it's a pretty, I would say, very weak assumption that can be realized very easily.
And I understand this application was for bathymetry, but would it apply to time varying estimation as well?
I believe so. So GP applies to like a multivariate, multi-dimension problems. And so we just increase the dimension by 1 time. So I think that should be applicable.
All right, let's thank our speaker again.
Our next speaker is Justin Liddard. He will be presenting blending data-driven priors in dynamic games.
Hi everyone, my name is Justin and I'm excited to present our recent work on blending data-driven priors in dynamic games, a framework that we call KL games. So recently, data-driven policy modeling has proven to be a powerful tool for learning complex tasks from diverse data sources, such as in traffic prediction, drone racing, and robotic manipulation. However, these policies are, of course, not perfect. They're often limited by their data sets, which tend only to have a fixed log of past behaviors. In other words, they don't tell us what an agent would have done in response to slightly different events. Of course, in the real world, robotic deployments may involve multiple interacting decision makers in closed loop, which requires strong counterfactual reasoning. As an example, let's see what happens when we deploy MTR, a state-of-the-art motion prediction model, in closed loop on the Waymo OpenMotion dataset. The result is quite a few collisions and interactive edge cases. Although these data-driven methods get us most of the way there in terms of a prior for human behavior, small prediction errors can lead to extreme consequences, which we want to avoid by reasoning about agents' objectives. Luckily, dynamic game theory provides a theoretically tractable method for running closed-loop policy optimization fast and online. But we rarely know agents' incentives exactly, which is where data-driven methods are helpful instead. In this work, we see the best of both worlds. We want to blend the data-driven and incentive-driven behaviors by formulating a multi-agent interaction as a dynamic game. Our insight is that by introducing KL regularization into differentiable model-based planning, we can frame a multi-agent interaction as a dynamic game. Our policy optimization objective is given as a sum of task and behavior cloning costs. The cumulative stage cost term in blue tries to optimize the task, while the KL divergence term in orange tries to keep the policy close to the reference provided by data. As we modulate our scalar regularization parameter lambda, we can interpolate between these two extremes. In the KL games framework, we assume that an agent has access to 2 key pieces of information. We let a data-driven prediction model serve as a prior for each agent's task uninformed behavior, and as with other multi-agent planning approaches, we assume access to some user-specified planning goals and constraints. This information respectively gives the reference policy from data and the stage cost for the task from our expert knowledge. Then we perform scenario optimization to balance these 2 incentives across a variety of stochastic rollouts. We use a game sheet to define a scenario, and we solve each branch with an iterative linear quadratic game. The resultant policy is a Nash equilibrium, where each agent has no incentive to deviate from their strategy. Since this Nash equilibrium is a mixed strategy, or in other words, a probability distribution, we can still capture multimodality. Thus, we can close the decision loop by sampling an action from this multimodal policy. Although solving for mixed strategy Nash policies can be difficult, we leverage information theory and show that our Nash policy takes the form of a reweighted Boltzmann distribution. Specifically, the blue term says that actions with less favorable long-term outcome should be exponentially less likely, while the orange term favors actions that are more likely under the offline data distribution. With this type of policy, our framework gives a robot 3 key capabilities. First, the robot's behavior policy is a product that blends or interpolates the task-driven and data-driven behaviors. Second, the goal-aligned incentives guide the resultant policy towards actions that are favorable in the long term. And third, the entropy of the prior affects its informativeness. We show in our paper that KL games are a superclass of maximum entropy games, another popular framework for modeling interactions. Now let's see the KL games policy in action. In this example, we use a real human driving data set of simulated races on the Thunderhill Raceway in California. On one extreme, we write a conservative driving policy using handcrafted task functions. This policy doesn't crash, but it's also terribly uncompetitive. On the other extreme, we write a conservative driving policy using handcrafted aggressive overtaking reference policy learned from the Thunderhill Racing dataset. This policy is overly aggressive and unsafe. And we show that using KL games, the ego agent is able to leverage the best qualities of both policies in order to safely overtake. We also tested KL games in a larger scale study in urban driving using the Waymo OpenMotion dataset. In this setting, we focus on steering the MTR reference policy towards actions that are more aligned with the car's goals, such as not driving off the road or colliding with other agents. Now, when we roll out the MTR baseline, which isn't trained with these incentives, the fast-moving car collides with the slow-moving car. With KL Games, however, we can avoid this with policy guidance via additional penalties for undesirable behavior. In this next video, the MTR reference policy is optimized online to avoid the slow-moving car, and thus avoids a collision while staying close to the car's data-driven motion model. We tested KL Games against our MTR baseline across 500 highly interactive scenarios from the Waymo OpenMotion dataset. When I play these next two videos, notice how both rollouts look quite similar, but the rollout on the right, using KL Games and the data-driven prior, avoids a collision while preserving the natural movements of all agents in the scene. In summary, KL Games provides a framework for closed-loop policy blending using behavior models as a prior. And if you'd like to chat more about our method, please come visit our poster session after the plenary and visit our website for additional information, videos, and code. Thank you.
Thank you. Questions from the audience?
This is very interesting. Maybe I misunderstood the notation. I just wanted to understand more. Does solving this require somehow, like, are you differentiating through your prediction model? And like, what is the computation time of doing so? And related to this, if you had to scale this up to take in more information than just like top-down state information, how would this potentially scale?
Sorry, could you just raise your hand so I could see where you're at? Oh, yeah. So in our framework, we assume that the reference policy is given as a distribution over actions. And so in our experiments that we did, we just sampled just a single trajectory from our motion model. So that can be done efficiently. And then we can just solve a dynamic game, which scales relatively favorably in the state dimension. And the limitation is basically solving a Riccati equation. So that can be done as fast as you can do a matrix inverse, essentially. However, there is an issue of going off policy. So if you can imagine, like, your resultant policy from the game will be different than the reference policy as time goes on. So what you could do to fix that is resample from your reference policy as you compute the game, which would make the game a bit slower to solve, but still possible if you have a fast enough inference for your reference policy.
Thank you. We'll leave other questions to the poster session. Thank you. Let's thank the speaker again.
All right, this time I'd like to invite our next speaker, Siddharth, to come on up. And Siddharth will be presenting Demonstrating Hound, a low-cost research platform for high-speed off-road under-actuated non-holonomic driving.
Hi, my name is Siddharth Talia, and I'm demonstrating Hound, a low-cost research platform for high-speed, off-road, under-actuated, non-holonomic driving. Off-road environments can present interesting challenges for perception, planning, and control, with applications in agriculture, search and rescue, and so on. Dirt, dust, and uneven terrain can make planning and control hard. Occlusion, sensor degradation, and so on can make perception non-trivial. However, solving these problems requires access to an off-road autonomy research platform. So what makes building such a platform non-trivial? Well, to survive elements of the nature, we can build an enclosed shell. To survive direct contact during a collision, we can inboard the sensors and the compute. To prevent large physical shocks from collisions, the remote operator can always use an e-stop. However, preventing and surviving damage from rollovers is not trivial. You see, off-road vehicles can roll over easily at high speed due to their high center of mass. This means you can damage the vehicle and the inboarded sensors without even hitting anything. The smaller the vehicle is, the faster this happens, and e-stops won't help you here. So, rollovers are hard. The AutoRally project has shown one way to address this problem, through physical ruggedization. Effectively, you make the vehicle into a tank, so it doesn't matter if it rolls over. However, this will now add cost and complexity. So, our question is, can we make an off-road autonomy platform as accessible as an on-road autonomy platform such as the Musher or the F-110? Our key insight is that a software-based low-level rollover prevention system is one way to reduce the ruggedization required. This now allows us to use cheaper components and off-the-shelf parts, making the cost comparable to the platforms such as the F-110. We now introduce Hound. The Hound integrates a low-level rollover prevention system into an autonomy stack aimed at off-road aggressive driving. This includes the software referring to the perception system that provides real-time elevation mapping and a control system that uses MPPI, as well as the hardware referring to the sensors, the actuators, and the 3D printed parts. For rapid development and testing, we integrate our stack with a high-fidelity simulator known as BeamNG. Here, we use a full-scale car for general off-road autonomy experiments and a small-scale car for Hound-specific experiments. The integration with the simulator has two modes. First, the software-in-the-loop mode, which spoofs everything up to the perception system. This, for instance, is useful for statistical analysis of the control system. And the second mode, hardware-in-the-loop, which spoofs everything up to the hardware. Here, the simulator integrates with ROS and provides raw sensor measurements. This can be useful for debugging deployed software. With regards to the rollover prevention system, we evaluated in simulation over 4 scenarios, 50 trials, and using 2 different platforms, a big car and a small car. We find that the rollover prevention system eliminates rollovers in all but the hardest scenario, that of a small car on a bumpy surface at high speed. In this scenario, the vehicle regularly loses ground contact during small jumps, which makes the system under-actuated and makes preventing rollovers much harder. We also test the system as a whole in the real world at speeds as high as 7 meters per second or 50 kilometers, multiple days, 4 different terrains, and without any repairs. Through our real-world experiments, we find some interesting future directions of research. During the real-world testing, we observed 3 rollovers, which happen when the vehicle takes a jump or loses ground contact. This is in line with what we observed during the simulations. To our knowledge, mid-air orientation control of such vehicles is an underexplored area of research. Second, sensor degradation in off-road environments can pose interesting challenges to perception. Dust clouds can confuse depth sensing and actively generate occlusions. This can be detrimental to downstream tasks. In summary, we demonstrate Hound, a low-cost off-road autonomy platform that aims at making such research accessible to a wider audience. We thank the audience for their patience and are happy to take questions now.
Questions for our speaker? There's a question in the front middle. We have
great work. So I have a quick question about, I'm still trying to figure out what is the output look like, so which may be a kind of a trajectory. Then my question is like, because I mean, you use elevation mapping and also you can only partially observe the, for example, there is a slope, maybe you cannot see something outside of this. So I just wondering, for example, for the cost, I mean, the most conservative way, maybe you just slow down and then pass it instead of jumping. So I'm just curious about such
I see. I see. So the safety system that we have is proprioceptive. It's reactive. So it's not exactly a planner. Think of it as a like a watchdog timer or a watchdog that's continuously operating at a lower level. So it's not planning forward. It's trying to just look at IMU data, wheel encoder data. It's not relying on any elevation maps. We did that for certain reasons, and I'm like happy to explore those reasons if you want to come and chat during the demonstration.
Any other questions? In the back, we have a question right there.
Cool stuff. Could you comment a little bit on how much of the vehicle's inherent agility you need to sacrifice to give this guarantee or a high probability of safety in operation?
Yeah, that's a great question. That actually is very important. I think we were able to get at least 80% of the lateral acceleration capacity. So if the lateral acceleration capacity is like 1g, assuming like you have there's like a critical lateral acceleration at which the vehicle will roll over. If that's like 1g, we can maintain up to 0.8 g's with the prevention system. We are being a little bit conservative in the real world because like I don't want the car to roll over. In simulation, we can actually go all the way up to like 0.9 something g's, but it's simulation, so it's like, you know, you get rollovers, it doesn't matter. In the real world, it really matters. So we're a fair bit more conservative in the real world, yeah. Thanks.
All right, let's thank our speaker again.
Our next speaker is Tyler Han. He will be talking about model predictive control for aggressive driving over uneven terrain.
Good afternoon, everyone. My name is Tyler Han, and today I'm presenting work from the University of Washington on our off-road autonomy project. Now, by off-road, we mean driving in completely unstructured terrain in any environment with no prior information, and as much as I'd like to sit back and play all the footage we have to prove this point, this work's been conveniently cited as one of the most aggressive systems in the literature. Naturally, a task and system this complex is designed to handle many different objectives. Today, I'll be focusing on one aspect of our system, which is reasoning about terrain geometry at our aggressive speeds. So why exactly is high-speed uneven terrain challenging? There are already robots at high speeds over flat terrain, as well as robots at low speeds over uneven terrain. So why don't these systems generalize to high speed and uneven terrain? As we've experienced, the combination of high speeds in uneven terrain subjects the vehicle to unmodeled forces that can result in failures like rollovers and ditch crashes, which we'll address in this work. To quickly introduce our system, the platform we're working with is a Polaris Razor Turbo S4. While there are 4 GPUs, the control algorithm is using only one of them. And in software, the sensor data feeds into a perception module, which provides an elevation map and a cost map to MPPI, which is our sample-based MPC algorithm. Oftentimes, obstacles like trees and ditches aren't fully perceived until the vehicle is only meters away from them. To be sufficiently reactive to new information like this, our representation is made simple enough to be computed quickly. To this end, our MPPI algorithm uses a fast two-dimensional kinematic bicycle model to sample rollouts. However, these simple representations introduce bias when these rollouts are evaluated, and because of this, it's important that our approach can accommodate these modeling biases during deployment. To derive our approach, we begin by projecting our sample rollouts in the kinematic plane onto the elevation map and proceed by backing out the desired 3D dynamics using a simple force-torque model. This model computes the total rotational torque at some point in time along a trajectory, which can be broken down into torques due to gravity, inertial acceleration, and ground forces. However, because these trajectories are sampled with a coarse kinematic model, the required ground forces may sometimes be infeasible, such as requiring the vehicle to be pulled down towards the ground. Because of this, we simply reimagine the ground force to be a fictional value called the residual torque, which grants equality to the left-hand side here. Then depending on the axis component of this torque, we constrain our optimization to select rollouts that, 1, prevent rollover by choosing the body roll axis, or 2, safely traverse ditches by choosing the body pitch axis. When implemented with MPPI, these constraints can be computed in place in parallel across samples and the control horizon, and in constant time on a GPU with little to no impact on the overall runtime of 30 Hertz. MPPI now efficiently reasons about terrain geometry at our high speeds. In our rollover experiment, we execute high-speed turns on slope terrain using both the autonomy and the human expert. We find that our constraints cause MPPI to behave qualitatively similar to the expert during on and off camber turning. We also find that as we increase the residual rolling torque limit, the robot makes successively more aggressive turns. In our ditch experiments, we perform ditch traversals with both the autonomy and the expert. The upper and lower bound on the residual pitching torque have different effects. We find that upper bounding the pitching torque, we can tune how aggressively the vehicle enters ditches at the cost of wheel grip and control authority. By contrast, the lower bound tunes how aggressively cuts of ditches are taken at the cost of higher impact forces. Ultimately, our main goal is to quickly and safely drive from point to point off-road. To this end, we deploy our method on 2 comprehensive off-road courses and compare it to the pure geometric baseline, which uses only attitude angles to combat rollovers and ditches. Our method beats the baseline method by 33 seconds on the tour due to the baseline's 8 false positive slowdowns. Using no ditch control method results in 1 intervention due to unsafe behavior. Our second course is called the Baja. This course is a 3-kilometer stress test of the robot with repeated ditch reversals, sharp elevation changes, dense vegetation, and rock fields. Here, our method really outshines the baseline method, improving by a total of 2 minutes and 28 seconds, which is 22% faster. Because the baseline doesn't reason about the severity of a ditch depending on the vehicle's state, it traverses all ditches with equal caution, which is an overly conservative strategy that results in a significantly slower course time. Physics-based method, on the other hand, is able to adjust its speeds to these ditches depending on their physical severity, resulting in a much faster overall course time. Finally, I want to make sure to acknowledge and thank everyone else who has helped develop other aspects of this very complicated system so that this work was made possible. And of course, thank you all for listening.
Questions from the audience? We'll have one in the very back on the right side. On the right side at the very back. Right side, very back, where the exit sign is.
Thanks for a great talk. For a given configuration of your system, are you able to predict the likely catastrophic failure rate over thousands or millions of hours of eventual operation?
Thanks for the question. It's kind of hard to say. I think especially in the off-road environment, we don't, unless you provide kind of a minimum or a maximum kind of risk or maybe slope or terrain type, it's hard to say what we'll exactly encounter, and that plays a pretty big role in the actual failure of our vehicle. I would say in the many, many miles that we have driven so far, we're pretty robust to failures. Yeah.
Thank you. Any other questions? We have one at the front.
Thank you. Yeah, really cool talk. Maybe a naive question, but how does your system perceive the difference between things like a clump of grass that you can safely drive through versus, you know, some grass around a tree stump that would spoil your day?
Yeah. So perception is definitely like another subsystem that I didn't have time to delve into today. Of course, you can come talk to me about it, but we are, at least as far as the control algorithm is aware, it has semantic information. So downstream from the reception module, control algorithm is told this is grass, this is dirt. There's an associated cost, and we can tune that a little bit, but that's as far as the control algorithm is aware.
Right, thank you. Please visit the poster session for more questions. Right, let's thank the speaker again.
All right, next speaker, Arun, is going to present demonstrating Crop Follow++, robust under canopy navigation with key points.
Hi everyone, I'm Arun from the University of Illinois, and I'm presenting our work Crop Follow++, which is a demonstration of a robust under canopy navigation system with key points. So under canopy robots are small compact robots that traverse the tight space between crop rows below the plant canopy. They can enable various applications like crop monitoring with these tiny robots. They can enable precise spraying, weeding, cover crop planting, which you can see on the left side with the bigger platform, which is not possible with over-the-canopy machinery like tractors when the crops are tall. Navigation in under canopy settings is challenging due to the unreliability of GPS. We don't have good RTK GPS signal below the plant canopy. The LiDAR scans are noisier because of significant occlusion and clutter. And also from a camera perspective, there is large variability in the appearance of soil, crops, lighting. And also there is very little margin for error due to the tight spacing. To address these challenges, we present Crop Follow++, which is a modular, interpretable, and anomaly-aware system using semantic key points. We deploy the system over 25 kilometers on multiple under canopy cover crop planting robots. And in this work, we discussed the various failure modes that we observed during this deployment. Giving an overview of Crop Follow++, First, for perception, we trained a convolutional neural network that takes as input a monocular RGB image, and it predicts 3 key points. These key points represent the vertices of the triangle formed by the 2 vanishing lines on the bottom of the image. We predict these 3 key points as heat maps, as a unimodal distribution. So the spread of these heat maps also provides information that enables to detect occlusions as anomalies. And these heat maps are then passed through a spatial argmax layer, which gives these 3 points indicating the peaks. This information then combined with the camera intrinsics and the roll from the IMU is used to estimate the 2 states that is relevant, which is the angle of the robot and the distance perpendicular to the crop probe. These 2 states are then used to define the reference path, which is the middle of the lane, and we use a model predictive controller to control the linear and angular velocity of the robot that keeps the robot in the middle of the lane. First, we evaluated the system by comparing with a prior baseline. The baseline method used a direct end-to-end system for perception by directly predicting the heading and distance ratio. So we evaluated on the entire data set, which was labeled, as well as a subset with challenging scenarios such as large variations in viewpoints, as well as variations in terrain. And in terms of L1 error in the heading as well as distance ratio, we can see that the key point representation in CropFollow++ has significantly lesser error than the direct approach in CropFollow. We then compared the systems by field testing our proposed approach with the prior approach over like 2 kilometers. And in terms of 2 metrics, number of collisions as well as the maximum distance traveled in each run before collisions, you can see that CropFollow++ in total had like 13 interventions compared to 33 in the prior method. Also, like in each run, CropFollow++ was able to travel farther before having a collision, unlike the prior method, which is lesser. We then deployed the system on this bigger robot, which is a cover crop planting platform. Cover crops are seeds that are dispersed before like the main crop corn is harvested, and we do it over like longer distances, like 25 kilometers over 3 of these platforms. And when we do this deployment, we also have an autonomous crash detection recovery module. Whenever the robot crashes into the corn plants, by observing the difference between the applied velocity and the actual velocity of the robot, we know that the robot has crashed. And we switch to the rear camera, which helps in recovering the robot autonomously. So in summary, from these deployments over these 25 kilometers, we had about 109 collisions, but 76 of those were detected and recovered autonomously. So only 33 were like irrecoverable collisions that needed a human to intervene. And we had like the longest run without intervention, about like 3.5 kilometers. And in this pie chart, we show the various failure modes that we observed in this. The major one being this corn gap, which is like there is this long gaps in the crop rows, which affects perception, and this is due to like errors in planting. We also have problems due to like errors in the model prediction itself, which happens when the robot is like drifted to one side of the crop row, and there are also some other edge cases that we see here. And here there is a visualization of failure due to the gaps in the corn row at the top, and in the bottom we see that the robot failing due to significant occlusion due to weeds present in the field. So in summary, we have demonstrated a robust under-canopy navigation system using semantic key points as the representation for perception, and we deployed it over a large distance here. I'm happy to take any more questions.
Question in the front.
Hi, great work. Can you give examples of what a recoverable and irrecoverable failure looks like? You mentioned those.
Yeah, so everything in the pie chart was an irrecoverable failure, but within the irrecoverable, we can split it into 2 cases. One is like when the front as well as the rear camera both have like perception error. That is one case, which can be improved by like either further training or like self-supervised adaptation. But there are cases in which both are like blocked due to occlusion, which is like a case where unless you have an additional camera, you can't really do much about it. And there are also cases of physical failure due to like very harsh terrain, which is like a hardware limitation itself.
Thank you.
Another question in the front.
Hi, yeah, great presentation. For the question about, you talked about the failure of key points.
Do you think that's just a question of more data and more training, or do you think there's other components of it you think they won't just scale with more data?
Yeah, so we are looking at, you can always, of course, add more and more data, but as you go from one field to another, there's always going to be cases of domain shift, because in an agricultural field, there is across species of plants as well as like lighting, various sources of domain shifts, right? So we believe that there is definitely necessity for self-supervised adaptation of this key point module itself, and we're actively working on it now.
Thank you.
Question in the back center. Maybe you could get a toss from behind you.
Great talk. So most of the tractors that are used to maintain large fields are GPS guided. So why can't you use GPS here? Because it's very flat, there's no mountains, there's not much GPS blockage.
Yeah, but unlike the tractors, when you go under the plant canopy, even if you use a RTK receiver, there is multipath error through the plants, so you don't get the same precision that you get with tractor. So the tractor's GPS gives you accuracy up to like 2 centimeters in GPS, whereas here, below the plant canopy, it degrades to like half a meter or a meter, which is more than the distance, the gap itself that you have.
Thanks.
All right, let's thank our speaker again.
And our last talk of the session is from Fadil Ginting. He will be talking about SEEK, which is semantic reasoning for object-goal navigation and real-world inspection tasks.
Thank you. Hi, everyone. I'm Fadil, PhD candidate at Stanford. I'm presenting our work, which is a collaboration between Stanford Intelligent Systems Lab and Field AI, a robotic startup that focuses on enabling embedded AI for field robotics. So we are interested in enabling autonomous inspection in real-world unstructured environments. In addition to map the environment, we usually interested to ask the robot to search and inspect closely specific objects based on the human request. However, doing this object inspection is very challenging. The first one, like in the field, the environment is large and a large search space. And then robots usually don't leverage the prior information and also like common sense knowledge that humans usually use for this task. And then lastly is challenge in searching and detecting these objects due to the perceptual uncertainty from occlusion, detection, and localization error. So current practice in object inspection usually rely on predefined routes or placing like identifiable tags next to the object. And recent work in the literature use semantic reasoning to guide the object search using VLM and large language model. And with respect to the related work, in this work, we focus on leveraging more the prior information that usually available in the specific industrial applications and combine it with semantic reasoning. And with that, we can formulate a new probabilistic planning approach for object goal navigation. And we plan to design this to be deployed fully on edge and run in real time. So in this work, we present SEEK, semantic reasoning for object inspection tasks, that pushes the current practice of real-world object inspection. In this talk, I will focus on the 3 key components of the approach. And the first one is the dynamic scene graph generation. So dynamic scene graph is like a hierarchical representations for the spatial abstraction of the environments. In this approach, we built this offline using the available information such as floor plans that is commonly available in industrial inspection or building information model. And we can use this for semantic reasoning and doing hierarchical planning. And the second part is relational semantic network, or we call it RSN. And the model here is to predict the probability of finding the target object on every room that is available in the dynamic scene graph. For example, if you want to find a sink, it has higher probability in bathroom, kitchen, compared to other rooms. And we train this network using data generated from large language model, because in the field, we have like limited compute and rarely have reliable internet access. And the last one is the semantic guided global planner. So given the SG representation and the prediction, we can formulate the planning problem as the Markov decision process. Here, the action space is we ask the robot to either to go to a room or like search a room or like area locally. And we do the planning on every global planning step. So we perform extensive simulation in the habitat sim, like a common benchmark for this, and also a gazebo and hardware experiment with Spot. Key takeaway from the simulation is our approach outperform like planner with pure query from LLMs with GPT-4 and also baseline approaches, highlighting the benefit of combining semantic reasoning and probabilistic planning. And we validate our approach also on hardware. Here in the office, we ask the robot to search and inspect a fire extinguisher. So the robot knows like, oh, it's usually located either at the entrance or at the kitchen, and it goes to that area first before performing local search. And this all computation happens on the robots, and it saves more time instead of like let the robot explore and until find it. So the key takeaway of our work is first, prior spatial configuration and relational semantic knowledge can guide the robot for object-goal navigation. And this enables a more efficient object search policy, and we design SIG to be deployed on edge and run in real time for real-world inspection. Some latest updates on our work, we actively develop this and make it more robust for field deployment. And particularly, we're interested in enabling this capability for our ongoing effort in deployment in the oil and gas processing facility. For more information, please check out our website. Thank you so much for your attention. Happy to discuss more if you have any questions.
Thank you. Questions? We have one in this corner.
Thank you for a great talk. I was wondering, so when you're deploying the field, there may be lack of visual silence or some confusion that you cannot find the exact location according to a BIM. Are you observing any emergent behavior from for example, foundation models that actively reduce uncertainty regarding its location, or do you have any strategies to resolve these issues when you're not sure which office exactly you're in or something like that?
Yeah, thank you for the questions. So the question was whether in the case of the model that we have is not able to search for the object correctly, what's gonna happen? So currently what we have is we just use LLM for just semantic reasoning and give a prediction of where the location is gonna be. And one thing that I realized, I came back from the field, is it's hard to detect this kind of object that our collaborator from the oil and gas is interested to look for. And one strategy is we need to gather more data first and then leverage the relationship between if I want to find to object A, it's usually close to object B or a certain part of the components. So that's one way to solve for that, in addition to just leverage the hierarchical representations, but also the relationship between objects. Thank you.
Thank you. Any other questions? I actually have a question, if there are no other questions. Very quickly. If the goal has been found, let's say the object of interest that you were interested has been found, do you actually need to use your model still to navigate to that object, or you can simply use any of the classical methods to go to the goal?
Yes, thank you for the questions. So the question is, once we detect the objects, do we use an learning-based model or a classical approach? So currently we just use classical approach because it works directly when it detects the objects. But I see that learning-based approach for navigations will be also useful, particularly when we want to approach the object that is a bit hard to get and it's not trivial to just go to point directly.
Thank you. We don't have time for other questions. Thanks a lot. Thanks to the speaker again. And this concludes the field robotics session. Thanks, everyone. Thanks to our speakers. And we'll move to the plenary.
I won't introduce until everything is ready. Yeah. Good afternoon, everyone, and welcome to our first plenary session. I'm very excited to introduce Professor Uta Noppany as our first plenary speaker. Professor Noppany is a professor of systems neuroscience at the Neurophysics Department and a principal investigator at the Donders Centers for Cognitive Neuroimaging and Neuroscience within the Donders Institute for Brain, Cognition, and Behavior. Before that, she was a professor and director of the Computational Neuroscience and Cognitive Robotics Center at the University of Birmingham, and independent research group leader at the Max Planck Institute for Biological Cybernetics. Her research investigates the computational and neural mechanisms of perceptual inference, learning, and attention in dynamic multisensory environments. She uses a multidisciplinary approach integrating psychophysics, computational modeling, and advanced neuroimaging techniques. She has received the Young Investigator Award of the Cognitive Neuroscience Society in 2013, a Turing Fellowship in 2018, an ERC Starting Grant in 2013, and an ERC Advanced Grant in 2023. So when I learned about Uta's work, particularly analyzing how our human brains perceive the world and integrate multisensory information in dynamic environments, I thought, wow, this is exactly the kind of problems that we are all thinking about within robotics, thinking about how we can make our robots' perception be more accurate and robust. So it would be super interesting to learn more about how this is done in the human brain and whether we can use any of those insights for our robotics design, as well to figure out if these insights about human perception can help us design systems for better human-robot interaction. So I'm super excited to welcome Uta. Please join me in welcoming Uta to RSS.
Well, thank you very much for the kind invitation. I'm really very much looking forward to this conference and immersing myself in the robotic community. As you have heard, I'm an odd one out here. And in this way, I'm really curious to learn a lot from you. So my naive perspective is right now we see all these sort of great strides in artificial intelligence, right, that basically the large language models constructing music or art or everything that I really enjoy. But then when I'm looking at my dishwasher, it still doesn't get emptied, right? And then from my psychological perspective, I always think, well, if I were a little robot, I would also pretend to be really clumsy at all these things that I don't enjoy. So I'm trying to find out whether this is really the correct perspective for robots, right? But I do think, as was already pointed out, we do have a common ground because both humans, as well as artificial agents like robots, they have to face comparable computational challenges when navigating our complex, dynamic, and sensory-rich world. So imagine this waiter at a busy restaurant, right? We basically, his senses are overwhelmed with numerous sensory signals, talking people, clinking glasses, the smell of delicious food, right? And amidst this sensory bombardment, this waiter has to pinpoint to the guest that is signaling for attention, perhaps based on with some sort of raised hand, perhaps with some shout from across the room. And so I'm focusing in my research on these sort of perceptual aspects that are basically challenging. So exploring how does the human brain, how do human observers construct representation of the world, make sense of the senses, how do they integrate sensory signals into coherent and more robust perception of the world. And as was always pointed out, human perception is remarkably robust, even in these very complex, sensory-rich environments in which robots still often struggle. So, so in this way, I hope that perhaps there might be some interesting things to find out because understanding human perceptual mechanisms may in this way perhaps provide like valuable insights about how to make robots more robust or how to sort of make the sort of robot-human interaction a little bit more versatile. And I'm sure all of you are familiar with mass levels of analysis. Let's quickly revisit. There's first of all the computational level, right? What does a biological or artificial system aim to achieve? What are the underlying computational principles? Then we move to the algorithms, representations. What are these processes? And finally, we focus on the implementational level. How are they really physically realized? Now, in this talk, I'll focus predominantly on the computational level, because this is also a ground that is shared between us, right? And only briefly, I sort of make like a quick hint to the implementational level where we use human neuroimaging to investigate how these representations might be physically realized, at least at the neurosystems level. So my research is really guided by normative frameworks of Bayesian inference. And I'm sure all of you are familiar with this. So the idea is you have a generative model that maps from some true world state to some noisy sensory inputs via the likelihood. And then the basic idea is that during perceptual inference, the brain or human observer needs to invert this generative model in order to map from the sensory input by combining the likelihood with the prior to compute a posterior distribution, which is sort of like then framed all by the recognition model. And from this posterior distribution, because usually we don't ask human participants to say, tell us your posterior distribution, which might be very, very challenging. That's actually a question that we ask in metacognition. To what extent can we access these posterior distributions? But we ask them to basically read out from the posterior, like make a single decisional choice. And so these sort of like Bayesian inference frameworks, they are really important for us because they set a benchmark for base optimal human behavior, against which we can then compare the human actual behavior. And we can ask, are humans really optimal? So Bayesian inference really tells us what the human brain should be doing in order to be optimal. And why is that a useful departure point? Well, it's a useful departure point because we've been around for so many thousands of years, and so we've been optimized based on evolution, and we've managed to survive. So we would expect that at least for very simple perceptual inference things, we might be relatively optimal. But often we are not, because the life and the world is really complex, and then we can use base optimal behavior as a departure point and ask, like, what sort of approximations and heuristics do human brain use, basically. So, and predominantly in this talk, I'll focus on the visual and the auditory sense. So I'm sure you're aware, right? The visual sense and the auditory sense, they're quite complementary. The visual sense offers high spatial resolution, at least in the fovea. It provides information about shape, size, color, but it is limited when there are occlusions. We've just heard this in the previous talk. Or it cannot inform us about sources that are outside our field of view or behind us. And it's got a very, very limited temporal resolution. By contrast, the auditory sense impresses with its high temporal resolution, and it can also inform us about sources that are behind us or in darkness, but it's got a very limited spatial resolution. So in this way, collaborative interactions across the senses are very important because they can basically provide sort of like complementary information and thereby resolve humans' perceptual ambiguities. So we can basically perceive a cup from the front, but we can explore it from the back. But in addition, it is also important, even if the information is redundant, to combine and integrate this information because it reduces redundancy. And actually, so far, our work has been mostly focused on the second aspect. So what happens when we have redundant information across the senses? How does the brain basically combine those? And so now you could argue, well, if we combine redundant information, we should observe a more precise percept, and that is correct. But it doesn't necessarily mean that the percept is actually veridical, truthfully representing the world. And there are lots of very famous illusions. And probably most of you right now are actually experiencing an illusion. Because I don't know exactly where the loudspeakers are, but they are probably not exactly here. And nevertheless, you think that the sound comes from here very often. At least in most movies, you actually basically think that these speakers are basically talking from the screen to you. And that is a so-called spatial ventriloquist illusion. So it comes from Latin, right? Venta means the tummy, the stomach. Loqui means like speaking. So the tummy speaks. And so why does it happen like this? Because this is like what you might have experienced like in the 1960s at a fun fair, right? Where you have basically a puppeteer and a puppet. And the puppeteer basically makes sounds and speaks without making any mouth movements. And the puppet basically makes mouth movements in synchrony with the speech. And hence, we basically provide the brain with audiovisual synchrony cues, saying like, look, these two signals come from a common source. But at the same time, there's a spatial conflict. And because sound has got a much lower spatial resolution, human observers mislocate the sound towards the visual location. And in fact, I've been training the whole night on this sort of ventriloquism for dummies to stage this year. And I've really worked myself through all the chapters, 1 to number 20, and learned how to speak without making any mouth movements. So instead of papa, you say nonna. But then I reached the final page. And the final page, the final chapter says, everything we've learned until now are just preliminaries. What really makes out a great ventriloquist is you need to get the punchline right. And then I got a bit worried and said, okay, let's better move on to the next illusion. And the next illusion is a rubber hand. And that might actually be much more important for roboticists, or much more exciting probably, because we have already like the touch and the rubber hand and so on. So how does that work? So I've brought like a quick movie with me. Basically, you place the arm of the observer out of sight its field of view, so it's occluded, and then you place a rubber hand in front of the observer. So the observer can basically only see the rubber hand. And then the experimenter basically strokes the rubber hand and the real hand in synchrony. And thereby, you generate like proprioceptive conflict and a body ownership illusion. So basically, the person believes that this rubber hand is his own hand. And what often happens then, if you really want to make like a cheeky performance in front of an audience, we then take a hammer and hit it on the rubber hand, right? And the person really screams. So, and you can really realize there's like a heart rate increase and everything. So illusions can be really, really strong, and they even happen when you are aware of it, right? So you know this illusion, but it doesn't go away. And what I hope to show in this talk is that these illusions, they arise in the same way as veridical perception from fundamental Bayesian principles. So, in this talk, we'll focus first on 3 sections, and we make basically our scenes progressively more rich. So we start with the integration of signals when the observer knows they come from a common source. Then we make the setting a little bit more complex, that there's some causal uncertainties, so there might be like signals coming from one or from separate sources. And finally, we basically make it really complex. There are multiple sources and multiple signals, and so it becomes computationally intractable for the human observer to solve this task. And then we argue there might be attentional mechanisms in play. So the first very simple situation, there is basically one single source out there in the world, and it generates an auditory signal and a visual signal. So then the observer should integrate, right? Now, as you know, we can basically frame this in the graphical model. You have like one underlying source, an audiovisual source that generates an auditory noisy auditory signal and a noisy visual signal. According to Bayesian probability theory, you should then, in order to optimize your performance, weight the auditory and the visual signal integrate them weighted by their relative reliabilities along with some prior knowledge. Now that's a very simple model for you, but for us it was important to check, do actually human observers have an access to their own uncertainty, to their sensory uncertainty? That's actually still not clear and still debated, but this, I think, is one of the key examples to demonstrate that yes, they have. So what are the key predictions that we should test in human observers? Well, first of all, we should observe a variance reduction, right? The variance of the audiovisual percept should be smaller than the variance of each unisensory percept. Now, you might see that I dropped out the prior. This is not because we now say, oh, we just do maximum likelihood estimation. This is because we have an experimental trick to present our stimuli such that the prior falls out of the equation. And the next thing is that observers should integrate the two signals weighted by their reliabilities. Now, in order to assess this, we need to generate a Q conflict, like in the ventriloquist paradigm, because otherwise, if the auditory and the visual are exactly at the same location, there's no way you can determine the weights. How do we go about this? Well, we present like a two-interval forced choice paradigm. For us, this is like a standard paradigm that everyone uses in deep psychophysics, but let's go through this. So you present first a standard, which is basically in the center of the screen. And then afterwards, you present like a probe stimulus. And this probe stimulus is sampled from different locations along the azimuth, so along the horizontal line. And then we have like auditory conditions, so both standard and probe are auditory. They can be visual or they can be audiovisual. And when they are audiovisual, we also have the trick that sometimes this audiovisual signal is congruent and sometimes there's a non-noticeable conflict. And on each trial, observers just have to do a very dummy decision. They just have to say, is the probe left or right of the standard? That really takes ages. We go like for 6 hours, we put people there. And people always, like colleagues always ask me, is this ethically valid? Are you allowed to do this? But I think these are adults. I think we are allowed to do this. Okay, so what do we do then? So we have basically on the x-axis, we manipulate the probe location, right? So it's minus 10 degree up to plus 10 degree. And so now it's very important. Now on a particular trial, even though the true probe location is at minus 10 degree, there's still some sensory noise, right? And that's why we have a Gaussian on top of it. That's sensory uncertainty. Now the problem is that we don't know which is the particular sensory signal that observers make their inference about. This is unknown to us. This is so-called experimental's uncertainty. So we can only say something on average, it should be in the middle, but we don't know on a particular trial because there's internal noise in the brain and there's external noise. And so across trials, basically we repeat these stimuli over and over and over again, and on each trial participants say, was the probe left or right of the standard? And as you can see, when the probe is very much to the left, observers say always left, and when it's very much to the right, they always say with 100% accuracy, it's on the right. But then you have like basically a cumulative Gaussian from left to right. Now what is important is this cumulative Gaussian, which we call like a psychometric function, is directly related to those probability distributions. So if there's less sensory noise, if there is a participant that has less sensory noise in his neural system, then this cumulative Gaussian, you can immediately see, right? If you shift this Gaussian now across, you will get like a steeper slope. And that's brilliant, right? Because now we can estimate from these psychometric functions 2 parameters. First of all, the variance, which basically is directly reflected in the slope. And this is basically like an estimate of the sensory uncertainty. And the point of subjective equality, which is this point, which is basically reflected here, the mean. Now, how do we do now test our predictions? Well, first look at the variance reduction. Well, for this it's very easy. We do our cumulative Gaussian, right, for the visual-only condition, for the auditory-only condition. For both, we get our variance out. We plug our variance into this equation. And that's not brilliant because we don't have now we have a parameter-free prediction. We now just go for our audiovisual condition and check, can we predict the variance that participants have in their audiovisual condition? So first of all, we should also notice we should have these 2 variants, they should be equated, right? Because then we get the best variance reduction. So that's what David did really like in a very fizzy way. It's very fiddly to get this done. But anyhow, it's nicely overlapping the auditory and the visual. They have more or less equal variance. And now the prediction is you get like variance reduction. And look at that, isn't that beautiful? Human observers show the variance reduction that is predicted by maximum likelihood estimation or by Bayesian integration. So that's the first prediction. And that demonstrates that human observers need to have access to their sensory uncertainty. Because otherwise, because we change the variance from trial to trial, you need to have an instantaneous estimate for this, otherwise it wouldn't work. And that's for us as neuroscientists really a fundamental way, because it means that the brain needs to somehow compute the uncertainty, need to have access to this. There need to be a representation of that. The next prediction was the precision-weighted integration. Now that's a bit more tricky, and that's where we need to have the ventriloquist illusion, the conflict trials. So we have basically the auditory trial we present, the visual trial we present here, and the auditory signal, not the trial, the visual signal comes from here, the auditory signal from here, and because they have equal variance, you should observe the audiovisual estimate of participants of the conflict trial should be exactly in the middle. And that means whether we present the auditory left of the visual, or the visual left of the auditory, or the congruent, they should all be perceptual metameres, which means participants should not be able to tell apart these stimuli, right? That's quite impressive. So you have the auditory left, the visual right, or the visual left and the auditory right, and you perceive exactly the same thing. And that's what the maximum likelihood estimation shows, but observers actually show a little bit of underestimation. So they basically assign slightly less auditory weight, or less weight to the auditory signal, which is typically less spatial reliable. And that is actually not only the case in humans, it's also the case in monkeys. So when you have visual vestibular integration in monkeys, they also assign slightly less weight to the signal that typically is less reliable for a particular context. And that already suggests that perhaps humans do have some sort of prior that influences how they weight the signals. Nevertheless, overall, I think these experiments have demonstrated that, yes, humans integrate audiovisual signals weighted by their precisions near optimally into more reliable estimates, though they underweight a little bit the auditory signal. But we were wondering, often the sensory uncertainty, right, that changes quite slowly. So do observers really just instantaneously estimate the sensory uncertainty, or might they perhaps also adapt across time? And for this, basically, we presented this experiment where we presented, again, audiovisual signals with a small spatial offset, but now we manipulated the variance across time. And so this is basically what it looks like and sounds like. I hope it works. Oh, there's no sound. Could people turn on the sound? It worked before. Hello? Okay. I'm not sure why is there someone listening? Hello? I don't know. Okay, let's maybe continue. Could we turn on the sound? Because it's audiovisual integration, so it would be ideal. No, it still doesn't work. I don't know why not. Okay, anyhow, then we need to continue. Do you know what I need to do? Yeah? It worked before we tried. No? Let's maybe continue. Anyhow, so what you should hear is whenever there's this sort of red, whenever it turns red, then there should be like some horrible noise, right? Which is basically a white noise, so maybe you actually prefer not to hear it. Anyway, it's like shh, shh, and that's basically coming from different locations. And you always need to locate the sound. Why do we make such a horrible sound? Because white noise is most easily localizable, because you have all frequencies, right? But it's not very, not very nice to listen to. So, and what is also important, as you can see here, these Gaussian clouds, they become bigger and smaller, right? First they're very small. Oh, wow. Okay. 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 I'm sorry, I didn't do that deliberately. I'm not sure I have ethical approval for that, actually. Anyhow, let's move on. So as you have heard, so as you have seen, these Gaussian clouds, in this experiment, we made them, modulated them across time according to a sine wave. It was going on and off, right? The variance becomes bigger and smaller and bigger and smaller. But we had many different sequences. And so now we basically cut it apart, right? And so the idea is that if observers instantaneously estimate the uncertainty, then basically when you go up and when you go down, it should be identical. So if you flip this side to the left, it should be identical, like an instantaneous learner. But look what human observers do. They don't have it identical, right? When it's going up, so the sensory uncertainty increases, then it's actually underestimated. And when it decreases, then it's overestimated. So is that maybe a Bayesian learner? So for this, we constructed a Bayesian learner where basically now observers infer their uncertainty as a hidden variable that depends also on the past. And indeed, that can nicely fit our behavioral data. It's like a Bayesian learner. But does that mean that humans really make a Bayesian learner? So that's where human cognitive neuroscientists are always very obsessed with this question. Is it really Bayesian, or is it just some approximation, like something simple? And indeed, if you do like a simple exponential learner that weights the uncertainty estimates from previous milliseconds, then you get like very similar predictions. And we've tried many different sequences to dissociate between those, but for all sequences that we tried, also for jump sequences, etc., we were not able to distinguish between those two. Okay, so that was basically sensory uncertainty is learned across time. Now let's make it a little bit more difficult. Introduce causal uncertainty, uncertainty about the model of the world, right? But now we have a very simple model. We can either have auditory and visual signals come from one source, or there might be like a separate sound source. So these are the two percepts that the brain should have, right? Either you basically perceive one person and you hear another one, or you basically see and hear the same person. So we basically have our simple forced fusion model, but now we need to have a second model, which is that there are two separate sources out there in the world. Now, the fundamental so-called binding problem or causal inference problem is that human observers do not know which of those two models are the correct models of the world. Instead, they need to infer this from noisy sensory signals themselves, such as them happening at the same time, at the same space, being temporally coherent, being semantically congruent. And from those, you then compute a posterior probability that the forced fusion or the full segregation model are the correct models of the world. And finally, in order to account for human observers' causal uncertainty or model uncertainty, you should then compute something like, for instance, model averaging, where you basically take the forced fusion estimate plus the full segregation auditory estimate, and you weight them, average them, weighted by the posterior probability that the forced fusion or the full segregation model are the correct models of the world. Now, the predictions of this, in a very simple thought experiment, if the sound always comes at 0, then they should, and the visual at multiple levels of audiovisual spatial disparity, then if observers were able to point always to the sound, irrespective of the visual signal, they should always point to 0. If they have something like visual capture, they should point along the identity line. Forced fusion would still be a linear equation, right, down here, but mostly biased towards vision, because vision is more reliable. But what is exciting is what happens here with the model averaging, or the Bayesian causal inference. Because then, when the audiovisual spatial disparity is small, you basically integrate audiovisual signals weighted by their relative precisions, but then the greater audiovisual spatial disparity, this model becomes progressively more likely, and hence audiovisual integration turns into audiovisual segregation. So that basically nicely transitions between integration and segregation. And that's exactly what we observed. So that means that indeed, even though human observers are instructed to just report where the sound is, again, you get illusions. You don't point where the sound is, but you go with the visual signal, but you do it, and you can also compute. Now we actually have like here already like more complex. It's not a simple Gaussian, but now it's a mixture of Gaussians. So humans are even able to do that, which is quite impressive again. So now comes the sort of small interlude where we go beyond just like behavior and computation, but we now say, well, this is a model which makes conceptually sense, right? It also predicts human behavior, but does the brain really represent these internal variables, like the audiovisual forced fusion, the full segregation auditory, or full segregation visual? And for this, we basically use something which is called functional magnetic resonance imaging, or EEG. So functional magnetic resonance imaging, maybe you've been already lying into such a machine, right? You're basically moved into the scanner, and then you have to perform different tasks. And whilst you're doing these tasks, we record basically the blood oxygen level dependent contrast in your brain. How much oxygen do you have in different areas? And that tells us whether certain areas are active. And that has got quite a low temporal resolution, not only because of the machine, but also because it's a hemodynamic method. So it's based on blood, right? And that's basically slow in the brain. But then we have like another method which is called electroencephalography, and here we can directly measure the neural signals at the electric level. So that's where we have like low spatial resolution, because we measure it only on the scalp, and so we have like an inverse problem to infer from the scalp back into where the sources are, but we have a high temporal resolution in the millisecond range. And so that's why we combine these two methods. And so we basically put participants into the scanner, and we then present them with auditory sounds and visual flashes, independently sampled from 4 different locations. So along the diagonal, you have the congruent trials, and the more you go off diagonal, the greater the audiovisual spatial disparity. And observers either have to report the sound location, or they have to report the visual location. And then we asked whether, and if yes, where and when, are these different variables from the Bayesian model represented in the brain. And for this, we use something like, it's called multivariate pattern analysis. Basically, it's a support vector regression model. We train a support vector regression model based on these activation patterns, right? So we extract activation patterns, and then we train it to decode the particular locations from these different internal variables. So this model is basically fitted to participants' behavior. That gives us for every single trial these variables, and then we ask where in the brain are these variables encoded. And what is, first of all, reassuring is that in visual areas, that's sort of at the back of your brain, right? That's basically here. You basically encode the visual location. And in the auditory areas, which is above your ears, you encode the auditory location. But what is exciting is what happens in these association areas, because in posterior, sort of more earlier association areas, you do something like forced fusion. And in anterior areas, just on the top of the hierarchy, so at the very, very end, you do something like Bayesian causal inference. And what is even more intriguing is that this cortical hierarchical organization is also reflected in the time, in the dynamics, right? Initially, there's a segregation, then the brain does something like fusion, and then it does something like Bayesian causal inference. So to summarize, basically, first we have full segregation in these sort of early sensory cortices, then we have fusion, and then we have Bayesian causal inference. Now that's quite intriguing, but also a bit puzzling, right? Because for sure, if the brain fuses the signal and loses these segregation estimates, there's no way you can compute the Bayesian causal inference estimates anymore, right? Once it's fused, everything is gone. So it needs to also maintain those ones. And the other thing which we also found quite interesting is like our Bayesian causal inference model so far just makes predictions for accuracy, right? But in the real world, the brain doesn't need to be only accurate, it also needs to be timely. When you cross the street, you can't have like 500 milliseconds to make a decision whether a truck is coming over or not. So when we basically ask participants to locate the sound source really, really speedily, and then we basically categorize those choices according to their speed, then we can see when they report very speedily, they actually have lots of cross-modal biases. They are much closer to the visual signal than when they are really, really slow. So that means we need to move beyond this very simple static Bayesian model. We need to have a dynamic model which basically takes into account that human observers not only need to be accurate, but they also need to be fast. And for this, basically, we extended our Bayesian causal inference model into a dynamic Bayesian causal inference model, where across time, basically, the brain samples auditory signals and it samples visual signals. And then it recursively needs to update its posterior distribution over both, over the spatial estimates as well as over the causal structure of the world. And that leads to complex nonlinearities and interactions. And it does so like, well, you know this, right? You basically always have the posterior of the previous time step becomes the prior for the next. So why is that exciting to do this? Well, because it can give us an explanation. Because at the very beginning, so that's now here across time, and this is just like a simulated trial where you have like the noisy visual signal samples coming in and the noisy auditory samples coming in. And so at the very beginning, there's an enormous amount of spatial uncertainty, right, about where the auditory signal is and the visual signal is. And as a result, the causal posterior is still biased towards common source, even though the two sources are actually separate. But then the more evidence you accumulate, the more narrower these distributions become. And so the causal posterior progressively is biased towards full segregation. And hence you can see this sort of model averaging posterior, initially all the probability mass, or most of the probability mass, is where the forced fusion is. So you get basically, this is the map readout, right? Initially it goes via the visual signal, but at some point it basically realizes, well, at some point basically the bump is stronger on the full segregation, and hence the readout basically shifts towards the sound. And that's sort of the nice and beauty thing about Bayesian models. Bayesian models still have very few parameters, and thereby they allow us to provide like explanations into why human observers show certain behavioral profiles. And that's sort of like the main reason for using Bayesian models. And we also ask, like, well, how do observers actually make decisions, right? Do they make a decision here? Do they wait for longer? And there we had like a couple of heuristic decision criteria. So one is, for instance, the entropy over the entire posterior distribution. Another is the change in entropy, so whether it becomes like, whether there's a reduction in entropy, or the map, or the difference in the map, right? And so when we do this, the best strategy was actually the one based on entropy. So when the entropy does not change much more anymore, that's when human observers say, okay, now I make a response. So that suggests that basically, human observers need to solve the binding problem for simple scenes when there's like some sort of like uncertainty about whether auditory and visual signals come from one or from separate sources. And we've demonstrated that the brain really arbitrates between sensory integration and segregation by accumulating evidence about the spatial estimates and the causal structure. And this basically, which is really beautiful, explains that initially here, when the model averaging posterior is still like focused mostly on the sort of like on the bump of the forced fusion estimate, because there's still some sort of spatial overlap between the auditory estimate and the visual estimate. Initially, observers seem to integrate like forced fusion, and later on, they seem to segregate like model averaging, right? But in effect, they constantly do something like Bayesian causal inference, right? And what we now try to do is, so if you go back now, we try to basically in this sort of like, in our model, using now MEG, which has got like a little bit more magnetoencephalography, which allows us not only to look at the sky, but do like better source reconstruction to assess how these different estimates in the cortical hierarchy basically get updated successively. So whether perhaps in the long term, these sort of like auditory and visual areas also get updated, and because in the end of the day, we don't believe in a sort of simple feed-forward architecture in the brain, but we also we know that the brain has enormous amount of top-down modulation. So the question is really like, how do these top-down effects influence and update these estimates across time? So now the final part of the talk is sort of not yet done, so I don't have a model yet, but at least I'll show you where we want to get at. Basically, approximate inference in complex scenes. So we've started with this model of this poor waiter with all these different sources in the world. And so what is the recognition model for such a complex, sensory-rich, and multi-source environments? Well, basically, there's a combinatorial explosion, right? You don't know which signals come from which sources, right? Which signals should be bound. I mean, anything can be possible. And there's no way that the brain can compute this in the face of sort of resource constraints. So what does the brain do? And that's where we now move on from the sort of normative Bayesian perspective, where we say, okay, we define what is the Bayes optimality, and we demonstrate that the brain can do optimal performance, but now we need to ask, what sort of approximations does the brain do? And one idea that we have, and that we currently pursue, that is the idea of an attentional spotlight, of attentional mechanisms. So the idea is that basically the brain, given that the brain cannot compute the source analysis or the sort of audiovisual binding problem, cannot solve it for the entire scene at once, it might sequentially select subsets of signals and assess them for binding, and then basically scan around more or less, right, with this sort of attentional spotlight. Now, what has brought up this idea is something very, very old work from Anne Treisman from the 1990s and 1980s on visual search. So if you look to the left and you need to identify the only line segment that is horizontally elongated, you can find this very easily on the left and very easily on the right. So there's actually no reaction time difference. So that's why scientists concluded, well, this is parallel feature search. So these features can be searched in parallel by the brain. There's no need to have any attention for that. But look to the right. Now again, you need to detect and locate the only green line segment that is horizontally elongated. Well, this is now really tricky, right? Because now we have green and red as one feature, and we have like horizontal and vertical as the other feature. And here you might see, okay, this is this one, but here you need to really scan through everywhere until you find it here. And that is indeed the thing that across set sizes, when you increase the set sizes, the reaction times will increase. And that's a clear indicator that attentional mechanisms are in place. So either you need to have, like, you shift covertly your attention across the screen, or you even make like active sensing and you make eye movements. So how can we do this now for audiovisual binding? Well, this is a bit more tricky because these sort of, actually until now, still visual search is predominantly always in static environments, right? Which is completely unnaturalistic. And as soon as you have like sounds, well, there's no static sound. Sounds evolves in time. So we need to move beyond these sort of very simple static searches towards dynamic searches and develop a dynamic search paradigm. So this is the way it works. So you have basically like these visual items along this sort of like a circle. And there's always on each search paradigm here, there's one single item that is either vertically or horizontally elongated. And this is the one that you need to detect. And these, across time, basically change their color. So that's the dynamics. And first, we have a purely visual dynamic search paradigm. So basically, you need to basically focus here on the fixation cross and try to detect the item that is elongated horizontally or vertical. Let's go. 1, 2, 3. Who has detected it? How many? A couple? Maybe 3 or 4? Okay. Now we have the next thing. Now we do it, oopsala. So now we basically make, we present like a beep in synchrony when the target changes, but only when the target changes, but not when the other distractors change. And now my tip is, don't try to look for the elongated target, but just for the target that changes in synchrony. So just detect the target that changes in synchrony. And again, fixating is important. It makes it easier. Okay, off we go. Oh, there's no sound. Can we turn on the sound again? Sorry? Which HDM cable? This one? No. This one? This one. Oh, replug. Oh, okay. Okay. Okay, let's try again. Do you have to do this always? Okay. So. Yeah, I try, but now it doesn't like it. I think now PowerPoint got. Oh no, there we go. Let's see. Let's start it again. Sorry. Okay. Hopefully this works now. So everyone needs to fixate and detect the target that changes in synchrony with the beep. No, there's no beep. Again, should I try? No. Why is not the beep happening? There's no beep. Maybe I should play the beep whenever it happens. I don't know why is that not coming? There's no beep. I don't know. What can I do? I don't know. But for the other one, it would be really nice because the other one I can't mimic. So maybe the video itself. Maybe with this. Let's do this. No, it doesn't play this. Okay, just the video. Okay, let's try the video. I've got the video somewhere. I don't think I have the beep only. Do I have that? Sorry? Yeah. Should I do the speakers real track? Is this one maybe? Okay, sorry about that. Yeah, this one. All right, everyone now again awake? So that's why I always put them in. So I thought like these roboticists, they should definitely wake up. Okay, there we go. All right, everyone fixating and the beep. Oh, what's this? Well, this is, okay, I don't think. Sorry? Oh, they're just like this. Okay, just like, okay. But it doesn't do anything either. It only works always once, or how does it work? But why did it work beforehand? I'm sorry, I really tried before, and everything worked. But, yeah. No, it doesn't. Yeah, it's a Windows problem, I've been told. Excellent.
Is the video silent under playback in PowerPoint, maybe?
What? A playback?
Yeah, it's up right in the toolbar.
Playback, and then? Volume, yeah. But it's fine.
It's correct.
It's correct. I think there's nothing.
Can we change it to the
Here?
speaker and just use a microphone?
Okay. Yeah. Or do you think it works if I only get the videos?
No, it's your system.
Okay.
Yeah, just change it to the speaker.
Where?
Yeah, the first speaker.
Okay. And now we do.
And they will hear it just a little bit not
Okay.
that loud.
Okay. Okay. So it's going to be more quiet apparently. Do people hear? Okay, cool. Okay, so I don't know whether you saw it, but usually when it's a little bit louder, not quite that you completely drop out, but it's then it should have like a pop-out effect basically. You should be able to detect and parallel search for a single visual item that basically does it in synchrony. And then what we have, and that's really sad that I can't show you this, because now comes the next paradigm, the next stimulus, where we have so-called stochastic figure ground sounds. And I really love them because they sound really psychedelic. And basically what we do is we have here these beeps, and on top of it, we have all these sort of additional sounds. And they're called stochastic figure ground sounds because you see these chords basically are formed from these other sounds in a stochastic phase. So they sound a little bit like, and so on. And so that's really, I mean, I can try whether it works. Maybe I try this again. Where is this here? And then, of course, it becomes much more difficult. And so just to summarize this paradigm, let me just go back into presentation mode. Oops. So basically, we have like first the visual set size effect, and the idea is, in a purely visual condition like here, then you should have longer reaction times. But when you have like a synchrony target detection task, and you just need to detect the synchronous target, then when you have a figure sound together with something that changes in dynamically, then you should basically have a pop-out effect. By contrast, when you locate basically a visual orientation target, then probably you might have, we don't know what happens then. I mean, visual alone, for sure, you get like an increase, but when you have it audiovisually, that's the question. And so first of all, that's indeed what we found. Like for the audiovisual synchrony detection, we actually got a pop-out. You can see that from the 6 set size or 12 items, it doesn't matter. So you're equally correct, and the reaction times are equally long. The only difference is that these reaction times are basically with a figure, so you're much faster when you have a figure sound, but when you have this sort of structure from stochastic figure ground stimuli, then you are becoming progressively more slow. And if you now have a visual orientation target, so rather than detecting something which is in synchrony, you have to detect something which is oriented, but it changes in synchrony still, then we actually observe something which seems to suggest like a mixture of two audiovisual strategies. Basically, you do get like a set size effect very strongly when it's visual alone, but when it's audiovisual together, then you see that the set size effect, the slope, the difference between set size 6 items and set size 12 items is actually reduced. And so that suggests that indeed, you can search in parallel for a visual target in parallel, but it's not that it's such like an automatic pop-out that if you have to do like another task, like a visual orientation task, that you then get such a pop-out. And so now let's come to the outlook. Where are we now? So this is like first a paradigm, and we now try to sort of model this in a way that we say we basically accumulate evidence. So we basically sequentially select signals and for sort of causal inference, and we then accumulate evidence about the causal structure in such an attentional spotlight. And at each time point, the human observer then needs to make a decision whether to stay on and accumulate more evidence or to switch to different locations or to stop altogether. And we formulate this as a sort of partially observable Markov decision process. And then we also want to sort of compare what happens when you do like attention mechanisms. So that means you fixate, but you just shift your attention relative to when you basically make active eye movements. And we can tell you that actually you are much better if you just shift your attention than if you make active eye movements. So attentional mechanisms are really fundamental for human observers to become really efficient and effective. And you might argue, well, we've been seeing always this picture, right? But I've never been shown you any experiments of this. And this is indeed where we are going to move on to now, and I think your field is certainly ahead of us, because I've already seen in your abstracts, you also have like hybridized neural networks with Bayesian models. So why do we want to do this? So we basically, in our sort of new grant proposals that we just, where we just started on, we now want to move really into the naturalistic real world. And of course, when we have naturalistic images, we can't have our simple Bayesian models anymore, because we need to have feature extraction, etc. But we would still like to have our Bayesian models because they really provide us with some explanation. So of course, we could have neural networks, and they could have comparable performance, but that wouldn't tell us much about what are the computational strategies. And that's why we want to hybridize the two, so that we basically get the best of both worlds, the explainability from our Bayesian models, and still being able to move beyond beeps and blobs and flashes towards naturalistic stimuli. And with this, I'd like to conclude. So first of all, in the first part, we've shown you that humans integrate auditory and visual signals weighted by their precisions. And this is very, very strong evidence that humans go beyond just simply mapping input to output according to some learned functions. They do have access to some sensory uncertainty. And this sensory uncertainty is partly instantaneously inferred, but is partly also learned slowly across time. Then in the second part, we've shown you that the brain also can solve causal inference problems. So it can move beyond just estimating some sensory parameters out there in the world, but really do some sort of causal structure inference or model inference. And there it can also compute quite nonlinear, show quite nonlinear functions, right? And arbitrate between integration and segregation, and do so also by dynamically accumulate evidence across time. And that's also very important, that we move beyond all these classical Bayesian models that are used in psychophysics, which are adynamic. We need to make models that are dynamic, because human observers do need to optimize not only the accuracy, but they also need to make timely responses when they cross the street. And finally, the final section that I'm most excited about, where we just move on to, is basically approximate inference in complex scenes. So how do humans basically compute solutions when it becomes computationally tractable to get like the full posterior, basically? And we've shown that salient sounds are very important. They can guide your visual target detection, and they can really speed up because they have some sort of parallel access. But in addition, we also need to have attentional mechanisms in the service of approximations to solve the audiovisual binding problem. And with this, I would like to thank you for your attention, and also the great PhD students and collaborators, in particular Tim Rohr, with whom we've started this actually in 2015, still like at the Max Planck Institute in Tübingen, and then Marty Aller, Agustin Mialik took on board like the sort of fMRI and EEG experiments, and then Jochen Bürske, now the sort of more dynamic Bayesian causal inference models, and Xin Wang on the sort of like complex causal structure. And also, like, in case any one of you might be interested not only in artificial agents, but also in human agents, then we are also looking for enthusiastic PhDs and postdocs. Thank you very much for your attention.
Thanks so much for that wonderful talk, and I would like to open it now to questions. I think we've got, yeah, maybe grab, yeah, please.
Test, 1, 2. Thanks very much for the talk. I vaguely remember an older experiment where they would play a sound from a certain direction and then observe the person's head movement as they try to sort of fixate the direction of the sound with their eyes. And then they would give the person a sort of a prismatic glasses and that would shift the visual field and see, you know, how initially they couldn't with the prismatic glasses turn their head exactly to where the sound was coming from. But they would quickly relearn that. So the visual field might have been shifted by 30 degrees or something, but they would pretty quickly adjust to that. How would that go into your Bayesian model? Or what's going on there? Is the brain relearning a likelihood function, recalibrating? Any
Yes.
ideas?
Exactly. So we do actually also have them. I mean, I have some work also on recalibration. It's basically audiovisual spatial recalibration. And that can be very fast. It can even be within 1 second. So, and that makes sense because if you move from one trial, and so I have some, I can show you. It's a different talk. So that's, I couldn't put it here. This is basically where we, exactly the causal inference in recalibration. So basically, when you move into another room, then of course your cues, your spatial cues are different. And then the causal inference problem becomes even more complicated, right? Usually the causal inference problem is either there is a discrepancy because of noise, so I should still integrate, or because they come from separate sources. But then it could also be because my cues need to be recalibrated. And initially it was thought that this sort of recalibration is quite long, it's quite slow, and it takes like at least like maybe 3 minutes or whatever. And if you do like nonlinear recalibrations, which has also been done by someone in our institute, John van Opstal, it takes even weeks until you get this, right? When you do like so you warp basically the space in a complex nonlinear fashion. So we didn't do this sort of nonlinear warping, but just this sort of small shifting forwards and backwards. And that's where indeed we can show that from within 2 seconds you basically recalibrate. And you do it also according to causal inference. So basically what we have shown here, we ask like participants, so we basically present one trial where the auditory is here and the visual is here. And then we present the auditory alone. Okay, and then it's really like an audiovisual lecture. And then we basically present the sound alone, and the sound alone is then also biased towards the visual signal. But what is very important is, we ask after the audiovisual signals, we ask always participants, did you think the two signals come from one or from separate sources? And we can demonstrate that the recalibration is very much pronounced when they perceive them as one coming from one source. So that means, yes, we can recalibrate very fast, and that is actually quite challenging because, of course, we shouldn't recalibrate too fast, right? Because sometimes they do come from separate sources. So it's quite a tricky bit. And what is also interesting, you can recalibrate the sound sources, the likelihood function, basically, at multiple timescales, which is concurrently. So there's also one experiment, not by us, but by others, that have demonstrated that if you constantly recalibrate the sound towards the left, and then at the very end, you just briefly recalibrate to the right, and then you ask first for the first 3 seconds, it's going to be recalibrated to the right, but then the recalibration to the right quickly decays, because it was also fast when it came, and you still have then the recalibration to the other direction. So it's a bit like what you also have in sensory motor learning. You can also recalibrate sensory motor stuff at multiple time scales. So it's fascinating what the brain is able to do. Yeah.
That's very interesting. Thank you very much.
Yeah, go ahead.
Thank you for the talk. I'm wondering the visual audio input would be perfect multimodal input for robotics. So I also heard Professor Uta lead the robotics lab. So what are you thinking about, like this research, so computational neuroscience research results in the implementation of robotics?
So what I think, why sound might be important for robotics? Is that what
No, I mean, how can we implement those results to robotics or human-robot interactions?
I mean, I think probably like visual tactile integration might be more important for robotics, right? But I think in principle that demonstrates that sounds are still very important even for spatial localization. So my impression is that robots probably mostly are visual based, but I mean, this is not my field. I feel like I'm talking here about what I shouldn't be talking about. So I hope rather that you basically find out and tell me why these results are important. But I do think sounds are very important. But in fact, I think they might be even more important for the aspect that I was not showing, namely for the complementarity. So that you basically, the sound is usually more like a fast sense, right? So it alerts you. When you cross the street, you focus on something, but then you know something, or someone attacks you from the back, from behind, right? Then you basically hear this, but you can't see this. I mean, maybe depending on where your sensor are, you might be able to see, humans are not, but it's still like, it's nice because it's omnidirectional, right? So that is, I think, the brilliant thing about sound. That is certainly one thing. And of course, like, it is very important if you want to communicate with humans, right? Because humans' communication, that's where the sound is, of course, very, very important, right? And maybe that's also what robots want to do in the long term.
Thank you.
Yeah, we have a question over here.
Hi, thank you for the talk. I was wondering if, so in one of the experiments you were showing with the blinking and the sound, there was a constant blinking, and then we can focus on, okay, this is the pointer that we should find. Like if there is a constant delay and you keep on moving the beep and keep on changing the marker, does the human brain kind of synchronize that, okay, the marker is moving at this rate and the sound is following it, or other way around, or it cannot really follow it and it gets lost that, okay, I'm seeing visual cues differently and audio cues are moving differently?
Are you talking about this experiment?
Yes.
So what is the question there? I didn't
Like if you desynchronize the visual cues and the audio cues against each other, or maybe in an order, is the human brain able to catch this kind of delay that the visual cue is moving and the audio is following it?
No, we haven't done this, but another group has done it. When they are not really synchronized, it doesn't work, it falls apart. I mean, of course, it's also like tricky here, because when it's not synchronized with the target, then it's more or less synchronized with the visual signal. And the problem is that the visual sense is temporally very unreliable, and that's actually maybe to her question also where sound comes into play, right? Sound has got a very, very high temporal precision, while the audiovisual binding window is quite imprecise. It goes up to 150 milliseconds. So when two signals happen within 150 milliseconds, you might still bind them, even though they are actually slower. So that's where, that's when you present, for instance, like, even if you present the sound before the visual signal, you could argue, well, this might be like an alertness, and you might still get the same benefit, but you don't. You only get the benefit when it's really temporally precisely synchronized, basically. And that suggests that it might be more like a bottom-up thing than just like a top-down attentional thing. But I could imagine, of course, like for robots, also like the sound might be like an alerting signal and everything. That might maybe also quite an important thing, right? Yeah.
Just to clarify, so you're saying that if the audio signal follows the visual signal, it's important, otherwise it might be mixed and we will not be able to integrate it.
Yeah, so if the auditory signal follows the visual signal both ways around, also if the auditory comes before the visual signal, it also doesn't work. It has to be within the sort of audiovisual binding window of plus minus 100 milliseconds. Yeah.
Good, thank you.
Yeah.
All right, well, please join me in thanking Uta for this wonderful and really informative talk. Thank you so much.
Hello, everyone. Welcome back from coffee. We're going to start to stay on time. I'm delighted to chair the HRI session together with Dr. Rashid Alami, and we're going to dive right in. So the first talk, thank you, on behalf of Lucy Shi is Kevin Black, and he's going to be talking on Yell at Your Robot, Improving on the Fly from Language Corrections.
Yeah, hello. As she said, unfortunately the authors couldn't make it, so I'll be presenting on behalf of Lucy, and I'll try my best. Yeah, so the robot setup, we've got this bimanual manipulator with a microphone. It has a microphone to issue, so you can yell at your robot. So basically the idea is, if you have these long horizon tasks with a lot of subtasks based on language instructions, we want to be able to issue corrections as a human. For example, use the sponge to open the bag wider, and then use that to further improve our policy. So how do we do this? The foundation is sort of this hierarchical two-level policy. We have a high-level policy that issues language instructions, so you go from an image to language. And then we have a low-level policy, which then goes from the language and the image to the action. And the method is kind of like the main idea is dagger on the high-level policy. Basically, the idea being dagger on actions is very hard because you have to control the robot, but dagger on languages is much easier because you can just yell at your robot and then fine-tune the high-level policy without even having to change the low-level policy. So getting right into experiments, here's an example task, like pick up the Sharpie, and this is just the baseline. So there's still a high-level policy and a low-level policy, but there hasn't been any dagger-like fine-tuning. We can see it drops the Sharpie, it's really bad. But the main thing to notice is that it doesn't issue corrective commands by default because there's not that much of that in the data. So for example here, it's really failing to pick up the Sharpie. So you really should, it would be really helpful if it said like go lower, or in this case like move to the left. So the idea is the person can say that, and you can like iterate this sort of this dagger-like loop, and then now the high-level policy will self-correct. So for example here, it's missing the bag. It'll say something like move towards me, like towards the camera, go higher, and then put the Sharpie in the bag, and we can see, even though the low-level policy hasn't changed, that can really help even in these precise sort of tasks. Here's another example. It missed the tape, so it said move to the right. And this one, it changes its strategy, so it's trying to put the sponge in the bag for kind of a long time. And then the high-level policy, which does have sort of a short observation history, realizes this isn't working, so it'll say release the bag, or release the sponge and then stuff it in the bag instead. This is especially important for long horizon tasks. So what we see here is a sequence where it has to do all three in a row. And the main idea here is that the corrections really help with success on each one. And the high-level policy after this process is very strong, and it can basically give whatever the correct commands are that will get the low-level policy to do the task. There's the stuffing the sponge if you missed it the first time. Yeah, and then another way you can use it is, if the policy still isn't good enough, another big advantage is that you can keep the human in the loop and keep issuing these corrective commands if you really want the best performance you can get. So what you see here, you can't hear the commands, but basically the way it works is if the robot looks like it's about to do something bad, you can just say like stop or like pardon or something, and then the robot will stop, and then you'll override the high-level policy and say maybe like, oh, like, move the scoop towards the bag if it was about to pour everything on the floor, or if you change your mind and you wanted to grab a different thing, I guess. Yeah, you can still issue these human commands. And I guess this is more examples of the autonomous corrections, like go higher before pouring, stuff like that. Here's the quantitative results. So the lightest line is the oracle performance with you keep the human in the loop. That's kind of the max performance you can get. And the point here is that the fine-tuned dagger policy is already like almost as good as the oracle policy, at least on these tasks. So yeah, the main idea is you can yell at your robot and it'll listen to you. You can improve only from this language feedback on the high-level policy. And the only bottleneck would be the low-level policy, which is not updated during this process. But you can still do a lot with only that high-level tuning.
Do we have any questions? I have a question. It looked like the language was all, there were no prepositions, or like it was all very specific, and each phrase kind of stood alone. So have you looked at adding more nuance to the language, like that thing, references like that?
Yeah, I mean, of course, obviously I'm not an author, but from what I understand, you can see the paper for more details, but one limitation is here they used like a discrete set of language commands. So you can't have too many basically because it's doing a nearest neighbor lookup in the training data. I think a very obvious next step would be to use like a language model, which is a lot more open-ended, and then I think you could get, a lot more like open-ended with the commands.
Thank you. The other question?
Yeah, in this example that you are giving, is there a goal given to the robot globally and then adaptation or not? Because it's not clear how the loop is running. Is it step by step or is it?
I'm not 100% sure. I think you'll have to check the paper. I think in this paper, there's a single task policy. So like it knows that the goal is always to like
sequence.
Yeah, like put all three things in the bag or something like that. But you should check the paper.
Let's thank our speaker again.
Okay, so the next speaker is Mike Allensbach. And the title of the paper is Task Adaptation in Riemannian Motion Policies.
Yeah, hi everyone. I'm Mike from the Autonomous Systems Lab, ETH Zurich, and as mentioned, I would like to show you how we do task adaptation in industrial environments. So most of you probably know modern robots have become increasingly common in different industrial applications. So we have seen assembly, inspection, also recently on construction sites, and also non-destructive testing, to name but a few. Now, these applications are, of course, vastly different, but we believe that they can actually be expressed and decomposed into several underlying tasks that are sort of shareable across the different applications. So you can see obstacle avoidance, exerting forces with respect to the environment, following a trajectory or a path. So this is something that's very common. And especially in terms of interacting with surfaces, you could, for example, need to maintain a certain distance to the surface or remain orthogonal to the surface. And finally, simple target tracking. So in order to synthesize any industrial missions, we believe that you basically just need to adapt these tasks and sort of combine them appropriately. And this is, of course, not very easy because robots are pretty bad at decision-making, so handling unexpected situations, unseen circumstances. And so we basically want to exploit human operators to do this. So you can see we have these different tasks in the planner. We need to somehow adapt them based on ideally high-level human inputs. So just to show you a bit better how this works, we've prepared a 2D example. So imagine you have the robot here, and then you have two different targets that you might want to track in the process of your mission. So you have the first target, which has its potential field, and then similarly the second target with its own potential field. And so now the question is, let's say the human actually wants to go to the first target, so how do we figure out, or how can we mix and combine these tasks such that at the end of the day we actually end up at the correct target? So the way this works is both of these targets, as I mentioned, have their gradient, their potential field, which basically dictate the direction of motion that they will end up implanting on the robot. The human sees how the robot is currently doing, how it's moving, and then issues corrective commands. So the idea is you just point towards the target where you actually want to go, and then this helps us to generate the desired direction of motion. And now it's quite straightforward. So you basically compare this desired direction of motion, so where does the human want to go, with what do the different tasks actually do, and the one that aligns best is the one that is activated at the end of the day. Right, and then again, so the task itself is basically done autonomously, so there's no more human input required. It's really just to identify the correct tasks. Now, how does this look like in reality? So we replicated an industrial non-destructive testing mission. So you can see we have this curved surface with these very professionally marked inspection targets. And the idea is basically you have a target at each inspection point, and the human needs to iterate through them as they're instructed. So what does this mean? You can see here a different perspective. The red circle is basically where we want the human to go. So this is instructed from an experiment supervisor. Then the blue circle is where our method thinks the human wants to go. And then on the bottom, you can see the joystick commands. And as this plays, you can see the joystick commands are very sparse and highly informative. So there's no manual control of the robot. This does all the tracking on its own. So the human really only gives directional commands. So I want to go to the top right. It's just the top right information. And this way, again, the joystick input is very sparse, so you can really help the system a lot. What's also nice here is you can seamlessly integrate this with an autonomous mission plan. So what do I mean by that? Here, the robot basically knows already in which order you want to go through it. So this is almost fully automated in how it switches through the tasks. But at any point in time, the human can actually intervene. So this is what you see now. It's the same method as before, so you just give it the directional input, but you basically pause this autonomous execution, so this allows you to maybe go back to take another measurement, maybe look ahead a bit to see what's coming. And at any point, if you want to go back to this sort of autonomous execution, you can just go back where it stopped, and the robot will continue on its own. So this way, we can put a bit of effort away from the human and let the robot do what it can do best on its own. So in conclusion, we have seen how we can do dynamic task adaptation based on human high-level inputs. And something that we also saw compared to state-of-the-art is we have enhanced modularity and also improved user interaction. Unfortunately, we didn't have time to put this in the video, but I would invite you to come to our poster and then we can discuss this. So we did a quantitative evaluation compared to different state-of-the-art methods. Thank you very much.
Any questions?
Yeah, I had a quick question about whenever the user provides the feedback, you can think about maybe that space being discretized over a grid. Is that feedback just like one discrete element, or could you think of it as maybe a probability around all of the different potential targets, and then you can kind of hone in as the user provides more feedback?
So you could do that, yes. At the moment, it's really just direction-based. So you basically check whatever lies in this direction, and it will go there. The limitation is a bit that if you have multiple targets that are sort of within the same range, then yes, it becomes more problematic. But it's a continuous method. So basically, as you get closer and the targets become more separated, then the human can better guide it towards the desired one.
Thank you.
Other question? No? Okay, so I have very fast. I have a question concerning, but I think it's the same as, if there is an ambiguity, what happens in the...
Yeah. So at the moment, so as I said, it's really let's say the limiting cases, for example, if you have two targets behind each other and then you can't distinguish it. So the way it handles it at the moment is each task has like an attractive or like a region of attraction basically. So as you get close to the one that's first, it will essentially stop and wait whether the user provides another input or not. But yeah, this is something we need to still work on a bit, also maybe artificially separating them to force the user to make it more clear. But it is a bit of a limitation or something to at least consider how to handle it. Yes.
Excellent. Let's thank our speaker.
Thanks.
Our third speaker can come on up. Introducing Justin Ledard, who's going to talk to us about risk-calibrated human-robot interaction via set-valued intent prediction.
All right, good afternoon, everyone. My name is Justin, and today I want to talk about risk calibration and human-robot interaction. Recently, foundation models' superior generalization capabilities have allowed robots to infer human intent in vague or ambiguous scenarios. We can now ask a robot to complete a task like this, or it must help someone sort some household objects into bins. The robot should try to understand the human intent based on what objects are in the bins right now, for example, placing various toys into the toy bin. But notice here, there's an ambiguous situation. This green wooden object might be considered as either wooden, like some of the toys, or green, like the other vegetables. So the robot is uncertain which bin to place the object into. In fact, when I asked GPT, it's not sure either. It says that the wooden toy could be put with the vegetables since it might be a representation of zucchini. And this might sound silly, but instead of guessing and causing someone to crack their tooth on a wooden toy, we like our robots to know when they don't know and ask for help before acting. In this work, we rigorously quantify the risk associated with model miscalibration in human-robot interaction scenarios where the robot is asked to predict human intent. First, we assume the robot has access to a prediction model, such as a VLM, to predict a human's intended high-level action to complete the task. We want to bound the risk as the expected cost of prediction errors across a distribution of scenarios. By quantifying this uncertainty associated with human intent prediction, we can give a robot two key capabilities. First, we allow the robot to know when it doesn't know and ask for help when it is uncertain. Second, we can bound this risk across a distribution of scenarios, such as different tabletop configurations from our cleanup example. Now, how can a robot know when it is uncertain? To help the robot take the right action, we generate prediction sets, which contain its best prediction for the human's intent. In this case, we generate a prediction set that includes vegetables or toys. Since the set has more than one element, we consider the robot to be uncertain about the human intent and let it ask for help from the human. Sometimes, however, the set only has a single element, which means the robot knows the human intent. We call our approach RCIP, Risk-Calibrated Interactive Planning. Our goal then is to tune these prediction sets to achieve a statistically guaranteed level of risk. With enough help, we can limit the number of task failures from incorrect intent predictions, as shown in prior work such as No-No from Coral last year. However, this might put the amount of help above what the human is willing to provide. Thus, we can model the help rate as a separate additional risk. Our insight is that by reducing the help just a little bit, the robot can still operate consistent with the failure limit while also satisfying the help limit. RCIP provides a method for guaranteeing that a robot can satisfy these two risk limits, that is, the failure and help rates, simultaneously, which is a novel contribution of our work. Now, how do we tune these prediction sets in order to achieve our statistical guarantee? That is being done with calibration. As input, the RCIP procedure takes a modest-sized calibration dataset of 400 interactions with the human and their failure and help tolerances, for example, 20% and 10% of scenarios, respectively. Our procedure uses multi-hypothesis testing to tune the prediction sets that contain the user's intended action, ensuring a higher task success rate while minimizing the amount of help needed. The output is a guarantee that these tuned prediction sets will satisfy the user's risk limits. Next, I'll present our results. We deployed RCIP in 4 different settings on both simulated and real robot platforms. Open category sorting in the upper left is our running tabletop example. The other 3 settings also involve challenging closed-loop intent prediction, and quantitative results can be found in our paper. Now let's see RCIP applied to our sorting example once again. So recall that we want the robot to ask for help when it doesn't know where to sort this green cylinder. Using our tuned prediction sets from RCIP, the robot's prediction set for the human's intent is vegetables or toys, and it prompts the human for help. Then the human specifies that they want the cylinder sorted with the other toys. Finally, all the robot has to do is place the cylinder in the black bin, which can be accomplished with any off-the-shelf pick-and-place planner. In our paper, we also show novel extensions to multi-step statistical risk calibration, which we apply in a multi-step sorting experiment similar to this one. We tested RCIP against several baselines at several risk limits. This figure shows the planned success rate per unit of human help. And overall, we found that RCIP achieved a higher success rate as the amount of human help increases compared to the baselines. Specifically, we compared RCIP to No-No, which uses multi-step conformal prediction to control success rates. While conformal prediction performs well against uncalibrated baselines, it's also a single hypothesis procedure, meaning that it's inflexible to different model parameters, like the temperature. Instead, our multi-hypothesis method generates more flexible predictions overall, leading to better calibration. To summarize, we present RCIP, Risk-Calibrated Interactive Planning. We introduce a rigorous uncertainty quantification method for HRI that allows a robot to know when it doesn't know, ask for help when uncertain, and, new to our work, tune the level of help needed based on user-provided failure and help limits. Before I conclude, I'd like to thank all of my collaborators at Princeton. And if you'd like to chat more about our method, please come visit our poster session at 6 p.m. and visit our website for additional information, videos, and code. Thank you.
Questions? We have one over there. Jonathan, can you hold that a little closer?
I'm like, oh, there it is. Okay. Thank you for this. There's a bunch of really interesting things that I'll bother you at the poster session about. I think one small thing I wanted to clarify from my understanding from the slides, I think at one point you had an example that explicitly said that the user had a 20% tolerance or something like this. Am I understanding that the user then, I don't know that I can say my tolerances in percentages for how much I am or am not willing to be asked for things? So is that a misunderstanding, or how does that actually get set?
So I think we need to be careful because this is a multi-step setting. Because we're using a procedure that assumes samples are IID, we do need to be careful about sort of task failures, and that can introduce distribution shift. So in order for, like, maybe you only care about the help rate, but you don't really care so much about whether it's 20 or 30% failure rate. That does play a role in terms of the validity of the other guarantees for you, the other risks that we want to bound. So yes, we can bound a certain number of risks, and if we don't care about certain risk signals, maybe we can leave them unbounded, but for this one, we do need to care about it a little bit. I don't know if that helped clarify or made it more
Yeah,
complicated.
that is useful. I think one minor thing is, but it is the case that I then do specify numerically my failure tolerances for everything.
Yes, that's true. We are assuming we have basically a bound between 0 and 1 for each signal that we care about. And if we don't care about it, except for the one you mentioned, then we don't bound it.
All right. Thank you very much.
I got one here as well. Thank you. I'm over here.
Sorry.
Doesn't matter, but disembodied voice.
Oh,
thank you. We need like laser pointers or something. So I realize HRI is your focus, but it also feels like when the robot's asking the human, to clarify something, that's something that that the robot could learn from, and then, over time not have to ask so often. Is that something you've considered at all, interested in at all, or?
I think it's something that you could merge with this framework. It's not something we did in our experiments. The complication for doing this like learning over time or maybe like some sort of Bayesian update is the fact that you have to apply your same policy at calibration time as you do at test time. And because of this IID assumption that I mentioned earlier, you can't really learn from other samples in a way that's tractable because you need basically this independent sampling from your distribution. However, you could learn over a sequence of points. So like maybe I interact with a user in a single environment and I learn only in this environment. And I think that's something you could do. But you just have to be careful about applying that same policy at calibration time and test time.
Thanks.
All right. That's all the time we have. Thank you very much. Let's thank our speaker.
So fourth paper is from Yves, Constraint-Aware Intent Estimation for Dynamic Human-Robot Object Co-Manipulation.
Hello. Hi, my name is Yifei from Grasp Lab. I will present constraint-aware intent estimation for dynamic human-robot object co-manipulation. So powerful robots are not working closely with humans and are often kept behind fences since they're too dangerous. The common approach to bridge this gap is to use a force torque sensor on the end effector to detect the intended motion. However, when co-manipulating in 6DoF, it's hard to disambiguate force and torque, especially when object is elongated. How can we make powerful robots co-manipulate objects with us in 6DoF while being amenable to our instantaneous needs without a force torque sensor? So we believe the answer is adaptive compliance. Make the robot more compliant when it's unsure of the human intention and stiffer when it's confident. Allows the robot to be compliant, allows the robot to transition between a leader and a follower adaptively. To achieve this, 3 problems need to be addressed: how to represent human intention and how to estimate it, how do we adapt between being the follower and the leader, and how do we make sure the robot satisfies all the constraints. So our method solves these problems with the control diagram shown here. For the intention estimation, we choose a simple representation that can be estimated in real time using 2 particle filters. So more specifically, we assume human intent can be represented as a simple goal-oriented dynamical systems, or a tractor that describes where the object is going, and a dynamics matrix describing how the object is getting there, generating reference velocity in both Cartesian and rotational dimensions. So DS has been widely used for controlling manipulators, ensuring stability, and basically compliance. However, works that use this usually predefine the DS, highlight or learn DS from demonstrations. So instead, we use a particle filter to estimate the parameters of DS highlighted in yellow in real time. So since with the robot being compliant, we can get away with using past velocities as and accelerations as observations. So next, how do we, given the reference velocity predicted by the particle filter in the previous step and the velocity tracking error here, we can compute the confidence as shown here, so that the higher the tracking error, the lower the confidence. We then compute task space force and torque with variable impedance controller and vary the gains with the confidence, achieving row adaptation continuum. As a result, when a human pushes the robot, increasing the tracking error, the robot will be less confident and use less control effort, leaving 6-off movement up to the human and only do gravity compensation. And lastly, to satisfy both human and robot constraints, we ensure goal-post feasibility in the particle filter and joint space feasibility in the controller. So in a particle filter, we implement a particle trimming scheme to remove goals that are infeasible for the robot based on inverse kinematics. On the other hand, we shape the particle filter noise based on human manipulability ellipsoid as an indicator of human capability and comfort, and demonstrated by the white dots here. And the capability-aware controller converts task-based output to joint torques and tracks a preferred configuration as null space task and enforce joint limit constraints. So putting it together, we have a system that estimates the intent while satisfying constraints. So we show in the paper that it's passive and closed-loop stable. To evaluate it, we designed a game where the subject is asked to move a 5 kg object towards a goalpost unknown to the robot. We use the force torque sensor on the handle to record the user effort as integrated force and torque over time. With 20 such trials and from 3 subjects, we find we save about 17% force and 23% torque compared to a well-tuned admittance controller. Of course, that uses a force torque sensor. We also find our method performs similarly to adaptation method, which knows the ground truth goalpost and selects between goals using human force measurement. Please see the QR code for more information. We also have integrated this work with the LLM and presented yesterday at a workshop that you don't have to yell at your robot if physical corrections are allowed as the communication interface. And we actually added, as that gentleman said, correction in the interaction history as learning in context, but found if you are like 5 or 10 interaction histories ago, you corrected a robot, that it retains about 80% of what you corrected to do if you are met with the same situation the next time. Yeah, that's it.
Questions?
Hello, thank you for the talk and interesting framework. So from the last slide, I understand that you don't have a torque sensor, but you're using a robot that is torque controlled, so you could estimate the force. Have you considered to compare, or I don't know, because my experience, if the force is high, you just make the robot compliant. And then
Yeah, that is correct. But that force torque sensor measuring from joint torques are notoriously known for very noisy and hard to measure, but we haven't compared it, but we will do that, yes.
Okay, thank you.
I have one question.
Yes.
What is the intent? What kind of intent can you express here?
So the intent here is actually, as I said, the attractor and the dynamics matrix, which is a very simple representation of intent. And I feel there's no like a common consensus on what the intent is. But currently, I feel because humans are moving all the time and specifying different things all the time, I think doing it in the MPC, which is what I'm doing, like always changing it, always re-estimating it live, might be the right thing to do. Yeah.
Our next speaker is Chen-Shu Wang, talking about demonstrating human Thor. I'll let him take it away.
Hello? Hello? Okay, introduce human Thor. We believe that building a simulation system is very essential for human-robot collaboration because it's scalable, economically cheap, and flexible. And we expect a simulation platform to have some key features. For example, 3D simulation with a VR interface for humans to act in the environment. And we also expect it to be human-in-the-loop collaboration instead of offline demonstration so that human can act in the same time with the robots. And we also expect it to be shared space collaboration. That means that human can not only be an instructor, but also can be do something by their own hand in the environment. And since we target as human-robot collaboration, communication is also essential. So we expect they can communicate with images and tags, and so just like using an instant messaging software. Yeah, so now we introduce Human Soar, a simulator built on the Soar platform supporting the aforementioned features. So we start from building a 3D environment with a Unity program, supporting various robot agents that can be controlled by algorithms through the APIs. And we also build a human avatar that can be controlled by the VR devices. We also embed a communication panel in the environment so that robots can send image text messages to humans, and humans can respond through the VR controllers. Now, Human Soar is designed as a general platform supporting various HRC benchmarks. From a platform perspective, we model the benchmarks in a hierarchical way. That means we start from supporting elemental skills such as object navigation and manipulation for both humans and robots. And then we combine them into HRC tasks, including mobile manipulation, VRN, room arrangements, and others. Finally, we can study some high-level scientific programs such as human trust modeling and series of one. Now we demonstrate our system with a few short examples. We start from navigation, a fundamental functionality, where the robots can move with the APIs and humans can move with the VR controllers. And humans can also manipulation. For example, they can grasp and drop objects by pushing and releasing the buttons on the VR controllers. They can also interact with the receptacles, such as opening and closing the fridge. Robots can also manipulate objects by the APIs. For example, we show a short example where the robot goes into the bedroom and pick up an apple and placing it on the desk in the living room. And objects are also dynamically configurable. So we can support multi-stage tasks such as room rearrangements, where the agent first explores in the environment and rearrange the objects in a messed up environment. Collaboration tasks can also be used to study human trust. Let me show an example in the video. And if the robots make a reasonable progress, we can expect that human trust will increase. But otherwise, if it takes some strange actions and sends some meaningless messages, we may expect that human trust will decrease. Now we show our general architecture of the system, including a Unity program that's responsible for the simulation and a Python software for providing the APIs for the HRC benchmarks and robot control. The system provides RGBD observations for visual-based agents, so it can be, the agents can be trained with deep learning techniques such as embodied clip and episode transformers and others. It can be very smooth to extend existing models to our system. And our system also supports customized task settings. For example, the numbers of robots and the capabilities of robots are also both configurable. And we will still continue to working on this project and develop some new features. For more information, please visit our project website where the link is shown below, and it also can be found in our paper. And welcome to our demo tomorrow.
Questions?
Thank you. This is, so two quick questions, if that's all right. One is, have you been able to test whether or not in this interface humans can perform well at the tasks like vision language navigation? So we don't normally have human level baselines for these things, but it seems like you can now use your infrastructure to evaluate those existing tasks and see what human performance looks like. Is that something you've looked at?
Well, so the question is whether the interface is suitable for the system and can improve the human performance. Well, actually, we have tested with some basic benchmarks. For example, mobile manipulation, where the human-robot teams need to just pick and place something. Just for example, putting an apple in the fridge. And we found that with the communication panel, and the robot can do something like helping finding the target object so that the human-robot team will perform better than no robot, single human. And for the communication panel, we have some user study to show that the robot is helpful with those communication.
It's very cool. I think that kind of brings me to the quick second thing, was just simply the communication panel is sort of turn-based. So is there ability to do interjections? So can you interrupt?
Yeah, we can interact. So the robot send a message, and the human can respond, and the robot can query whether the human confirm its message or decline its message or do something else. Yeah.
Okay, we'll get more at the poster. Let's thank our speaker.
Okay, so our next speaker is Erin, and the title of the paper is Developing Design Guidelines for Older Adults with Robot Learning from Demonstration.
Hello, everyone. Can you hear me okay? Is the mic okay? Okay. So hi, again, my name is Erin Hedlund-Body, and along with my co-authors, Lakshmi Seelam, Chushwan Yang, Nathaniel Bellis, Zulfikar Zaidi, and Matthew Gomble, I'm going to be presenting about what we learned from older adults teaching a robot with learning from demonstration. So the world's population is aging, and people may start to require physical or cognitive assistance as they age. And there's also shortages of caregivers and space-assisted living facilities. And so one solution to enable older adults to age in place is assistive in-home robots. But everyone has different needs and preferences, and so we need to give non-expert users the capability to customize and communicate their preferences to a robot. So learning from demonstration is one way to enable non-expert users to teach a robot new skills. And in this, the human provides the robot with a demonstration of how to do the task, and the robot learns from that demonstration. So the robot learns a policy pi hat that tries to minimize the distance between the learned policy pi and an expert human demonstration pi star, where pi is a policy that maps states to actions. However, learning from demonstration is underexplored with older adults, and there's a critical need to really explore our systems and if they're going to work or fail with target populations. So in this work, we are really investigating if learning from demonstration is a valid research direction for work with older adults. What are the current barriers for teaching, for older adults teaching with learning from demonstration? What are people's perceptions? Do older adults even want to teach with learning from demonstration? And then also, what can we learn? How can we improve learning from demonstration to be more accessible in the future? So in this paper, we first conducted focus groups, then we designed an interface, and then we conducted an experiment with the real robot where participants came in and taught the robot with learning from demonstration. So here's a video of the experiment. So we had a population of older adults and a population of younger adults teach the robot using learning from demonstration. They taught two different tasks. One was loading the dishwasher, and the other was wiping the counter. So this video shows the procedure for loading the dishwasher, and so you can see our interface that we developed in the corner. And so participants gave 3 demonstrations to the robot, and then the robot showed its learned performance. And then participants could give another 3 demonstrations and see the robot's performance again and see if they could improve the robot's performance. And I want to note that the robot was learning in real time. The average training time was about 46 seconds. And so the way the robot learned, we implemented a probabilistic movement primitive algorithm. And so we tracked the Cartesian pose of the objects using April tags. And this could be replaced with something like a computer vision algorithm or something in the future. And then the robot learned a trajectory. And we picked ProMPs because they can learn very quickly with very few demonstrations. But I do want to note that the accuracy of our system wasn't perfect, but our goals were to evaluate an end-to-end learning system with real users learn in real time, and understand user perceptions during both success and failure. So if it was a perfect system, that wouldn't have necessarily helped. And so here's a video of the robot, what the robot learned from the previous demonstration video that you saw. And after people saw the performance, they rated the robots on terms of accuracy, usability, and we conducted qualitative interviews. And so here's some results, more in the paper, but we see that younger adults perceive the robot as significantly more accurate than older adults. Younger adults is in purple, older adults is in blue, but there wasn't a significant difference in objective accuracy. Also, older adults asked significantly more questions when using the interface and found the process significantly less usable. So overall, older adults were more critical and found the process less usable. From the qualitative interviews, we found that everyone wanted to teach the robot, but older adults would want a technician's help to get started. And we also found that everyone found the value in learning from demonstration, but older adults would only really want to use this or an assistive robot if they couldn't do the tasks themselves. We also found that when giving demonstrations, older adults used more gestures and talked to the robot and used gestures like pointing and other things which confounded the learning from demonstration algorithm. And lastly, we found that older adults tended to blame themselves more and were less confident while teaching the robot. So we synthesized all these results to develop design guidelines to make LFD more accessible in the future. For example, people need better instructions and tutorials on how to be good demonstrators. Also, people wanted feedback from the robot, especially when it failed. They wanted to know why. LFD algorithms shouldn't just mimic the human. They should also understand the environment and the goal in a way that's sample efficient and easy to train. And also, we should be incorporating multimodal information like verbal and gestures into learning from demonstration algorithms. And overall, our goal is for these guidelines to ground and inform future work in learning from demonstration, and so we invite everyone to read our paper.
Thank you. You're asking very interesting questions, but I'm wondering how much you can generalize your arguments. For instance, you made a choice of 3 demonstrations, and if you had done 10, right, it may have been more accurate, but people would have been more bothered to do all of these demonstrations. So how can we be certain about that, for any learning from demonstration that we can learn from this type of user studies?
So, I mean, I think that's a good point, and there's a lot to say about the generalizability of it in terms of small sample size and cross-sectional study. But I do think that what we learned, I don't think will necessarily change that much with giving more or less demonstrations. I do think there's, people might have been less positive if they had to spend a lot more time teaching it. That would be my hypothesis, but that's why, in our design guidelines, like one of the things that we need to make sure is that these are actually like sample efficient, and so I think another future study would be really interesting to kind of see what that line is of like how willing are people, like how much effort are, real users, not people that are being, paid to give demonstrations, but, real end users, how much time are they willing to devote to this before they say this is too much work?
Hi, thank you for the talk. I saw that the perceived accuracy was quite low, around like 0.4 or something. Was this because the tasks usually failed, or was it because it just seemed to be like intuitively inaccurate from the robot side or something like this?
So, like I said, the accuracy was lower than we were originally hoping for. There's reasons in the paper why that is. Some of the reasons were actually, this is why one of our design guidelines is that we need better instructions for demonstrators. I'm not putting blame on the demonstrators and saying like, oh, they were bad teachers, but people moved too fast. For example, really in the wiping task, if they moved too fast in the detections, it actually aliased the signal, and so then instead of going back and forth, the robot just kind of like stayed in one spot. They moved too fast, they would cover up the tags, which then occlude the objects so then the robot couldn't see. There's some other reasons. There's a correspondence problem. People moved the objects in a way that then the robot's elbow would come down and hit the table, that they can move in a different way than the robot. And so there's some of those reasons that inform why we need kind of better training for demonstrators or robots to better learn from the way humans want to naturally teach. I also think, your question was the lower accuracy. So I think perceived accuracy was the human's rating of how well the robot did. And then we had an objective accuracy of kind of like, did the robot accomplish the task? But the perceived accuracy, I do think, one of the reasons that's why we said older adults were more critical. Like if the robot failed, or even like if it kind of did most of the task but wasn't quite right, I think the younger adults were kind of like, oh, it tried. Like I'll give it, like a 7 out of 10 or something. Whereas older adults were like, no, it didn't do it perfectly, 1. Like I wouldn't use this in my house. Like absolutely not. It didn't do it the way I wanted.
I see. And was there a big discrepancy between the objective success rate and the perceived accuracy?
So we found a significant difference between older adults and younger adults for perceived accuracy. So older adults were significantly more critical, but we didn't find a significant difference between the age groups in terms of objective accuracy.
I see. Thank you.
All right, I'm sorry, I see the question, but we're going to have to move on for the sake of time. So let's
Come
go
to my
the
poster.
next speaker. Let's thank our previous speaker. Our next speakers are Rajat Kumar Janamani and Priya Sundarasan, and they'll be presenting on flare feeding via long horizon acquisition of realistic dishes.
Hi, everybody. I'm Priya, and this is Rajat. And
that was my fault.
In this work, we present a system for robot-assisted feeding called FLARE, feeding via long horizon acquisition of realistic dishes. And in this video, you see FLARE feeding a care recipient with multiple sclerosis, whose preference in this case is to dip strawberries into chocolate. Our system FLARE can cater to strong user preferences, such as this one, without compromising on efficient plate clearance. And our system uses a large library of different feeding skills to perform long horizon bite acquisition of realistic dishes such as oatmeal, fruits and vegetables, noodles, desserts, and also sauces. The main motivation for our work is millions of individuals with mobility limitations who are unable to feed themselves independently. And while there are robotic feeding solutions on the market, they are largely pre-programmed and thus able to handle a very small subset of food items. Meanwhile, prior work has made immense strides towards both food pickup and food transfer, but tends to be largely limited in the kinds of plates which they consider. And oftentimes, these plates tend to consist of homogeneous food items and also ones that are neatly arranged and lacking variety. In this work, we aim to take a step towards more in-the-wild plates that a robot might encounter in the real world, that could be ordered, prepared, or homemade. But in-the-wild plates present 3 main challenges. The first being that there's many different strategies that we as humans use to pick up food. It's very long horizon, and humans have very different preferences over how we're fed. But FLARE is able to address all these 3 challenges using a large library of skills and factoring in both efficiency and preference into bite sequencing. We deploy FLARE across 3 different robots and at 2 different institutions as well. Our system uses a large library of skills, which we implement on custom hardware. And in this case, we use a motorized feeding utensil with 2 degrees of freedom. These extra degrees of freedom enable us to implement a large library of vision-based skills, including skills for food pickup like skewering, twirling, scooping, and also dipping food items into sauce. And we also consider pre-acquisition skills that can't directly perform food pickup but are useful for downstream manipulation, such as cutting non-bite-sized food items, grouping dispersed foods, and also performing pushing.
Equipped with this library of skills, FLARE takes a plate image and an optional user preference as input. It begins by querying VLMs to detect and segment food items. A task planner then generates the sequence of skills necessary to pick up each food item. The length of these skill sequences provides a notion of per food item efficiency, which we pass along with the given preference as context to an LLM, which uses chain of thought reasoning to decide which bite to feed next. For this user, who prefers strongly to not eat meatballs, the LLM prioritizes feeding spaghetti, even though it is slightly less efficient, as we can see in the skill execution sequence, where FLARE first pushes the meatballs, which are occluding spaghetti, and then twirls spaghetti, which is in line with the user's preference. We compare FLAIR against an efficiency-only and a preference-only approach in a user study with 42 individuals without mobility limitations and 6 realistic plates. We hypothesize that FLAIR is more efficient than preference-only. As an example, for this mashed potato and sausage plate, and no user preference, FLAIR indeed executes more food pickup skills than preference-only. Also, notice how FLAIR varies bytes much better than efficiency-only, which picks up all the sausages first. These trends hold across plates, with FLAIR in orange being more efficient than preference-only in yellow, and producing more byte variety than efficiency-only shown in gray for the no preference case. For strong preferences, we validate that FLAIR adheres to these preferences better than efficiency-only. Finally, to feed complete meals, FLAIR can seamlessly integrate with any existing byte transfer framework. Here we combine with an existing inside-mouth byte transfer method to feed a care recipient a dish containing various veggies and dips. In response to 2 Likert questions, the user strongly agreed that FLAIR's diverse byte acquisition skills and adherence to meal preferences are crucial for daily acceptance. Our system is not without limitations beyond food perception inaccuracy and hallucinations in skill sequencing. The biggest current limitation is open loop skills. Still, we are excited by the prospect of moving towards feeding more realistic dishes and encourage you to visit our poster session and our website. Thank you so much.
I'm here. Hey. Thank you for your talk. I have a question actually about the disposition of your plates. So when we look at the pictures, it's very color separated, food separated, right? You have all the ingredients that are still very separated. Did you try something that was, let's say, more mixed or something with less color differences between ingredients, and what would happen in those cases?
Yeah, I think some of the plates did have like slight color differences, and like many of these plates are like in the wild. For example, spaghetti and meatballs was like directly ordered from DoorDash, and we just put it on the plate, and like both meatballs and spaghetti are sort of red, so it does reasonably work in those settings. But yeah, every once in a while we do see like food perception inaccuracies, in which case our low-level skills, they have these checks in place, and if we detect something went wrong there, then we re-perceive and go through the loop again.
Okay, thank you.
Hi, I have 2 questions. One is that many of the videos you didn't like mark how to speed up. Is that all like 4 times speed up, or yeah?
Yeah, I think the videos in this are pretty much all 4 times speed up. We also, for example, with the motorized utensil, we have control over modulating the speed of some of these primitives. Like, for example, twirling takes a bit longer, as you saw, with things like, then compared to like linear pushing. So in the future, that's something that we're looking into, is maybe parameterizing these skills and the velocities and other parameters a bit more closely.
Yeah, also I have a little problem that do the patients need to reach for the fork, or the fork will come to his mouth like?
Yeah, so the in-mouth byte transfer framework, which you saw there, actually does come to the patient's mouth. And this is specifically designed for patients, for example, who have involuntary head movements. We want to be able to adapt to that, and also who may not have the mobility to lean forward. We also did integrate the system with outside mouth byte transfer framework, which, for example, just servos. So that's an option for people who have a little bit more mobility. But yeah, it's a great question. Thank you.
All right, I'm so sorry. We're going to have to save these for the poster session. Okay. We have one more speaker.
We have one more speaker. I don't know where he's coming. So the last speaker is Namdeen Gabu. Sorry for the benefits of sound resource and in-person replication on the ability of character-like robot sound to improve perceived social warmth. Yeah. It's not the right one.
Oh yeah, this is not the very different.
But can't you do it? Well, for social warmth, it's not sure.
Okay.
Yes.
All right.
Hi, I'm Nam Doagu, and I'm presenting our work, The Benefits of Sound Resound, on behalf of our authors from Oregon State University. When we talk about sound, we're particularly talking about nonverbal sound. So nonverbal sound essentially ranges from,
Can you help me start the video, please? Thank you.
Oh,
Go ahead.
cool. Yeah, my name is Andrew Wagu. I'm at Oregon State University. So when we talk about sound, we're particularly talking about nonverbal sound. Nonverbal sound can essentially range from anything like R2D2-like noises to the mechanical sounds of a gearbox. And it's seen some attention in human-robot interaction for quite a variety of benefits. In particular, it's been found to be able to help shape the social perceptions that people make of the system, be important for its actual adaptability in real life, and even influence the perceived cost. And we'll kind of get into a few of these later. Kind of before we talk about the paper at large, though, we do need to talk about these 4 types of nonverbal sound. So the first is consequential sound, which is essentially the sound that robots make as they move, and caused by interactions that they have with the environment. The next is functional sound, which largely conveys state information. So you can kind of think of things like an elevator that will ding when it arrives at its location. And there's emotional sound that conveys emotional information. You might have seen this in the design of fictional robotic characters like R2-D2 or BB-8. Lastly, there's transformative sound, which is kind of all about masking that consequential sound as before. You'll see this in things like electric vehicles most recently, where they'll play a tune or melody to bring attention to themselves. Kind of before we jump into the paper itself, we do need to talk about a few key insights from previous studies that we've done in our lab that informed some of the design decisions that we made in this paper. So first, we've explored the what-ifs of consequential sound, where we looked at making consequential sound quieter or less whiny, and essentially we saw that higher pitch was associated with higher social warmth and lower discomfort, while a quieter robot was associated with lower discomfort. Really, the main thing that we got from these studies was this idea that the base sounds of a robot do matter quite a bit. Going forward, we also explored emotional and transformative sound, where we saw that across a variety, or applying these sound profiles across a variety of commercial robot platforms, across contexts as well, we were able to make these robots appear more socially warm and more competent. And lastly, we've also explored the monetary value of sound. So we found that adding transformative sound to Turtlebot in particular increased its perceived value as well. So at large, we've kind of built up somewhat of a baseline of the effect of different types of robot sound. But in the explorations we've done so far, we hadn't really explored functional sound. And a lot of the studies that we've done previously were all online. So we looked to kind of remedy this with within subjects in-person study. So our particular study had participants engage in an assembly task where a service robot would intermittently deliver pieces towards completing that task. When the conditions changed, essentially what sound was played and when in the delivery process it was played as well. And we measured the social perceptions, perceived localizability, and monetary value. The conditions themselves were, the first was the consequential sound condition where there was no added sound, the functional where we had 2 tones that played on arrival and departure, and the character-like condition that essentially was a combination of the emotional and transformative sound, where the emotional sounds also doubled as notification. And the transformative sounds were played as the robot went back and forth in the table. And the kind of takeaways from the results, we found that The warmth and competence replicated as previous study with the character-like and no sound condition. Warmth with significance across all of our conditions, so character-like ended up being the highest, functional next, and the perceptions of localizability were as kind of we expected between the character-like and no sound condition. Our interviews also bolstered our story where we saw that people wanted sound in some way, and without it were noted that it was fairly uncomfortable, and this idea of like the sound cutting the tension between the user and the unfamiliar agent really bled through. Hopefully the main takeaways that I hope you get from this is, using nonverbal sound should kind of go beyond just social robots as it is used now, considering the competence and localizability implications. But thank you.
Questions? Any question? Okay, so is there one? Yeah. One question? Where?
Hi.
Hi.
So yeah, the results went very quickly, but usually we will find that there's like a trade-off between competence and warmth. So when an agent is perceived warmer, it usually decreases in the perceptions of competence. So could you, maybe repeat results or reflect on this and how the study results appear to be?
Oh, I wasn't actually too keen on like the paper that's referencing, but whether or not, yeah, I mean that's kind of interesting because I guess in both the original study that we had done with the emotional and transformative sound, we saw that both warm and competence were significant as well as applying it here. I guess. Yeah, I guess like I'm not as familiar with the trade-off, but I'd be happy to talk about it later at the poster session as well.
Sure.
All right. That brings us to the close of the HRI session. Let's thank all of our speakers again. We launch directly into grasping.
Test. Could the speakers for the next session please come to the stage?
Yeah, I'm combining. Yes. Cool.
Hallo, hallo. All right. Welcome back to session number 6. This is Grasping. I'm Jukse Leitner from Robotics and Monash University, both in Australia. and we're going to start the session in grasping. We have 8 excellent papers, and I hope there's going to be some questions, and I'm sharing the stage with Kapil. And we're just going to go straight into it because we're a couple of minutes late.
Okay.
First paper is by Hongbin Lin. There you
Okay,
go.
thank you.
Explain.
Good afternoon. Hi, everyone. I'm Hongbin Lin, and today I'm going to present our research word model for general grasping. And automating surgical tasks can greatly relieve surgeons' mental and physical fatigues. Frequent surgical tasks include grasping objects such as the needle, sponge, gauze, and thread, and the process like the debridement. Visual motor learning in general surgical grasping is challenging. First, the pixel ratio for the task objects, such as the gripper and the target object, is relatively small. The pixel ratio is less than 1%. Second, when we are using the Intel RealSense D435, the depth error is prone to be large, since the light pattern cannot be fully projected onto the object's surface due to its narrow and small shapes. We first segment object masks using the video object segmentation method, track anything. In each rollout, we first annotate the first frame of the streaming RGBD image with a few clicks. After the annotation, we can track the mask automatically. To solve the imprecise depth issue, we first estimate the imprecise region using the closest ground truth area. The depth is estimated as the median of the ground truth area, and the uncertainty is estimated as the minimal diameter of the bounding ball, including the ground truth and the estimate area. So in this example, the uncertainty is the length of the 2 links. So in order to solve the small pixel ratio issue, we present a novel visual representation. We have 3 layers in our representation. The first contains the mask coordinate and the scalar signal. The second contains the zoom-in mask. The third contains the zoom-in depth. So our intuition is to encode the depth and the mask into a compact 3-channel image. We are directly zooming the mask image. In the Dreamer V2, the initial encoded states are set to 0. In the beginning of the rollout. So the large error leads to the poor performance. So we deploy a simple technique called the virtual clutch. At the beginning of the rollout, we switch our controller to the idle action, which keeps the robot same configuration. After a few time steps, the controller switches to the policy action. We deploy a domain randomization, including the camera pose, target disturbance, gripper noise, and the image noise. We graph 3 objects in the simulation, including the needle, rods, and the box. Our learned policy can directly transfer to the real robot without fine-tuning. We evaluate in our controller in the real robots. We compare the SOTA baseline, including the Dreamer V2 and the PPO. So our method can significantly outperform the SOTA baseline. And we also evaluate our controller on the liver phantom qualitatively. Second, we evaluate the generality of our controller. Our controller can grasp diverse unseen objects and can grasp the object with an unseen gripper. So the success rate is 69% and in a quantitative study. Lastly, we evaluate the robustness of our controller. So for the visual robustness, our controller can adapt to the visual occlusion, including and the variation. So the minimum success rate is 75% without significant performance degradation in the quantitative study. For the control robustness, we evaluate our controller to grasp a moving target on the rotational platform. The success rate is 80%. So we also evaluate the regrasping within the time limits with the 55% success rate. So thank you for listening and happy to take some questions.
You're working in a very important domain. Don't you think in this important domain you should not be using an Intel RealSense D435?
Yeah, good question. So yeah, we see that in our domain, it is the safety is in the first consideration. So there is some previous work they used the RealSense for like the validation of to get the point cloud, right? Get the depth image. So actually, that RealSense, like the depth camera, can be deployed into the surgery, like the open surgery. You can just get the image. And in something like the laparoscopic surgery, you can first put the camera into the stomach first, and use another gripper to grasp to fix the camera. So it is feasible, but we are looking for some more advanced methods.
One quick more.
Okay, so there's a lot of learning involved here, but classically this problem would have been really effectively also solved by doing something like antipolar grasping from the segmented image. So did you guys consider trying to do something like that as well? Or I guess what else did you baseline against?
I'm not very sure. Do you ask the segmentation?
No. So assuming that you have a segmented image, you can either learn sort of a policy for grasping, or you can compute something like an antipolar grasp and then go for the antipolar grasp itself, or apply any sort of previously used grasp networks. So I'm just curious, did you guys consider any of those alternatives or no?
Still not really clear because I didn't really get the voice is really low.
Oh.
But maybe I can get. Is it the question is that why we are using the segmentation in our work?
No. I'm assuming you have your segmentation. Now, better? Yeah. Assume you have your segmentation, right? There are a lot of different techniques for going from that segmentation to a grasp. So historically, we've looked at antipolar grasping. People have used grasp networks. I'm wondering, did you do any sort of ablation here? Because the success rate is relatively low considering the simplicity of the object you're trying to grasp.
So you are asking about the difficulty in the grasping of the objects. Is it a unique question, or it can apply to the other objects, right?
No, the question is more about what other techniques did you try to evaluate how well you can...
Okay, I get your question. So in a previous method, they are using more like the tracking the position of the objects. Like you need to get the feature, or you need to get the specific point to track the position of the specific point, or the pixel of the specific feature. So in our method, we use the visual motor controller, which the input is the home image, which is can be more robust. So our method aims to increase the robustness and the generality. So let's say you are using the previous method, and you cannot grasp any objects, and you cannot get such a good robustness in terms of the vision and control.
Great, thanks.
Thanks, Hongbin. Maybe move that to the poster session so we can go on to the next speaker. Thank you.
Okay, I'd like to introduce Spring Grasp, Synthesizing Compliant Dexterous Grasps Under Shape Uncertainty. They'll be presented by Siri Chen.
Hello, I'm Suri Chen. I'm here to present our research work, Spring Grasp, a method to synthesize, sorry, how can I go backwards? Okay, it's a video. Oh, God. Okay. Yeah, grasping objects for knowing that their exact shape is important for grasping different objects in everyday life. Both passive compliance grippers as well as active compliance in the fully actuated dexterous hand can help to grasp different objects under shape uncertainties. Given an object, the existing force closure metrics evaluate a set of contact point P's to determine whether they can apply a valid set of force F's that balance the object in an equilibrium state. To successfully plan a compliant precision grasp, we need specific grasp metric that can consider different level of compliance and different level of surface uncertainties, as well as how the object moves during the compliant grasping process at the same time. Overall, our grasp planner takes partial point cloud of the object as input. We first feed in Gaussian process implicit surface, GPIS, with partial point clouds, which gives us a probabilistic model of estimated object surface and level of uncertainties. Then we optimize a compliant pre-grasp with our spring grasp metric based on the GPIS of the object. We will obtain an optimized pre-grasp, pre-grasp hand pose, a set of fingertip target positions, and a set of impedance controller gains. Then we will use fingertip impedance controllers to grasp the object. Each controller's gain is set with optimization. In our spring grasp planner, we modeled fingertips and object as virtual spring system connected to target anchor O's. The impedance controller gains are the spring stiffness, and force applied by each fingertips are the tension of the spring. The grasping becomes a dynamic process of these systems, evolving from its initial states as T0 to the equilibrium states as T equilibrium. In a feasible compliant grasp, force applied by fingertips should always satisfy friction cone constraints from the beginning to the end of the dynamic process. We define a friction margin to evaluate how close the current force is to the edge of the friction cone. The objective is that we hope the friction margin to always stay positive during the entire grasping process. Directly checking whether the force is feasible needs simulation of the dynamic systems step by step. Instead, we utilize the fact that we can analytically solve the equilibrium states using a singular value decomposition. And we check the friction margin of the initial states and at equilibrium states to measure the feasibility of the grasp. To optimize a compliant grasp, we use logarithmic mapping of the friction margin to do optimization. During the optimization, we also add other terms to encourage a stable grasp, such as to encourage fingertips to stay at object surface to avoid collision, as well as other heuristic terms to encourage more stable grasp. We demonstrate that our grasp planner can grasp different objects using single depth camera. Quantitatively, our method achieved at least 18% higher grasp success rate compared with baseline methods that plan with force closure baselines, including using higher gains, lower gains, as well as heuristically selected gains, as implemented in previous works. Even only with single view, we can achieve higher success rate compared with baseline methods with two views, which supposedly have more information. For each object, we can also grasp it from different poses. Our compliant grasp can also resist some perturbations when you apply it on the object. Compared to baseline method using force closure metrics, both stiff and compliant force closure baselines fail to grasp the object under uncertainty. Thank you. If you have any information, feel free to email me or visit our website. Yeah.
Any questions?
Yeah. Hello?
Better. I wonder, so you're doing these adaptive gains for the impedance of the hands. What is the Gaussian process implicit surface doing in all this process? Is helping doing something? Are you using some, I don't know?
So there's two roles for GPIS. The first role is that it will roughly describe where the object surface is. The second is that the Gaussian process implicit surface also can provide variance of certain region of the object, or even in the space. So we can plan the controller gains accordingly. For those regions with like higher uncertainties, we may use lower gains, which means being more compliant to ensure the contact is made on the object or prevent some kind of like abrupt or unexpected contact. Yeah.
Thank you.
Another question?
For the talk. Could you perhaps say a bit more about how you actually solve the grass planning problem? And do you rely on using nonlinear optimization, for instance?
It's a question about how I actually run a grass planner.
Yes, how do you solve it? And if you rely on using non-convex optimization, how do you initialize the solver?
So basically, we have we have 7 fixed like initial gases for all the optimization problems. So like all those graphs you're seeing in the video, or like even everything in the website, are from those 7 initial gases. And then we will run gradient-based optimization to minimize the energy functions, which I described earlier or in the paper. The key term here is grass feasibility energy terms, which utilize the friction margin of the spring grass matrix. Yeah, so basically it's a gradient-based optimization process.
I see, thank you.
Okay, say thanks to the speaker.
Our next speaker is Hao-Chen Shi, and they're presenting the work called DexCap.
Hi everyone, I'm Hao-Chen, first-year PhD student from Stanford. Today I will present DexCap, scalable and portable mocap data collection system for dexterous manipulation. In recent years, data-driven methods have shown promising results in teaching robots dexterous skills. Prior works mostly rely on teleoperation or vision-based motion capture systems. However, teleoperation systems are unportable and expensive to scale up, while vision-based methods are prone to occlusion. This makes us ask, is it possible to find a system that is portable and accurate for collecting dexterous data? We introduced DexCap, a portable mocap system with an RGBD camera on the chest, a pair of motion capture gloves, and a SLAM IMU-based tracker to localize the wrist pose. Here's the visualization of the collected data. DexCap captures 3D human hand motion and the RGBD point cloud of the environment, making it portable and capable of collecting data in the wild without robot systems. Our goal is to train robot policies with the collected human data. And how do we do that? We separate the training process into 3 phases: action retargeting, visual retargeting, and policy learning. First, we use inverse kinematics to match fingertip positions between human and robot hands. Here we showcase a matching result. To bridge the visual gap, we designed the chest camera to be attachable to the robot workspace. We transform the RGBD data to a 3D point cloud, convert it to the robot operation space, and remove redundant background points. With the retargeted data, we train a point cloud-based policy network. This consists of a point cloud encoder, either point net or perceiver, followed by a diffusion policy to generate robot actions. Our setup includes 2 Franca arms and 2 leap hands, and special thanks to Kenny for the awesome leap hands. Here are the train policy rollouts. The policy is learned with 1 hour of human mocap data collected with DexCap without the need of teleoperation data. We find that point cloud-based policies can generalize to unseen object geometries. During data collection with DexCap, humans interact with 6 objects. The learned policy handles new objects outside of the training distribution very well. How about more challenging tasks with longer task horizons and more fine-grained finger motions? We designed a T-preparation task to stress test our framework. We found 2 failure modes in the learn policy: failing to reach the correct position and failing to stabilize the lid when unscrewing it. So how do we fix our learn policy with less effort than recollecting all the training data? We introduce a human-in-the-loop correction framework with DeskCap, which includes residual correction and teleoperation correction. In the residual correction mode, a human will DeskCap and adds residual risk action to the policy action. This is useful for small adjustment. And for larger mistakes, which are very rare in our dataset, we switch to teleoperation mode to gain full control of the robot. Using these methods, we gather a correction dataset, merge it with the original dataset, and fine-tune a policy model. With a few 30 human-in-the-loop corrections, our robot completes a very challenging T-preparation task, which has long task horizons and fine-grained finger motions. Our framework also allows the robot to perform human activities like using scissors to cut paper. We observe a more than 30% improvement in task success rate after fine-tuning with correction data. Point cloud-based policies outperform traditional image-based methods when learning from in-the-wild human data. That's all for my talk. You can find more information on our project website. Thank you.
Thank you. Is there a question? There's one up here in the front.
Hi. How does like the policies compare to being trained on just teleoperation?
Yeah, that's a great question. So we tried teleoperation, and we found like it takes 3 times longer to collect data with teleoperation compared to DeskCap. So we didn't collect as many demos as we did with DeskCap to train our policy network. So so with a limited amount of data, teleoperation is definitely worse than our framework. And if we want to get the same amount of data, it will take much longer.
Makes sense. Thank you.
One more quick one.
What types of training loop did you use in order to smoothly combine the human actions and robot actions in the training loops?
Okay, so the question is, how do we combine the human correction and robot action in the human-in-the-loop correction framework, right?
Yeah.
Yeah, so our method is very simple. The human operator will provide the residual action when correcting the robot action. Because when the policy roll out, the robot will miss the target. For example, mix the grasp a little bit, but not too much. And the human operator only needs to move their fingers a little bit inwards to correct this action. And we directly add this residual action to the original data set to have a new data set and fine-tune the policy network for a few more epochs. And then we observe a more than 30% success rate.
Okay, thank you.
Thank you, Hajan.
Okay, our next speaker is Tazbalat Tanyazov, and he will be presenting GRACE, balancing multiple criteria to achieve stable, collision-free, and functional grasps.
Hello, everyone. I'm Tazbalat from CLIA Lab of National University of Singapore. And today I'm going to present our work on grasp synthesis, specifically how to combine different grasp criteria to achieve good grasps. This is a joint work with my colleague Kelvin and my supervisor Harold. Now let's start by looking at the example of the handover for the scissors. In this case, the person grasps from the blade and hands over the handle to someone else. This is safe and natural, but in some circumstances, this grasp is not possible. Consider the case where the scissor is inside the cup, like this. In this case, human grasps by the handle and hands over the blade. This is not the perfect grasp, but it's definitely a practical one. This shows that there is an inherent hierarchy on how we handle grasps, showing that certain grasp criteria takes precedence over others. Let me elaborate this more with the following visualization. here we are given two grasps, blue and red. Both visually look stable. Red grasp is in collision with a cup, but it's a good grasp for handover, while blue grasp is collision-free, but it's not the nicest grasp for handover. And the practical choice to execute is the blue grasp. So this shows that we value the collision freeness over functionality. So how do we bring this to the robotic grasp? To do so, we propose our first contribution, GRACE, grasp ranking and criteria evaluation. This is the modular probabilistic framework and with the core function of grasp utility function. We left out the derivation, but the high-level idea is that those ranked criteria from our previous example maps to the single grasp utility function shown here. So as a result, you can see the blue grasp has a higher utility value over the red grasp for the handover. And the target is to optimize this objective function. Unfortunately, when we tried to optimize, as you can see, gradients are mostly non-informative and flat. So we needed to do something about it. So we derived the lower bound using Jensen's inequality. This one worked well in practice, but one thing is happened in the final form, hierarchical ranking of grasping has vanished, which is not good for our scenario. So this brings our next contribution, another optimization framework, GRACE-OPT. The idea is to tackle the flat regions using gradient-free evaluation strategy while we take the gradients lower bound for further fine-tuning. So let me give you details how it works. Initially, we sample initial grasps using any METs available. We use GraspNet from NVIDIA, but it's not limited to this. Next, we sample more grasps around these grasps, normally in SA3, and optimize using the lower bound. And similar to evaluation strategy, we select the top grasps based on the original utility function. And then we iterate this T times until we get our final grasp, which is the blue grasp for the handover of this screwdriver. We tested our method in Isaac Gym in a scenario where it's hard to sample good grasps. The grasps were hard to sample because it was in collision points and it was unreachable. And the results show that our proposed framework gave higher success rate over the baseline filter method. Now let's look at the qualitative result. Here you see that initial grasps are all red, bad grasps, and when you used for the use functionality, you can see the grasps are being biased toward the handle, which makes sense because that's where the robot's supposed to grasp to use this. And when it's used for other functionalities such as handover, you can see that the grasps are being pushed away from the handle, which also makes sense because this is where a robot grasps it to hand over someone else the handle. We also run the real-world experiment using the Panda robot in a cluttered 2 different scenarios, and our results stay the same, where GRACE outperformed the baseline filter method in both scenarios. In conclusion, we propose GRACE, a probabilistic modular framework with rank-preserving grasp utility function. In addition, we propose GRACE-OPT, an optimization technique that uses strengths of both gradient and gradient-free methods. For more information, please visit our poster. Our ID is 183, and scan this QR code for the paper. Thank you very much.
Any questions?
The optimization seemed to work very nicely, but here on your right. But I didn't get how you collected the information that, for instance, the handle was the right place to grasp the, the pot or the pan. It was not from data. Was it like semantic information?
Okay, good question. Here, I just want to mention out we didn't train anything. We used whatever existing methods in the literature. For that question that you're asking, where did I get the grasps that satisfy the certain functionality for the objects, right? We used task grasp from NVIDIA. So we didn't modify anything. We just plug and play since our framework is modular. So if you have your own, let's say the data-driven or other methods for this kind of functionality assessment, you can just plug it here. But we didn't collect the data for that reason. Thanks.
Okay, one more quick question.
Hey, I have one question. So you said that you're using GrassNet for initial grass sampling?
Yes.
So I'm wondering, have you tried it out with different grass sampling approaches as well? Because the image you showed that many grass are in collision actually. So I was wondering how it works if you use, for example...
Sorry, can you repeat your last statement again?
The image you showed, many proposed graphs were in collision in the scene. So I'm wondering if you use a different grass sampling approach, how your method works then.
Okay, if I correctly understand your question, is you are asking whether we used anything except GraphNet, right, for initial sampling?
Yeah.
All right. Yes, we tried the GPD and the grass point detection. I think it's a famous method also, but it's more like analytical. Yeah, so we found that when you use GraphNet, I think it generates better initial samples, and usually we get better results. Yeah, but we tried also GPD, a bit worse, but it's still okay. But if you have initial graphs that are really bad, let's say it's completely random, then it was very hard to optimize them.
Okay, thank you very much.
Thank you.
Okay, thank you, Taspalat.
Thank you.
Our next speaker is Shura Pen, and she's talking about universal manipulation interfaces. Hopefully the video, can we get the video?
Hi, I'm Chur, a first-year PhD student from Stanford. Oh, okay. Hi, I'm Chur, a first-year PhD student from Stanford. Today, I'm presenting you with Universal Manipulation Interface, or, oh, I think it's not press start. Oh, okay. Hi, I'm Chur, a first-year PhD student from Stanford. Today, I'm presenting you with Universal Manipulation Interface, or UMI for short. UMI is a universal manipulation interface that allows anyone to collect manipulation demonstration data anywhere for any actions that is transferable to many robots. So, what exactly is UMI? First of all, UMI is a physical interface for human demonstrations. In contrast to in-the-lab teleoperation data or in-the-wild human video data, UMI is a sensory handheld gripper, which minimizes the embodiment gap while still remains portable and intuitive to use. You can easily carry UMI grippers anywhere to perform hard manipulation tasks, such as washing your dirty dishes. The onboard GoPro camera records egocentric visual observations, and visual inertial slams tracks the camera motion to recover robo actions. With a portable handheld parallel jaw gripper with a single wrist-mounted camera, how can we get sufficient information for policy learning? There are a few critical design decisions that make this possible. To get sufficient visual information, first, we utilize GoPro's fisheye lens to capture a larger visual context. Then, we utilize visual inertial slam to recover precise 6-soft gripper poses. We also add 2 side mirrors to create extra views for depth to create something we call implicit stereo. To get sufficient action information, we apply continuous gripper tracking to recover precise gripper width. We also use soft fingers to provide implicit force information from finger deformation. More importantly, we make sure this hardware interface can be shared across different robot platforms, such as Franca, UR5, and ARX, resulting in a universal manipulation interface. After demonstration, all the data are stored in just one single MP4 file, which contains all the data needed to train a robot policy. We hope that this can become a standard and shareable format for robot data. In addition to being a physical interface, UMI is also a policy interface for hardware-agnostic learning. UMI learns from the collected demonstration by training a neural network as the robot policy, which takes in visual observation sequences as input and predict robot action sequences as output. We use relative trajectory in the camera space as the action representation, which eliminates the need for a camera calibration with respect to the global warframe. during UMI data collection, there's no time difference between the observation and the corresponding action sequence. However, when deployed on robots, there exists latency between observation and action execution caused by sensor processing, policy inference, and hardware execution. So if we execute the predicted action sequence from the start, this will not match with the current observations. So instead, we execute the action sequence from the correct starting point, matching the current task state. Latency matching allows accurate execution and allow policy deployment on different robot hardware with different system latencies. So what can our robots learn to do from UMI? UMI enables performant and robust manipulation policies in the wild. Let's look at some hard tasks. Thanks to latency matching and accurate motion tracking from UMI, we can easily and intuitively teach our robot to do dynamic tossing. Our policy achieves 87% success rate. Oh, it's over there. And then we find that without latency matching, the robot exhibits jittery motions, and as a result, will destroy the build-up momentum and the object fall short of the target. With intergripper pose synchronization, 2 UMI grippers allow you to do bimanual claw folding with 70% success rate. We also find that we can allow robot to do long horizon tasks like dishwashing. The robot needs to turn on the faucet, clean the dish with the sponge, and also handle unexpected perturbation like the added sauce in the middle. Very annoying. Overall, UMI achieved 70% success rate on this task. So how does UMI handle in-the-wild generalization? We tested this for a cup arrangement task, which requires pick and place and non-prehensile pushing. Within just 12 person-hours, we were able to collect 1,400 demonstrations with 30 in-the-wild environments for this task. We drag our robots around campus, and to our surprise, our policies is able to achieve 75% success rate in diverse outer distribution environments, even on the water fountain. Thanks to the policy interface design, the whole system requires no camera calibration and is robust to base disturbances during execution, making it well-suited for mobile manipulation. Everything, including the car policy checkpoint, is open source and should work for any espresso cards from Amazon. Please check out our website and tutorial to give it a try on your favorite manipulation task. Thank you. And we have the UMI gripper with us at the poster session, so please come and give it a try. Thanks.
Thank you. I think there's a question there on the left already.
Nice. Dynamic tossing works there.
Applause for the speaker. Yeah. Okay, I have a question. You said you use the IMU plus a camera to do the visual odometry and to obtain the actions, right? I wonder whether it is robust enough because you have a fisheye camera, also have a mirror which contain a lot of dynamic objects in the view. At the same time, IMU is also a very jittering sensor. I wonder how do you filter this, the odometry or make it work all the time? And yeah, that's my question.
Yeah, thanks for the good question. So first of all, I think we're building off of ORSLAM 3, and then we're blocking out the mirror view so that that's not used, that the features there is not used during tracking. And then I think acknowledge that I think the SLAM process right now is sort of the most brittle point of our process. However, we do think that basically inherit all of the limitations from current visual SLAM system, so you need like well-lit room for good visual tracking for the features to work. However, I do think that there are future works that can be incorporated. For example, you can potentially use the iPhone AR kit to extract the post information there, or you can use a standalone VR tracking device to kind of give you more robust off-the-shelf SLAM performance. And we're actively thinking about that for future works. Thanks.
Okay, thank you.
Hello. Hi. You said that this is embodiment agnostic, yet you always use the same fingers. How much bias does this end effector add to your task? This is my first question. I have another one.
Thanks. Yeah, I think the question is about how embodiment specific or agnostic the policy is. So I want to acknowledge that I think while the data collection process is agnostic to embodiment, we do apply kinematics filtering on the data, depends on what robot, downstream robot we are using. So, and that's quite relatively easy. So once you know the robot base location as well as the kinematic chain of the robot, you can simply reject the data based on the end effector stays in the task space. And so and basically we do that on the data side, and then we train different policy for different downstream robotic embodiments. But
yeah,
in the future,
the question was, the end effector itself is an embodiment, and you use the same end effector around the robot. So did you try it with other end effectors?
Oh, it's a question about whether we can use other kind of end effectors?
Yeah, a different gripper, a two-finger gripper, but different one from the one that you used to collect the demonstrations.
I see. Okay. So for our work, we always use the same parallel jaw gripper, and we find that actually surprisingly, with two parallel jaw gripper, we can surprisingly do a lot of tasks already. But I think with maybe more complicated end effector like dexterous hand, we can do more diverse dexterous manipulation, and we're definitely thinking about that for future works.
Okay. I have a second question, if I can. Can I? So I think the overall structure that you have, it's a very interesting approach, and I think it allows you to collect data, etc. However, everything that you do is on the level of the fingertips. But there are many tasks that are very complicated. Like I want to put my hand inside, I don't know, a shelf in the fridge and get something, and there are a lot of collisions. So how am I going to do this with all this structure around your fingertips? And I could imagine that it is quite brittle to have all these mirrors there to do all this process. So do you think about the future of a different approach of getting this information without having all this built structure around the fingers?
By view structure, do you mean basically the limitation of
the camera, the mirrors, everything? They add collisions, so you cannot really go beyond the end of the fingertip interaction.
I see. Yeah, so I think we're definitely thinking about incorporating more, I guess, dexterous or more complicated end effectors so that we can actually go beyond it. And then we also are thinking about how can we make our policy to be able to handle collision avoidance either during the data collection part or during policy training.
Okay, thank you.
Thank you.
In the interest of time, I know there's a few more questions, but in the interest of time, please ask those questions in the poster sessions. We'll just 10, 15 minutes away. Thanks, Chair.
Thank you.
Okay, the next paper is Learning Any View Six-Off Robotic Grasping in Cluttered Scenes via Neural Surface Rendering. I'll be presented by Snehal Jari.
Thank you. Hi, everyone. I'm Snehal Jari, and together with my co-authors Ishika Lunawat and Georgia Helvatsaki, we're happy to present this work from the Pearl Lab at TU Darmstadt, Germany. All right. In this work, we consider the any view, any scene grasping scenario, where we have a home robot, which is, let's say, a mobile manipulator, and it needs to operate in an unstructured environment, and the only input it has is an embodied camera, let's say a head-mounted camera, that it used to perceive the scene. This work is a reinterpretation of grasping as neural surface rendering to enable the extraction and learning of local features relevant for grasping. And we show that our approach enables state-of-the-art any view six-off grasping. We use a neural implicit representation of the scene. This is done through an occupancy network where we take a single input depth image, encode it into a TSDF, and use an occupancy network to reconstruct the scene. However, an open question still remains about how we can actually extract grasp-relevant features from a neural implicit scene representation. So towards this, we propose to use new GraspNet, which reinterprets grasping as rendering. And we essentially use a two-stage approach. As a first stage, we use grasp candidate generation using scene-level rendering. So using an input that you see on the left, you can use virtual cameras around the scene to do raycasting and get a coarse global point set. And then you can use this to get dense grasp candidates around the whole scene, and also include constraints such as semantics or reachability already in this stage. Then, as a second stage, we perform local rendering. Now, In local rendering, again, we use virtual cameras around the gripper and perform raycasting with these local cameras. These allow you to extract features relevant to the local gripper and object relationship. And we again do this in a way such that you can implicitly query these features for any particular grasp. So overall, this is what our overall pipeline looks like. At the bottom, you can see the implicit scene representation and scene reconstruction. On the top left, we see the global surface rendering and grasp candidate generation that allows grasp candidates throughout the scene. At the middle, in the top, we see this local feature rendering per grasp. With the local feature rendering, we get the local information between the gripper and the object. And crucially, we train for both grasp quality prediction and scene reconstruction jointly. This enables good feature extraction in a joint training pipeline. We evaluate our method on the VGN benchmark. As done in many prior works, we generate a data set in simulation using grasp labels, whether they're successful or they fail. And we train our network new GraspNet as well as the other baselines on this data set. And we see that new GraspNet significantly outperforms baselines in terms of grasp success rate, as well as decluttering all the objects in the scene, or declutter rate. We also evaluate on the EGAT dataset, which is a dataset of objects of varying complexity. And we also randomize the viewpoints, so we try fixed top views, random views, as well as hard views. And again, our network is able to perform pretty well even with difficult scene reconstruction scenarios. We then perform a sim-to-real transfer to a real robot. Here we see a mobile manipulator with a head-mounted depth camera, and we use this robot to perform this grasping task with some domain randomization to improve sim-to-real performance. We then transfer to more complicated mobile manipulation grasping scenarios, such as grasping from the top of a cupboard, or grasping from a shelf, or the robot moving and grasping from different views around the table. And we show that new GraspNet can actually generalize to all these different mobile manipulation grasping scenarios and is robust enough so that the performance degradation is not too much. So for more information, such as how to extend this kind of approach for affordance prediction, please visit us at the poster session, and you can find our code on our project website. Yeah, with that, I'd like to thank you all for your attention.
All right, this is really cool work. I'm curious about the occupancy network part of the story, where it's very difficult to train such a model if your mesh or your point cloud is not watertight. So I'm assuming that somehow you're performing some sort of a heuristic to close these meshes. And I'm wondering, what is that heuristic and how much does it affect your downstream grasping capabilities?
Thanks a lot for the question. Yeah, that's a very astute observation. Yes, we do assume our meshes are watertight, and we do have to make certain approximations. I would say that it is a case that still covers a large majority of objects that we're considering in this scenario, but we would need some different way of creating some kind of approximation of the mesh if the mesh is really not watertight. Another common scenario is also if the meshes are too thin, which we've observed sometimes in this scenario. Like I've tried to grasp like knives with this approach, and then the mesh just becomes a bit too thin to actually get some information. So we probably need some kind of integration of RGB information as well, and then we could maybe get somewhere with this.
That's great, thank you.
Okay. One more quick question.
All right, is this thing on? Okay. So it seems like, correct me if I'm wrong, but it sounds like your grasp prediction score is invariant to translation and orientation. I'm wondering if you thought about including center of mass information, or gravity direction in your prediction.
Yep. Thanks for the question. Yes, I would say this is another thing that would be useful to extend the method. The center of mass would be very relevant. Like, for instance, if you were grasping a hammer, this current approach would only consider the geometry of the hammer and not consider that the end of the hammer is way heavier and then so on. I think it would require some integration of the semantics is probably the easiest way to go about it, because yeah, if it's a new object and you really can't predict the center of mass, probably the semantics is what could do it. So I would think that's the correct way to go about that.
Okay, thank you, Snail.
The next speaker is Max Spahn, and he's talking about mobile manipulation retail environments.
Cheers, everyone. Yeah, so today I have the honor to present this demonstrating adaptive mobile manipulation in retail environments in the name of all my co-authors. And there we try to bring all these nice technologies into a mobile manipulation. To an actual setup. So we picked order picking as a challenging problem because first of all, there are narrow passages, there are a big variety of products, there were humans in the round, and well, it's a very challenging problem academically, but also the business partners were quite interested in it. So what were the main questions we were interested in? So basically, how can we ensure fault-tolerant task planning and execution? So what if something goes wrong, if you're obstructed while doing it, and potentially intentionally obstructed? How can we generate safe and robust trajectories? Like what are the methods that will actually work in the wild? And then how can we easily adapt the robot to pick new products? So in supermarkets, oftentimes new products are added. So how can we be flexible to new products? So these were the main questions. And next I will present roughly the overview, if we get to the next slide. The system overview might be very normal. So we have a task planner, which kind of orchestrating everything. It picks from a bunch of symbolic actions, and I will talk about it later how it does it. We have a perception that is responsible for localizing the robot in the room or in the supermarket. Then it's also responsible for detecting objects. Then we have a motion planner. Here we rely mostly on geometric fabrics, if people are familiar, otherwise just ask me. Then we have low-level controllers and that kind of makes our system complete. Now there are many components in this pipeline, but I will want to talk about 3 of them. So the task planning. And we want it to be fault-tolerant, right? So we use behavior trees, but instead of having a behavior tree of actions, we have a behavior tree of states. And then at runtime, we infer which are the good symbolic actions to get to the next state. So basically, to reach a goal, such as here, getting the target red dot on the table, well, the first state we have to get, the table has to be free. So the robot will infer, okay, well, then I have to push first the other thing out of the way. So that's for the task planning. It was published somewhere else, so if you're interested, you can ask me about it. Next, we use geometric fabrics, optimization fabrics for trajectory generation. So essentially, geometric fabrics can encode collision avoidance and self-collision avoidance, but that's not the point here. I want just to talk about how we encode goals. Because, for example, as you see on the image, like looking at the shelf might be a very different goal than actually going to a pose. So every goal is composed out of these tuples of different points on the kinematic chain and the value, like the vector of between those 2 points. And how do we get the values of these vectors? Well, we just record a trajectory. Basically, we ask a colleague, in this case, can you please do it for this product? And then during this one demonstration, we just record the values of these tuples. And then at runtime or at deploy time, we just play it back and potentially transform it to a new product location if needed. So it's at most one demonstration per product. Yes, so that was quite robust, but then let's go to the perception pipeline. For the perception, we wanted to have something that easily adapts to new products. So let's say there's a new product added to the supermarket, how can we quickly get used to or also integrate that into our workflow? So we use a pre-trained image network that was just detecting these bounding boxes and the items, and then we have a fine-tuned protonet which just maps this into like a latent space where nice clusters appear per product. And then at runtime, we just classify these clusters. We validated in a realistic supermarket, so at the headquarters of our of the funding company, and we realized a success rate of around 60 to 70%, and most failure cases were due to picking, which is a good justification for this session, I guess. So the lessons learned, I mean, it is a demo paper, so what are the lessons learned for us? So it is very efficient to teach robots from demonstration. It is a very efficient way to convey intuition of the product to grasp. Then accurate and continuous feedback while doing the grasp or while going to the object is very important. Then in these human shared environments, we realize compliant robots are much more important than safety guarantees. So it's very key for acceptance of people, of customers to have a compliant robot. Then whole body control is quite efficient in increasing the workspace. So if we utilize as the base, we were much more successful in the grasping. And then, yeah, for these complex systems, please pay attention to software development a bit. Yeah, so this was our demo. So we will present it tomorrow again. If you haven't checked it out today, it will be between 12 and 1:30, and also during the lab tours, because I happen to be from Delft. So feel free to check us out, or just come to me and ask me any question. Thank you very much.
Thank you, Max. In the interest of time, I'll suggest going to the poster session, which technically has started 2 minutes ago, and ask Max a question there or go to the demonstration.
Okay, our last presenter is Yushu Zhang. She'll be presenting Diffusion Meets Dagger, Supercharging Eye and Hand Imitation Learning.
Hello everyone, my name is Xiaoyu and I'm here to present our paper, Diffusion Meets Dagger, Supercharging Eye and Hand Imitation Learning. Imitation learning suffers from the well-known compounding execution errors problem. Small errors made by the learn policy lead to out-of-distribution states, causing the robot to make even bigger errors. The current solution is to get expert actions on learner state, a strategy known as dataset aggregation or Dagger. However, it is hard to do in practice, so people often resort to collecting more data. Instead of doing this, in this paper, the key idea is to automatically generate observations and action labels for these out-of-distribution states. We call our framework Diffusion Meets Dagger. In more detail, we're given test data, which is a collection of expert trajectories. However, training only on this data gives poor online performance upon encountering states not covered by the expert trajectories. So we use a model F to generate out-of-distribution views. And the delta P here represents small perturbations from the original observation. We then assign action labels to these generated views, and then we just sample many such perturbed views. And this process creates an augmented data set of out-of-distribution states. So closest to our work, Joe et al. Spartan model used NERFs on test data. However, NERF assumes a static scene, so it cannot reliably generate images when the scene undergoes deformation. For example, when the apple is moved to a target. Here we show images generated using a NERF fitted to this expert trajectory. Since the grabber is constant in the camera view, we have to mask it out. Here we show no masking and two different kinds of masks. However, you can see that it cannot generate the moving apple, and the images contain many artifacts. Therefore, in this paper, F is realized using a conditional diffusion model pre-trained on large internet-scale data. We adopted recent work from Yu et al. It conditions on reference image IA and relative camera transformation to produce a new view IB. We use a U-Net diffusion model to predict noise added to the image, and the denoising is done in the latent space of a BQCAN autoencoder. And we experiment with 4 different tasks, pushing objects to a target, stacking cups on a box, pouring coffee beans from one cup to another, and sliding the shirt off the table and putting it on a clothing rack. And the experiment includes both non-prehensile and prehensile tasks, and it tests the system in many different ways. For example, generalization to new objects, 6-off action space with diverse range of motions, and also precision in reaching a goal location, such as the pouring cup or the clothing rack. So here we first show perturbed images generated by the diffusion model for the task of pushing, stacking, pouring, and hanging a shirt. So these images are in a local region around an initial image in the expert trajectory. And you can see here that the diffusion model faithfully synthesized the images. So DMD outperforms behavior cloning because it suffers less from the dagger problem. You can see here that BC gradually deviates from the intended path, and the cup is lifted further and further away from the table, and the shirt is raised too high without reaching the clothing rack. By training on these synthesized images, DMD maintains its course towards the target, and the two cups are brought close to one another, and the shirt is put down onto the rack correctly. Moreover, DMD not only outperforms BC across these three training cups, but also generalizes better to two unseen instances. Here we highlight that lack of corrective behavior causes BC to drift into irrecoverable states. But you can see that DMD prevents the system from going into such state. We also test additional load data settings for the Apple push-in task and found that DMD maintains 80% success rate with as low as 8 demonstrations. We also train on 1,400 demonstrations from a recent work UMI and test on 5 unseen cups in our lab environment. And we show that DMD still improves generalization, even in the presence of a large number of diverse demonstrations. So in summary, we propose a data creation framework diffusion misstagger that uses diffusion model to generate out-of-distribution images. We tested through a suite of tasks and show that it improves over behavior cloning effectively. Please visit our website and come talk to us at poster 313. Thank you.
Thank you. For the sake of time, I think we'll just move straight to the poster session. Thank you again to all the speakers and for all the great questions asked by the audience.